All right, guys, we might start a few minutes earlier since we have a very flexible schedule, and I think the house is already full. So I think the opening remarks is has a lot of contents, and yeah, if you are okay, we might just start now. Is that okay? Okay, sure. So welcome to our workshop on the foundation models for autonomous driving systems. And here are a few background for you guys to know. So the background or motivation for our workshop is that we all know we have the data issues, data scarcity in terms of real world public data, which is very scarce compared to the huge volumes of data scale. So we have the synthetic or simulation data to generate all the safety critical or rarely happens corner cases data. And then we have the foundation models. But to be honest, how to define the foundation models is not exactly defined in the community. So as to how to formulate the task or what methodology you're going to use, and Infor is an info or framework critical to develop a foundation model. These are all very important challenges. And after having the data and foundation models, we have the applications for the autonomous systems, whatever in driving or robotics or in broader sense in model AI. So the workshop aims to address the following question, that is, how does foundation model facilitate autonomous driving systems or autonomous systems? Apart from the workshops, we also hold the second edition of Autonomous Driving Grand Challenge, and many thanks to these host organizations. So we all know this is a little bit background as to why those tracks or challenges are set up. So in the earlier stages, we have the perception or scene understanding to recognize objects in the scene. That is multimodal understanding, whatever you are doing the object detection or mapping or tracking tasks. And then as for now, especially for the current few years, we have the end-to-end or multimodal topic, which is to try to unite different perception and all the decision frameworks together. So we have the more complex systems to unify different modules together with the tools of word model and other advanced technology, including the system 1, system 2, which is a dual system, and the super alignment and other technologies. So the big goal is to achieve more active exploration to the real world and interact with the world. That is a potentially tentative solution, the roadmap for achieving the AGI, right? So as to this, we have set a few tracks surrounding those backgrounds. So whatever you are doing the object detection, or as for example, last year, occupancy is very popular and it's a really high peak. So we want to keep that. And also, given the popularity of LLMs, we will have some challenges doing how to adapt the LLMs into the driving systems, and also how to improve the performance or how to utilize those foundation model techniques into the end-to-end domain. And also we have the predictive word model. So in this afternoon, each track organizer will give you a detailed statistics on how each track or how many participants or how many teams have participated in the challenges. So here in overall, this is a summary or statistics of all the tracks in total. So we have more than 20,000 people interested in filling the form. And actually, we have like nearly 30 countries or regions to participate, and with more than 3,000 submissions in total. And we can see this is a worldwide engagement. Interestingly, this year, we also have Africa and from Brazil, from even literally covering all the continents from the world to participants in this challenge. And mostly of them are from academia and with a decent percentage from the industry. And for this, I have specifically add this into the slides. We want to emphasize how we select the innovation prize because I think nowadays the most challenges are simply ranking the performance score, and the first or second place are naturally obtained. But for our challenge, we have set up a higher prize for the innovation prize. And here is how to select them. So from all the participating teams, for those teams interested in obtaining the innovation award, they will submit a technical report. And for the organizers, especially for the track organizers, they will seek some technical reviews from anonymous reviews, and they will obtain all those review comments and nominate to the award committee, which consists of 11 people. And we received some feedbacks, around nearly 50 of them gave us feedback. And we have noticed that there are some conflict of interest with the experts, with their institution. So we have already removed their conflict of interest. So this is probably considered. And then the final winners are announced in our website. So if you are interested, feel free to resort to the website. So for this workshop, we have an exciting lineup of speakers, Sergey Levin from the UC Berkeley and Alex Kandel from Wave and other amazing speakers. So so feel free to visit the website and have a chat with them on site. And we also have big shout outs to the workshop and challenge organizers. We are especially thanking all of the guys. Some of you cannot attend in the States because of visa, but others have come here. So if you have time, feel free to say hi to them. And also, this is a schedule. In the morning, we have 3 amazing speakers, Sergey Levin, Sherry, and Alex. And then we have the challenge innovation award presentation and for the detailed plan, their solutions on the challenge. And in the afternoon, we have also another 4 speakers on different topics. And one of the highlights in our agenda is the panel discussion, which is involve the live voting or discussion through the Slido. We want a more than a static panel discussion to prepare to discuss some prepared questions or topics. So instead, if you are interested, feel free to come here in the afternoon to propose your own questions or participants in the voting process, because we have provided 3 topics, and for each topic, they have the pros part and the cons part, and each panelist will have express their opinions on that. I'm really excited about it. And for the last one, this is a little advisement. So we have prepared an attribute standard for the alignment thing, because we really think autonomous driving is a safety critical thing. So with the appearance, with the emergence of large language models, how to align the value of the model outputs with a human driver experience is super important. So we have applied the standard, and luckily it got approved. So if you are interested, feel free to participate for the working group members to draft the standards. So that will be all. And I think we have a really amazing schedule here. So we might start very early. So lastly, I hope all you guys enjoy CPR and Seattle. Okay. So let's welcome Sergey Levin from UC Berkeley, and his expertise is on the RL, and there are lots of amazing and popular works from their group. So let's welcome Sergey.
Yeah, I think that's that one's slide. And you don't need me to do audio, right? The audio.
Yeah.
Thanks. Thank you for the introduction. Let's get started. So I have the same title as all of the other speakers today because that's the topic of the workshop, but I get to go first. So I guess my title is going to look original, and then everyone else will have a similar one. I think there's maybe like a little bit of philosophy behind that, which is this is actually the topic that's on a lot of people's minds these days in 2024. And I think that while the basic concept behind what a robotic foundation model represents, which is the possibility that we'll actually get robots, autonomous vehicles, all sorts of systems to actually behave intelligently in a broad range of situations, while that promise is extremely appealing to all of us, the practicalities of how we can bring that about raises a lot of question marks. So that's what I want to talk about a little bit today, how we can take steps towards real robotic foundation models that do for robotics what systems like GPT-4 and Gemini and so on did for NLP, and what are some steps we can take in that direction. But first, a little bit of motivation. The motivation maybe will not come at all as a surprise to any of you, but the way that AI systems used to work, the way that things here at CUPR worked maybe 5-6 years ago is, well, whatever problem you might want to address, like let's say image segmentation or classification or anything else, you would collect a data set, typically you would label it, maybe you would put in a lot of work to get crowd labeling and things like that. And then you would train a large neural network model, and there would be different kinds of architectures for different applications, you know, really good architecture for classification versus some fully convolutional thingy for segmentation, some kind of other thing for text summarization, and that would be your approach. And that was actually quite effective because if you could get a large data set like that, you get really good results out of it. The problem is that it was very difficult to make these kinds of systems flexible. The system that was trained for classification was not really a great system for image segmentation. In fact, its performance on image segmentation was undefined because it simply could not be applied to it. And that meant that for every application, you would have to go through this whole process all over again. So, of course, the way that these things work now is we don't bother with any of that. We instead train extremely large models on basically everything we can get our hands on, which is these days mostly all of the internet. And then we call these things foundation models, and we find some way to adapt it to the task that we want to solve downstream. And we adapt it either with prompting or with fine-tuning, or sometimes a combination of both of these things. So that works really, really well. Why? Well, because if you have an application for which you don't already have the luxury of a gigantic labeled data set, you can simply load up one of these large pre-trained models that is trained on all of the internet to do all sorts of things and then adapt it to your task. And that works really, really well. It's a very flexible kind of general reasoning inference engine. So what about robotics? Well, how robotics works now is that if you want robots to do something, whether it's navigation, manipulation, or anything in between, you take your task, you set it up, you do a bunch of engineering. If you want to do robotic learning, you generate lots of data, and then you have a policy that hopefully does your task in a particular environment with a particular robot. And each time something changes, then you go through this whole process all over again, whatever weird task you want to do. And the more esoteric your task is, the less likely you are to be able to get that large data set because you have to do everything yourself. And this is probably one of the biggest barriers to the use of machine learning and robotics, that each domain actually requires a lot of bespoke effort to be put into it. So, of course, the natural inference from this is, well, can we somehow do the same thing that language models and so on did for other areas of machine learning, but for robotics? Can we get this kind of internet of robotic data and somehow train something on it with a scalable, self-supervised objective, so that if you have a new robotic task, like, I don't know, sorting recyclables, you can just load up your robotic foundation model, get a few hundred trials, fine-tune it, or you can just prompt it in zero shot and get the policy that controls your robot to solve your task. Very appealing vision, but what are some of the questions that start to arise when we want to put this into practice? Well, there's a whole lot of questions, far more questions than I can possibly get through in this talk, but I do hope to get at least at some of these. For example, one question is, what kind of model should we use? And there are a few very interesting possibilities and some very strong arguments to be made for a number of different designs. What kind of algorithm or objective? The success of foundation models in NLP and vision very strongly relies on being able to use all available sources of data. And using all available sources of data means using very general objectives, which are typically self-supervised. Most data on the internet is not labeled with ground truth labels, so we use things like next token prediction, contrastive learning, and so on to provide scalable self-supervised objectives. What would be the equivalent of that for the robotic foundation model? Very big question. What type of representations do we hope to get? What is it that we're actually going to pull out of robotic foundation models? And there are very strong arguments to be made for different perspectives, including maybe they're about predicting video or simulation or modeling, or maybe they're just about straight up controlling the robot. Lots of important questions. What kind of data do we use? That's perhaps one of the biggest questions, and I'll have a few things to say about that today. But even downstream, once you get one of these things, how do you actually adapt it to your task? And what kinds of tasks can you adapt it to? What kind of things could it be suitable for? What kind of fine-tuning modalities? What kind of prompting strategies? What kind of downstream algorithms can it be compatible with? So these are all big questions, and I'm not going to answer all of them, but I will try to touch on at least a few of these today, the ones that I consider to be perhaps the biggest bottlenecks. And then for the rest, well, I'll leave that as an exercise for everyone else. So how do we build robotic foundation models? I'm going to cover this from three perspectives that are very complementary. I'll talk about some of our recent work on robotic foundation models for navigation and how we got from basic models that can control a variety of different navigation platforms to systems that can be fine-tuned flexibly for a variety of tasks. I'll talk about how we can take these ideas into the world of robotic manipulation and incorporate vision language models into the process and what that gets us. And then I'll talk about how we can combine data from very different heterogeneous robotic platforms and why we might expect that to actually be a really good idea to address that big data challenge. But let's start with navigation, and I kind of want to more or less go in chronological order because for the students in my group, this was actually one of the first topics we studied when we had started working on robotic foundation models a few years ago. We had this idea that, well, there's a lot of data of various ground robots on the internet that different research labs have put together. So we can actually put together a fairly significant and very heterogeneous data set of robotic navigation data, and we can actually start experimenting with robotic foundation models in that setting. This is work that we started doing actually at this point almost 3 years ago, so it was first published in 2022, 2 years ago. What we did is we had our own data sets that we collected for robotic navigation, and we also borrowed some data sets from other research labs for a variety of different robotic platforms. So my student, Luke Shaw, he assembled this data set that contained things from small-scale RC cars to full-scale ATVs. And then he tried to train very simple, flexible models on this. And remember, the key to make this pretty scalable is to use things that are as self-supervised as possible. So the particular training scheme that he chose to use is goal condition policies. Goal condition policies are very simple and appealing because you don't need to actually know anything about what task is being performed in the data. The outcome, some amount of time to the future, is considered to be the goal, and then you simply predict the action, and in this case also the temporal distance between the current observation and the goal. The model that he trained takes in current observation and goal observation. Now it's trained on multiple different robotic platforms, so one would think that it also needs to know something about what kind of robot it's controlling. We experimented with a few ways of dealing with this. It turns out that actually you could do something very simple. You could give it a little context in the same way that a language model gets context. The context just consists of a history of observations from the last couple of seconds. One might not think a priori that this is actually enough to do the job, but it turned out to actually do the job really well. Kind of makes sense that if you see roughly how the robot is moving from its recent history, you can infer roughly what type of robot it is and what are its physical properties. Probably not the solution that would solve this in every general case for every possible robot, but for this particular data set, it turned out to be quite adequate. The goal condition policies combined with a topological graph for doing long horizon navigation, which is a fairly standard strategy for learning-based control in navigation. And that's basically the approach. Now, it's trained on 6 different types of robots, 8 different data sets. And one of the things we were very interested in is whether we could take these general navigation models, as we call them, and apply them to other types of robotic systems. And we actually got pretty surprising degrees of generalization, which kind of makes sense in retrospect, because for navigation, a lot of basic principles are conserved. But one of the things you can see here in the top left, this is a drone. Now, the drone is being controlled by the same exact model that is trained on these 6 data sets. There's no training data of drones whatsoever in the data set. There is a little catch. The drone is pretending to be a car by flying at a fixed altitude, so the altitude is not being controlled. But the steering and velocity are controlled by the model, and it basically works in zero shot. It can fly around hallways without collision. The camera view from the drone is very different from the vehicles, but because all the vehicles have different cameras, it basically generalizes. So this is in some ways actually very unsurprising, but it is kind of nice that it wants to work in some sense. Now we can go further. This is a collage of all the different evaluations, so you can see different kinds of robots, outdoors, indoors, navigating around furniture, navigating around hallways, navigating around trees, a lot of variability. But of course, sometime around 2023, the thing that you were supposed to do is take these things and put them together with a large transformer, which is what we did. And the next iteration of the system, which we call the visual navigation transformer, was quite a bit more general. Now, this model is still very small by language model standards, so it's about 150 million parameters, about, let's say, 2 orders of magnitude smaller than even the open source language models, but it does the job because the data set is also a bit smaller. And now it can generalize to other systems. For example, it can control a quadruped. It's not moving the legs here, it's just selecting the direction. So just like the drone, the quadruped is pretending to be a car, but nonetheless, different dynamics, different turning radius and so on, it basically does the job. We can also adapt it in interesting ways that sort of resemble prompt tuning. So we could take that goal encoder. So there's the goal image goes through an encoder. We can cut off this thing and train a different encoder that encoded the same tokens that we're using to represent the goal during pre-training. And instead of encoding a goal image, we can encode some other task modality, like for example, turn-by-turn instructions, like the kind that you might get from Google Maps. Basically embed them into the same goal space, very much like how somebody might train a multimodal language model where they embed images into the token space, token embedding space. Here we embed other task modalities into the embedding for what would otherwise be a goal token. And then we can get this thing to do fun things like drive vehicles in Carla using a few hundred fine-tuning examples. So what is being fine-tuned is actually not the entire model, it's just this goal encoder to basically take turn-by-turn instructions, put them to the same transformer that's pre-trained on all that real-world robotic data. We can do some fairly rudimentary driving in Carla. This model is actually publicly available and people have actually used it. People have used it from all over the world from let me try to remember what these are. So people send us something every month about what they do. This video here, this is from a university in Estonia that used this for orienteering. So they put this on their robot and it drives around the Estonian countryside and locates landmarks, which is pretty cool. This is from Finland, I believe, and this was a project on semantic navigation where these folks, they had their own system for the semantics part, and then they just used Vint for the actual navigation layer. And this is a drone project from, I believe, from Princeton that also used Vint as, in this case, a baseline. So these are kind of small things, but I think what's interesting here, and for those of you that work on robotics will probably recognize this is pretty unusual, is that we actually have a model where we just put the weights on our website and people can download the weights and they can run it on their robot. And that's very rare in robotics. Like usually some people can take your idea and implement it. Sometimes they can take your algorithm and run on their own data, but it's pretty unprecedented for someone to be able to literally take your model and run it on their own robot driving through the Estonian countryside. So that was pretty rewarding for us. And of course, we can do fun things like take it to a conference and run a demo. This is at, I believe, the BARS conference in the Bay Area. Interestingly, we never trained the robot on data around humans. We did have a lot of data in forests. So I have this hypothesis that the way it navigates around humans thinks these are all trees, but it does pretty well here. Now, a lot of the really fun things we can do with foundation models have to do with fine-tuning. So one of the things we wanted to see is, can we fine-tune with RL? Can we fine-tune autonomously? So we took this multi-robot data set. We actually modified pre-trained to use offline RL rather than supervised learning. And then we tried to see if we could fine-tune it to a little RC car to learn to race in indoor and outdoor areas. So we ran an online algorithm, and what you saw there in that clumsy video was the beginning of training. So it's initialized from other robots. The active space is actually different. Instead of waypoints, it's controlling directly steering and gas, but that's just a different head on top of the same backbone. And then after a bit of training, after about 15 minutes, fine-tuning, I should say, with online RL, this is kind of what we get. So not perfect yet, but it kind of has the idea. It's going around the hallway. Sometimes it gets a little stuck on the walls. And then 25 minutes in, it actually does pretty well. Now, in the third-person video, it kind of doesn't look like it, but this RC car is actually driving around this hallway at pretty much the same speed that Kyle, the lead author on this project, would do from the same first-person camera. And I will say it actually looks a little faster from the first-person view. Turns out that if Kyle uses his own eyes, he can go even faster. So human eyes beat robot eyes, but from the first-person view, it's about the same. Now, this is pretty cool because those of you that are familiar with DeepRL will recognize that training from pixels in 25 minutes is kind of surprising. So that pre-trained initialization from all those other robots is actually buying us a lot in terms of efficiency. Same exact thing works outdoors, so this is fine-tuned to drive on grass. It figures out cool strategies like going on a little concrete walkway in between the checkpoints. So the checkpoint's on the lawn, but then in between the checkpoints, it goes on the concrete path because, well, you can go faster on the path. Here's a first-person view. Pretty tough task. Like, there's a lot of camera shaking. All the grass gets in the way. And this is also fine-tuned with online RL in about 30 minutes. So that's cool. We're getting a lot of cross-robot capability, generalization, and the ability to fine-tune to different situations in different ways using different algorithms. All right, so that's navigation. Now let's take this a little bit further. Let's go into an area where there's a lot more semantics, and that's robotic manipulation. So in studying cross-embodiment robotic manipulation, of course, one of the first things we had to do, just like with navigation, is assemble a data set. And this was a fairly complex effort because there is not as much robotic manipulation data lying around. So we had to go to many more places. So this was work that was led by Quan Bong from Google and my postdoc Carl Perch. And a large number of other folks contributed. So this is a pretty big effort. What Quan and Carl did is they put together a kind of a coalition of about 34 different research labs. I guess 32 if you don't count their own labs, Berkeley and Google. And basically they called everybody up and they were like, hey, if you've got robotic manipulation data, donate it to science and we will give you a checkpoint in exchange. Most people didn't really know what the value of a checkpoint was, but it was fun, so they sent over the data. And then Juan and Carl spent a few months just converting everything to the same format. We ended up with 311 scenes from 21 different institutions, a total of about 1 million episodes, 22 different kinds of robots, 527 different skills, depending on how you count, and it was kind of a giant mess. So there's lots of histograms, lots of pie charts and so on, but I think that in a talk like this, it's probably easiest if I just show it. Apologies, let me restart this so that the videos will play properly. Sometimes PowerPoint gets a little bit with this. All right, so there's our videos, and you can see that there's a lot of heterogeneity in there. So all of the trials that were used in the actual experiments consisted of single robotic arms with parallel jaw grippers. We did have other types of robots in the data set, but we didn't use them in our final experiment. So these are just single arm parallel jaw gripper. But even there, you can see there's a huge amount of variability. A lot of variety of viewpoints, a lot of variety of robot types. They're doing all sorts of weird stuff. Some of them are making coffee, some of them are loading dishwashers, some of them are doing whatever this is. So there's a lot of stuff going on. It's very heterogeneous. And compared to the kind of data sets we use for robotic learning, it's basically the Wild West. So what did we do? We took all this data, we trained a language condition model on it. We actually trained two types of language condition models, but I'll tell you about the simpler one first. So the simpler one was structurally very similar to Vint. It was the model is RT1, which is actually which came before Vint, but same design. It's a transformer that takes in the current observation, some kind of task definition, which is in this case language, and then predicts actions. And then we took this model and we sent it to 7 of the labs that donated data. Here you can see videos from 4 of these. And we asked them to basically take this model and compare it. Compare it to what? Well, this was basically the first real cross-embodiment manipulation model. So we asked them to compare it to whatever their best model was for their data set, because they made the data set, so presumably they knew what to do with it. So what you can see here is the gray bar. This is just a baseline where we asked them to train the RT1 model, the same model in just their data set. The rainbow colored bar, this is the cross-embodiment model, and whatever bar is here on the left, this colored one, this is their best method. And on average, this is the average score, the cross-embodiment model was about 50% better in terms of success rate than whatever the best model that each lab had. And this is actually like, to me, this is actually even more remarkable once we kind of pause and think about what this means, because whenever you do research, especially in robotics, I think roboticists are even more guilty of this than most others, you kind of favor your method a little bit. Like you set up your task and then you have your method and then you kind of change your task and then you change your method and then eventually your method is really good for your task. Here we just sent a model to a bunch of people. Admittedly, these were very capable researchers, but they weren't like incentivized to make this model look good. They were just incentivized to drop it in there and run it compared to their method, which they've been tuning on their task, and just see what it does. And it does 50% better. So I think it's actually pretty interesting. I think this actually suggests that there's this benefit of generality, where the general purpose model is actually doing better on the specialized tasks than the specialists that were designed for that task. It's just kind of old news in the world of NLP and computer vision, but it's not something that roboticists are really used to seeing. Now, I mentioned there were 2 kinds of models. There is a second, more sophisticated model that we experimented with. And to tell you about that one, I need to provide a little bit more backstory. So one of the things we had been doing separately from this, but in parallel, is investigating other kinds of model architectures that could be suitable for robotic foundation models. And one of the things we were really interested in is whether large language models could be fine-tuned to control robots directly. So we had done some work on large language models doing higher level control with things like SACAN and PaulMe, but we wanted to see if we can actually have the robot policy itself be a language model. So this was work that was done in mid-2023, and what we tried to do here, this is a project called RT2, is we took a vision language model. This was what later became known as PolyX. At the time, it had a more secret code name. And PolyX is basically a classic multimodal large language model. So it's a language model backbone that is fine-tuned with an EIT encoder and encodes images into the same token embedding as the language model. Very classic recipe. And then we took this thing and we then fine-tuned it to output actions. Now, how do you get a language model to output actions? Well, there's some really clever ways you could do it, but one thing you could do is you could literally get it to print numbers, like, literally just like the ASCII characters, and that actually works. There's probably much better ways to do it, but we didn't have time to figure out better ways, so we just had to print numbers. And then you could do stuff like you could give it commands like put the strawberry into the correct bowl, and it will basically speak robot actions and move the arm and do that task. Now, this might seem like a little bit of a funny exercise because you're kind of taking this model that's designed for things like visual question answering and then torturing it to output numerical action values. So why might you want to do that? Well, it turns out that if you do this right, you actually inherit a lot of those rich semantics, a lot of that semantic knowledge that's contained in the vision language model. So you can do fun things like specify tasks for which the robot data can't possibly be adequate to get the robot to do it. Like you could say, move the Coke can to Taylor Swift. I promise you we did not have any robotic demonstrations that have pictures of Taylor Swift, but the robot definitely knows who Taylor Swift is, and if Taylor Swift needs a can of Coke, it will gladly give her the can of Coke. You can also do fun things like give more nuanced instructions and actually use the semantic reasoning capabilities in language models to essentially do chain of thought where the end result is an action. You could say things like, bring me a drink, and it will figure out that to bring a drink, it should pick up the 7-Up can because the 7-Up can is a drink. So if you just told a regular non-BLM policy, bring me a drink, it would understand that just because of the nature of the labels in the data. You can figure out, well, 7-Up can is a drink, there's a 7-Up can, so let's output the actions to do that. You can even do more complex things, like you could say, here's a picture of here's what the robot is seeing, there's a table with some rock and a sticky note and so on, and it says, I need to hammer in a nail. What object from the scene might be useful? It figures out that it's a rock, and then outputs the actions to go and pick up the rock. So these are fairly rudimentary examples, like, giving the Coke can to Taylor Swift is probably not the be-all end-all application of robotics, but it does give us that little sense of how the deep semantic knowledge and reasoning capabilities in vision language models could actually be integrated into robotic control in an end-to-end way. So, of course, what we want to do with our large cross-embodiment data set is see if this kind of vision language model could also improve from integrating data from many different robotic systems. This is not at all an obvious hypothesis because, of course, the vision language model already makes this policy very, very powerful. So one might suppose that the null hypothesis, that basically the VLM already gives it so much generalization power that all those little robotic data sets wouldn't really help, that null hypothesis is quite probable. So we wanted to test this out, and we created RT2X, RT2 train on cross-embodiment data. And we stress tested it on a variety of tasks that they're almost like designed like a robot intelligence test. So we gave the robot a variety of semantically fairly challenging tasks that involved relationships between objects, like move the apple between the can and the orange, those kinds of things. These were basically designed to be things that were pretty difficult even for the original RT2 model to handle. And this is what we saw. So we saw that just by changing the data set, including that cross-embodiment data for many robots, performance on this suite of fairly difficult semantic tasks jumped by about 3x. And that's a very big improvement. Here are some more examples of what these tasks look like. A lot of them have to do with these semantic relationships. Put the orange into the pot, move the orange near the pot, object relative motion, move the apple between the Coke can and the cup. And it turned out to be a lot better. So you get a lot of benefit out of having the rich semantics and vision language models. We also get a lot of benefit from including all the robotic data you can get your hands on, even if it comes from other robots. And I'll also mention the robot we tested this on. This is the Everyday Robots robot. It was the robot that was the most overrepresented in the data set. So this was the robot for which there is the most data. And even the majority robot actually benefits significantly from all those other data sources. Okay, other things that are maybe more interesting to this audience in this area, if you want to get into this cross-embodiment robotic foundation models research yourself, we released a model called Octo, which is a open source model designed for cross-embodiment research. It's a very flexible model that can take in different types of task specifications, language, and goals, and can be readily fine-tuned to different output modalities. So Octo is basically, you can think of it as like a really big version of Vint with a variety of different input modalities. Octo does pretty well in zero-shot evaluation, so we compared it to RT1X and RT2X. These are what we refer to as in-distribution tasks. So these are not tasks that are meant to stress test generalization. They're meant to test basically your ability to fit the data. It does pretty well in those things. So these are 3 different robots that were visible in the pre-training data set, and it does significantly better than RT1X, and actually often matches the much larger RT2X model. The RT2X model is still better when it comes to difficult generalization problems, but for the in-distribution tasks, it's very similar. We can also take the Octo model and we can fine-tune it with a small number of trials, something on the order of hundreds of trials, to a wide variety of different tasks, and it's really designed to be fine-tunable. It can be fine-tuned even to other action spaces like the bimanual system, this is the ALOHA system. So these are a few videos of the kinds of tasks that Octo can be fine-tuned to. And that's really important because, of course, if you want to grab this model and use it yourself, chances are you're going to be fine-tuning it to your own data. Now, of course, if you want the VLM component, very recently there was a project, a collaboration between Stanford, Berkeley, and a few other labs called OpenVLA, which aims to provide an open source vision language model fine-tuned for robotic control. OpenVLA is exactly what it sounds like. The core VLM that it's based on is prismatic VLM, and it's fine-tuned to output robotic actions with the same RTX dataset. OpenVLA generalizes really well, so this is another one of those large generalization evaluations. It's actually a different one than the one that was used in RT2X, just because this was done at a university with a different set of tasks. But performance is pretty good. We were able to get a comparison to RT2X using the API version, and yeah, it's pretty good. On in-distribution tasks, it kind of is similar to RT1X and Octo, but on other distribution tasks, it's quite a bit better. All right. Now, in the last portion of today's talk, I'm going to talk about how we can push this cross-embodiment idea even further. So far, we had a little bit of a trick. All those navigation experiments all were first-person navigation on a 2D plane. Even the drone was pretending to be a car. It basically goes to 2D checkpoints, PD control to a 2D location in front of it. The arms were all single arms with parallel draw grippers. So that's pretty convenient because you can use forward kinematics, same action space, etc. But what if you want to use all of the embodied data you have from whatever kinds of robots you might get? Can we push this even further? Can we, for example, take our data with robotic arms, incorporate data from cars, incorporate data from legged robots, arms, vehicles, everything we get our hands on? And why might we expect that to be a good idea? So there were a couple of papers that we released recently that studied this. The first one by Jonathan Yang, called Extreme Cross-Embodiment, aims to narrow in on a very particular aspect of this problem. Can navigation and manipulation data be combined to lead to better generalization? So what we did in this work is we took data from robotic manipulators as well as mobile robots, legged robots. Again, legged robots just control in terms of weight points, autonomous driving data, and ground robots, and tried to see if we can combine it all into one. 1 second, let me start this. Just keep breaking. Yep. Okay, so here are just some animations of the kinds of episodes that are in the training set. You can see that there's some manipulation with wrist-mounted cameras and navigation on different kinds of platforms. And the reason that this might help is that at some level, the physics and geometry of the world is the same, whether you're controlling a robotic arm or a ground robot. So this is Jonathan and Catherine prepare these little videos to kind of illustrate that point, that you can see that if you're trying to approach the apple on the table, or you're trying to pick up the strawberry, you have a wrist-mounted camera versus first-person camera on the ground robot. The relationship between your actions and the change in the viewpoint is basically the same. So there's the same kind of visual servoing primitive, the same kind of geometry, the same kind of physics. So insofar as you can get at those underlying concepts, you'd expect them to be conserved. And therefore, you'd expect to see forward transfer. You'd expect to see positive transfer across these embodiments. So does that happen? If we train one model across all of this, well, first, does navigation help with manipulation? So if we want to solve manipulation problems, we include navigation data. Does it make it better? Of course, Probably want to know what does make what better. So these are just some videos of those manipulation tasks just to remind you. And these, the different groups here are different tasks. The different bars are different models. The solid green bar is trained on only manipulation data. The striped green and blue bar is trained on manipulation and the GNM data set. The GNM data set is the one that we used way back at the beginning of the talk for those cross-embodiment navigation policies. And the green, blue, and yellow striped bar also includes BDD100K, which is an autonomous driving data set. And you would think that autonomous driving has very little to do with grasping strawberries, but it turns out that even that helps. So the average you can see here, about 20 points of improvement from only manipulation to including all of the navigation data. So knowing how to drive really helps you pick up those strawberries, and now it's a proven fact. Does manipulation help navigation? There actually, the evidence is more mixed. We're not sure why. Maybe it's because navigation data is so much more diverse. So it does help a bit, but definitely not as clear cut. So this is a more complex experiment. These are the videos. The blue bar is only the GNM data. So this is the data from those 6 different robots driving around. The yellow stripes include driving data. We're probably underfitting. We need bigger models and more GPUs. When you add in the green stripes, that's the manipulation. And then green, blue, and yellow is all of the above. So pattern here, well, probably the real pattern is that driving data is making us underfit, and we need a bigger model and a bigger GPU. But if you disregard that, it does actually seem like it. So definitely more mixed, definitely more research needed, but it seems like something good is going on. All right. Now there is a little trick that I wanted to tell you about that we used here. The trick is that in all these cases, we were using egocentric cameras, so wrist-mounted cameras on the arms and first-person cameras on driving robots, and actions that are in the coordinate frame of the camera. So the action space is actually the same for all of these systems. So it kind of makes sense that, yeah, like you kind of make it into a visual sobering problem and you benefit from visual sobering. So can we lift that assumption? Because aligning all those action spaces is kind of a pain and it might not even be possible in the general case. So can we make it even more extreme and literally just dump a bunch of different robot embodiments into a model and train one big model to control all of them? And it turns out that we can. So here's the design. This is a model that we called Crossformer. It's a model that has basically different action heads for different action spaces, but otherwise shares most of its parameters across different robotic configurations. And finally, for these legged robots, we're actually going to control the legs. So here, every robot is controlled in its native action space, controlling the legs for a legged robot. Single arms are controlled in end effector space. Bimanual systems here are controlled in joint angle space because that's what prior work did, so different action space. And then the ground robots are controlled in terms of waypoints that are about a meter in front of the robot, so basically 2D locations on the ground. So it's one big model treatment, all of this, and it does pretty well. Here, this is kind of one of the most surreal comparisons I've seen in a robotics paper. All these different groups of bar plots are different types of robots, ranging from single arms to Aloha, which is dual arm, Locobot, which is the ground robot, and Go1 is a legged robot where you're controlling the legs. Yes, this thing actually helps. It does better than single robot policies, and it does better than whatever is the best environmental model that can ingest all the data. It also does significantly better than the previous method I discussed, which is not all that surprising because this model is really designed to deal with variable action spaces. But it's maybe a little bit more compelling if I actually show in detail what each of these embodiments looks like. So this is just a sampling of the kinds of things that we tested. These are the single arms, so these are basically language conditioned or role conditioned manipulation tasks. This is the bimanual system, it's the Aloha system. It doesn't look all that different because it's just 2 arms, but it's controlled in a very different way. It's controlled at 50 hertz with large action chunks and joint space, whereas these are controlled at much lower frequency in end effector space. So they're much more distinct actually than they even look. These are the navigation experiments. For the navigation experiments, these models are also combined with topological graphs to do long horizon navigation. So this is embedded in a pretty different kind of overall robotic system. The legged stuff, still running this in the real world. So this is a simulated experiment, but yes, it is actually moving the individual legs. So the action space here is 12-dimensional control of step points for the leg joint angles. Okay, so to summarize, I think from these discussions, perhaps there's an image forming of what my opinion might be about how we build a robotic foundation model. That opinion might be actually fairly straightforward. Take all the data you can get from all the robots you can get your hands, all of them. And then take a model that is already very, very good, like a vision language model, turn it into a vision language action model, fine-tune it on the robot data, And then you have your robotic foundation model and then use it in as many possible ways as you can. Use it in zero shot, fine-tune it with some prompt tuning to do some driving, fine-tune it with RL to do fast racing, utilize it for downstream instruction following, go wild, use it for whatever you want. And as long as you use a really nice big visual language model, and as long as you use a really nice big diverse data set of all sorts of different robots, maybe you'll get some approximation of the kind of capabilities we want out of robotic foundation. That's it for my talk. We recently started a company called Physical Intelligence to basically see if we can instead of these things for real. This is very much a work in progress. I'd love to talk to you more if you're interested. But I want to conclude. I want to thank my students and all of my colleagues who carried out this research. And I'd like to thank you for listening.
Any questions from the forum? Yes. We have a mic. Yeah. And is quiet.
Can you share some learnings about what's important when you file all the data together? Maybe from different sources.
Yeah, so the question was, what did we learn and about what's important when we file all this data, data together from all the different modalities? There are a lot of things that are important. Unfortunately, these are things that are hard to put into concrete rules. One thing that's really important, and this is very annoying, is balancing the data. It is extremely important to balance the data properly, and we have no idea how to do it. And if you do it wrong, then the thing doesn't work. If I had to guess as to a principle, the principle is you want to weight your data in proportion to the amount of useful information contained inside of it. Unfortunately, I don't know how to determine the amount of useful information contained in the data set. But this really matters. And it's not as simple as just upweighting the robot you're testing on. It's not as simple as upweighting like the coolest robot or the most interesting robot. And it really, really matters. And this is very important. For what it's worth, the folks that are working on language models and vision language models have to deal with the same thing. So the choice of your trading mixture is important. So maybe it's kind of comforting, but it's also important for box. Other stuff. We do have to still take some care in regard to action spaces. I think we're getting a lot better at handling heterogeneous action spaces, but it's very easy to go horribly wrong with like, like I have velocity control, but my velocity is represented in like degrees per second instead of radians per second, and it's not normalized correctly. So all those little details kind of matter. But I think that's the thing that's actually getting easiest and easiest over the last year. So maybe a year from now, this won't be as big a deal. There's probably half a dozen other things. Unfortunately, they all fall into that category of things that are where I don't have like really good answers about what to do, just things that are difficult.
Yeah, so thanks for the great talk. I'm Renshaw from Remote Research. So for the last section, you show that picking up using the travel data can help picking up the strawberry. Do you have any guides why can that happen? And also if we do in the reverse way, picking up the strawberry, will that help the dragon?
Yeah, that's a really good question. So I think there's a lot of speculation. One thing I will tell you, which we did actually examine to the best of our ability in the paper, and I would encourage you to check out the paper for that, is the degree to which what's actually being transferred is essentially like a visual servoing skill, and that does appear to be happening. So we have a few experiments that provide circumstantial evidence for that, and that kind of makes sense because basically, if you're doing navigation, you learn some very basic geometric things. Like if an object is small and far away, and you move towards it, it gets bigger, right? And that's true for whether you're reaching for a strawberry or driving a car. I think that it remains to be seen further on from that, the kinds of concepts that can be effectively inherited. And this is a very difficult thing to study because the ability for a model like that to distill out the fundamental concepts instead of pick up on surface level patterns requires enough data that the true underlying concepts are actually apparent. So it may be that the much more sophisticated kind of transfer will be hard to understand until data sets are at the right scale, until you get that kind of emergence effect that we've seen in large language models. So the short answer, geometry, visual servoing, the basics of how 3D worlds work. The longer answer is we won't know for sure until we scale it up enough.
Yeah, all right.
I have a short question. So there's a clear trend that usually people are adopting the billion scale large language models as the backbone for robotic tasks. But the thing is, the robotic instructions are usually not as complex as writing fictions, answering a variety of questions. So is there really a need to adopt such large capable model as the backbone for the robotic tasks, as robotic tasks are usually requires the efficiency?
Yeah, that's a really good question. I'm glad you asked that. I would like to give my robots more complex instructions. I would like to tell my robot, you are a robot bartender. Be a good bartender. Now, any language model worth its salt can figure out what that means. If you ask GPT-4, what do you do to be a good bartender? It'll probably tell you a lot of things, probably more things than you even want to know. So the knowledge is in there, which means that we can essentially, in the future, treat these kinds of models almost as like robotic operating systems, where you write your robotic application in English. Like you take literally the manual for the job that you want the robot to do, give it the manual, and it does the job. And I think that'll be a very complex problem. We're nowhere near that. Like right now, we're picking up pictures of Taylor Swift, but I think we'll get there someday. And I think that large multimodal language models will help us get there. Yeah, very good question. I unfortunately don't have a car that I can use for autonomous driving experiments. I do think that'll be really fascinating. Now, I think there will be additional challenges that come up, but I think that one of the really interesting things about autonomous driving is that in contrast to like driving one of those robots through a hallway, autonomous driving is very semantically rich. And sometimes, you know, a lot of what we do when we actually build practical autonomous driving systems, we bake that semantic richness into a bunch of rules and we work really hard to encode them. But there are semantic rules. Like you could, in the same way as the robotic bartender, you could literally give like, you know, the state of Washington driving exam to the VLM and see if it'll figure out how to drive the car with some rough approximation to the rules of the road. I think that'll be really interesting to study. I haven't gotten to that, and I don't have an autonomous car, but if anybody's interested in it, OpenVLA is out there, and you can grab it and you can fine-tune it for driving. You can give it lots of complex prompts and see if it'll yield to pedestrians and do all the other things that maybe drivers in Washington State aren't as keen to do. Yeah, any other questions?
Yeah, wanted to get your opinions on, are you familiar with the VJEPA architecture from the where do you see incorporating that into your future?
Yeah, this is a really good question. And I think that maybe something that is underlying your question is the role of models and prediction as compared to policies. The question was, well, how does this compare to the VJEPA architecture, the one that Jan McLean was famously advocating? So I think the bigger thing underlying this question is the role of models in prediction in this context. Everything that I presented is very unashamedly about policy learning. And policy learning makes a lot of sense if you want to kind of get the ball rolling on these things, because, well, policy learning, like if you get a policy, you control the robot and you're kind of done. At the same time, there's a very good argument to be made that prediction is a really good objective to use in this context, because you can learn to predict from lots of data that is difficult to use for policies. And it makes sense to incorporate prediction to things like this. In fact, we already did that to some degree, to a very limited degree in the VINT model, because the VINT model was actually predicting reachability. Now, reachability is not the same as predicting future states, but it gives you a little bit of a proxy of that. It's kind of value function. My own, this is maybe getting too much into the weeds, but my own opinion on this is that actually there is not a dichotomy between prediction and policies. There's actually kind of a smooth gradation where you can predict progressively higher and higher level concepts. So things like reachability, value functions, they're also predictions. They're a little bit model free in nature, but they're a little bit model based, all the way to full on prediction of states. And I would argue that the JEPA type design is kind of also in that middle ground where it's, well, it's not predicting raw states, but it's predicting embedded representation. So I think there's a big spectrum there between fully model free prediction and fully model-based prediction. I think exploring that spectrum is a really fruitful thing to do, particularly in regard to getting better self-supervised learning objectives from large amounts of sequentially structured data.
Yeah, we might have the last question.
And I wonder if those kind of transactions from robots and offline, like,
yeah, that's it's an interesting question. I think there's actually a lot wrapped up in that. So there has been a fair bit of work on incorporating vision language models into systems that involve an ensemble of different models. And the way this pertains to your question is that one design that folks have explored to a considerable degree is something where there are separate perception systems that are queried as tools by a language model or vision language model. And that's actually kind of a pretty neat design, because you can imagine that, like that chain of thought example I showed with the rock, you can imagine a much more advanced version of that says like, hey, I need to find this type of object. Let's call an object detector, figure out where it is. Let's paste in the output from that object detector into my prompt and use that, and then call some other model and so on. So you can kind of stitch together a system out of these different models. In the olden days, we would do this in robotics using ROS and using lots of subscribers and publishers. But now that it's 2024, maybe we do this by using a language model to actually make those queries to those tools. And you could imagine it almost like as an embodied chain of thought process. There's quite a bit of research on this, including from my colleagues, including from many other labs. I think it's a pretty exciting area, and we'll see a lot of progress in that over the next year.
All right, thank you. That's thank you. Okay, we have a emergency issue. I just told by our technical staff here that this room is fully capacity due to the fire regulations or whatever reason. We cannot have so many people standing out there. So I was required to tell you guys. So please, if you have yeah, we cannot hold so many people here, right? Okay, so if you are standing back there,
You guys need to exit the room. The fire marshal will take control. You guys are not in a seat. You guys need to exit the room.
okay. I'm sorry for that.
We will put the recording on the website.
Yeah.
Yes. Okay, let us continue.
We can start until everybody who's standing needs to. If you are standing and you cannot find a seat, you have to exit the room. Can you find a bigger room or not? Too late.
Unfortunately, yes.
Can you add more chairs?
Unfortunately, not.
These
guys are part of the unit.
Yeah, they are. Okay, I'm sorry for you guys. And okay, let us start. We might welcome the next speaker, Sherry Young from the Google DeepMind and UC Berkeley. And his talk is also, he has a lot of famous works. I believe you guys all know it, including the Unify, the series of work. So her talk is focused on the foundation model as real-world simulator. So let's welcome Sherry.
Let's see if I can speak loud enough for people outside also here. Yeah, thanks for the introduction. Very happy to be here to talk about foundation models as real-world simulators. So when I look at the past 10 years in machine learning, I think the most exciting advances are in 2016, where AlphaGo outperformed human Go players, and more recently, large language models and large video generation models are able to generate highly realistic language and videos. And if we were to step back a little bit, try to understand the technologies that empower these advances, we would see that technologies that empowered AlphaGo is actually research going on in this community known as decision making. So in decision making, the goal is to have computers automatically decide on actions to execute in the real world. And as these actions are executed, the real world gives some feedback and some what happens next. And we want to utilize these additional information to train an agent to know how to act in the world and how to act better according to the feedback. And we saw that this worked pretty well when we have a really good simulator, such as the example of Go, and we have achieved that in 2016. But the progress in decision making has been slow in terms of having more real world impact beyond Go. And what happened recently is that we saw these large internet scale video and language datasets being used to train these video and language foundation models. So then my question, or the focus of this talk is, can we utilize these internet scale datasets to essentially learn simulators of the real world so that this can bring us back to the initial decision-making setting that we wanted, which is to train agents in a real world like simulator so that it can learn how to solve real world tasks beyond just the game of Go. And before I go into the details of how to learn a simulator, let's first understand how could decision-making enable agents to perform better than humans. And if we were to look at when decision-making has worked, let's take AlphaGo as an example. And what happens is that these agents usually have some ways to imagine into the future, right, through these simulated rollouts. And as a result, the agent actually knows more about what happens in the future, like, for example, the outcome of a particular Go game. And then with this additional information, the agent kind of comes back in time and optimizes the current decision. And because the agent knows more about the future than humans, that's how they outperform us. And for this to work, there are actually two things that are very important. First, we need a perfect simulator. The simulator that the agent uses to imagine into the future has to be the simulator, has to follow the same rules, right, when the agent plays with humans. And on top of that, we need good decision-making algorithms so that we can search and plan in simulation to find the best action. And because the simulator is perfect, then the action found from simulation transfers directly to the real world. This is the setting of AlphaGo. But then once we go beyond these game settings, it's actually really difficult to expect that we have a perfect simulator. These are the simulators that people often use in robotics, which is quite different from what real robot looks like in practice. So as a result, when we develop these algorithms in simulation, the best actions found in these simulated settings rarely transfers to the real world. And of course, we can try to run real robots in real time and try to learn policies by running real robots, but it's very expensive and not very safe. Then the intriguing question is, what if we can learn a realistic simulator? And I'm just going to use the world model as a loose definition for a learned simulator. I will show you what that means later. But you can imagine that in this setting, once we have a realistic simulator, then we can develop these algorithms in simulation. And because the simulator is very realistic, then the actions found in simulation transfers. So given this motivation, I will talk about a series of work, starting with how we can learn world models or learn simulators from internet scale language and video datasets. And next, I will talk about, after we've learned the simulator, how can we combine the simulator with decision-making algorithms such as reinforcement learning and planning to solve real robot tasks. And lastly, I will talk about various challenges and next steps that I think are important in terms of learning real-world simulators using foundation models. So let's begin with learning world models from internet scale datasets. So this first project was really kind of inspired by this observation that we made from language models, that one reason that, in my opinion, language model works so well is because text is actually a unique representation of information. What do I mean by that? Well, different types of information, right? Wikipedia articles or math equations or code can all be represented as text. So it's a very general type of representation or data format. And not just text is a unified representation, but text generation is actually a unified task interface. For example, these different types of tasks considered by the NLP community, such as sentence completion, translation tasks, and also dialogue bots, right? These tasks used to be considered separate tasks, but now they're all casted into a natural language generation task. And as a result, we have a unified representation of information and a unified task interface. We can just gather together the internet scale data and pour these data into the single model using a single training objective. So this has worked great for large language models, but large language models don't really have a visual component, right? And when we talk about learning simulators, there has to be a visual component. And then the bold assumption that we wanted to make is that this actually is true for videos as well, in the sense that video is also a unified representation of information, and that video generation is a unified task interface. So let me show you some examples. For example, if we have some videos of human cooking in the kitchen, and if we condition this video generation model on the initial frame and also on the language actions such as cut peppers, and we train the model to generate this video that corresponds to the execution of cutting peppers, then in some sense the model has learned the notion of cutting peppers. And similarly, to the same model, once we change the dataset into giving it some initial frame of some robots and some low-level control actions like delta x, delta y, how much to move the robot endpoint, and we try to generate the next frame. And in this case, the model has learned somehow of a real-world physics in a sense. And again, we can actually feed the simulated data as well, right? We'll have a lot of simulated robotics data sets. We can condition on the frame and some control to try to predict the next frame, and then the model has learned simulated dynamics. And when we have these panorama scans or 3D data sets, for example, we can also introduce actions by language such as turning towards a certain direction. We can generate a video that corresponds to that motion, and in some sense, the model has learned what does it mean to turn 90 degrees to the right. And even when we don't have videos, so we only have images, right? We can still try to generate the image from the natural language input. And in this case, the model has learned notions of what a free speech should look like. So this is like just to show you some examples of why video generation is a unified task or unified interface, right? We can merge a lot of different data sets of humans, of robots, or simulated data, of navigation data, manipulation data, all into one model, right? So I want to go into a bit of a detail of how exactly we implemented this model. So I'll have to go into a little bit of background in the model that we use, which is a diffusion model. So diffusion model was initially developed for images, where when we have some clean image, we can corrupt the signal in this image by repeatedly adding Gaussian noise until we have a fully random image. And what we're going to do during training is we're going to learn this reverse schedule epsilon theta by minimizing the mean squared error between the noise that we added to the image and the reverse schedule we're trying to learn. This is our training objective. And during inference, we can start from a noisy image, and by repeatedly subtracting this learned noise schedule epsilon theta, we can generate a new image. And we can further condition this noise schedule on some control input, some language such as I want to generate an image of a robot, or I want to generate an image of a human. So this is diffusion model for images. What about world models, right? And in world modeling, oftentimes the language is usually specifying some activity, for example, happening in the foreground. Wiping table have this robot. But then the background usually needs to stay consistent. So to ensure that, we replicate the first frame across time and pass this replicated future frames into the video diffusion model to ensure the temporal consistency. And next, we're just going to condition on, in addition to conditioning on the first image, we're also going to condition on some language instruction, such as wiping table, to generate the visual execution, these video frames that corresponds to the motion of wiping table. And lastly, we can also use these temporal super resolution to generate coarse frames into the future first, and then condition on these coarse frames to fill in the gaps, right, to generate more detailed videos. So this actually allows us to generate videos of arbitrary horizons by just either inserting these intermediate frames or condition on the last frame of the previous generation. With a new language instruction, we can simulate that again. I will show you an example later of what happens. And so that's on the modeling side. And on the data side, we really went out of our way to try to gather together as much video data as possible. So you can see some robot data here, real robot data, simulated robot data, human activities such as Eagle 4D, and these panorama data sets, and also internet scale text image data sets such as Lion. So I want to show you exactly, we've been talking about this world model or real world simulator for so long. I want to show you what this looks like. So in this setting, we actually have diverse scenes to choose from. And really, if the server is running, you can really upload an image of your own and as the start initial frame. Remember, like the model has to take an initial frame. So in this case, we're going to pass the initial frame, which is a first-person view, person standing in the kitchen and looking down at a cutting board. And then we can actually choose from these diverse language instructions. And for example, we can choose language such as wash hands, and we see that the person actually went on to wash their hands. And a simulator being a simulator, it has to support repeated interactions. So in this case, after the first action, we can give the simulator a next action such as shut off water. So the simulator has to start from the previous observation of the last interaction to generate this new interaction such as shut off water. And in addition to supporting repeated interactions, a simulator should also support diverse actions such as pick up the ball, cut carrots, or dry hands, all from the same initial frame. And not just that we can generate these diverse manipulation instructions, but we can also try these navigation instructions starting from the same initial frame. We can ask a person to turn left. All of these videos are generated, like they don't exist on the internet. And we see that the person actually turned away from the kitchen and it seems like a dining room showed up. And when we ask the person to turn right, a wall shows up, right? So this is really to show like, diverse interactions like manipulation and navigation can all be casted into video generation. And not only we can do this for humans, but also we can do this for robots. We can ask robots to put sponge in a drawer and to, take the sponge out and so on and so forth. So, and I actually like this example the most. In this example, we have a napkin sitting on the table, and we can give the instruction of uncover some objects. And you see like a human hand actually uncovers the toothpaste. And furthermore, we can have a human hand interact with the toothpaste, like pick it up, or slide it to particular directions. And we can really kind of like, use language to structure the output space of this video generation model so that we can see a pen and have a person pinch the pen. You see the distance between the two fingers is really fitting the pen. And so the interaction is really diverse. You can really like, any natural language instruction that's like natural given this setting, you can really kind of try to simulate it. And there are many more examples. You can check it out on the Unison website, like uncover a plate and put an apple on the plate, or interact with a plate in various ways and have different objects and so on. And you can, even put a cup next to the bottle. So so this is some examples of what this real world simulator looks like. And so to recap, like the real takeaway from this first part of the talk is that when we have a unified representation of information, such as videos, and a unified task interface, such as video generation, we can really merge very diverse data, and as a result, get these generalizations of new interactions as simulators. Oh, okay. Okay, I'll just try to speak louder. Okay, so that's the first part of the talk. Okay, that's the first part of the talk, and let's look at how once we have this realistic real-world simulator, how are some concrete ways that we can use this simulator to actually train agents? So one decision-making algorithm that has been popularized so much is reinforcement learning, right? So reinforcement learning holds this promise that once we have a simulator, we can just put the policy inside of the simulator. The policy is going to try to execute some low-level actions, delta x, delta y, observe the outcome of the action, such as some reward and next observation, and it can just optimize itself without human intervention. So this works really well when we have, simulated evaluations. But once we try to develop a reinforcement learning algorithm training simulation in the real world, we actually run into this trouble known as sim-to-real transfer issue. And even in this very simple task, right? So the task is to rearrange the blocks on the table according to the language instruction. And even in this very simple manipulation task, we see that the simulator and the real world looks very different. So how does the simulated rollouts from Unison look like? So all of these rollouts on the right are generated by rolling out a policy repeatedly, right? Because every time we only predict one frame conditioned on this delta x, delta y. But then this is rolling out many steps of the policy. And we see that this rollout of the policy actually looks quite realistic in terms of what a real robot movement might look like. And to just show you some examples, we compare it to just directly running behavioral cloning using the same data set. And we see that because the data set is mixed, it has expert data and also non-expert data. As a result, we actually get somewhat of a low success accuracy. But then like once we do some RL on top of it, the success rate actually dramatically increases. So then coming back to this diagram, then you can see that on the right, this is actually a zero-shot transfer of the policy directly on the real robot to perform its task of pushing the red star towards the blue cube. And then the policy is only trained in simulator, trained only in Unison. So then like the intriguing thought is that maybe the solution to the sim to real transfer is indeed to have a learned simulator that is pretty much real. So that we talked about some very simple tasks, right? So if you look at this task, right, place your hand above the blue cube or move red star towards the blue cube. It's like very simple, relatively short horizon. We just need to figure out what the low-level controls are. But once we want to do some long horizon tasks, right? So for example, we want the robots to put all of the fruits into the top drawer. So this is a long horizon task that is very difficult to directly train RL policies to perform. So what we can do is that, remember, Unison also takes language as input. So what if we just try to generate a video of putting the fruits into the top drawer conditioned on the first frame and this language instruction. So this video is generated by Unison. You see that the model actually, the robot opens the first drawer and it puts the fruits in the drawer. But this video doesn't mean that the robot has executed anything, right? So we only have a video. To actually turn this video into real robot executions, we train a separate inverse dynamics model. So an inverse dynamics essentially just takes two images and takes the delta of that two images and try to predict the action that caused the change between the two frames. But remember, like the difference between the two frames is relatively low rank, and it's really just capturing the movement of the robot arm. So this is actually a much simpler task. And on the right, you can see the real robot execution when we use the actions, low-level controls recovered from the generated video to control the robots to perform this long horizon task of putting the fruits in the drawer. So this feels like magic, right? We can generate something and then just directly execute it on the real world, in the real world. And so I guess one thing I wanted to point out is that to generate this video is actually non-trivial because you see that this video is also pretty long horizon. There are multiple steps involved, right? So how can we make sure that we generate the right, sub-steps every single time? So to go into a bit of a detail of how we actually generated that long horizon video, we started from this initial image and language instruction. So we first asked the language model to break down the task, right? So what should be the first step if we want to put the fruits in the top drawer? And language model tells us, okay, maybe open the top drawer, but it's a stochastic model, so there might be multiple samples. Another action says place banana in top drawer, but the top drawer is not open, so the second action is wrong. But then the reason that the second action is wrong is because the top drawer is not open. So there's some kind of reasoning that has to happen in the visual space. So directly using language to know that place banana in the top drawer, the second action is not good, is not trivial. So instead what we do is that we use Unison to simulate the visual execution of this language instruction. And we see that the action 1, which is to open top drawer, actually correctly simulates this interaction, whereas the other action, put the banana in the top drawer, it just doesn't complete the task, right? Because the top drawer is not open. And furthermore, we kind of need, we want to automate all of this, right? So we wanted another visual language model to be able to tell us which execution or which simulation actually is correct or making progress in the task. So this is when we fine-tune a visual language model as a reward model to help us to distinguish which execution to actually proceed. And now remember, we're only one step towards making this task, right? So we condition on the last generated frame of opening the top drawer, and then we ask the visual language model again, what should I do now? What should be the next step if the goal is to put all of the fruits in the top drawer? So then we can sample from the visual language model, use Unison to visualize the execution, and use reward model to select the good branch. And until that, we have the full branch that completes the task. We can use this inverse dynamics model that we talked about to translate this video into robot controls and execute the robot controls on the real robot. So maybe here you can recall that we talked about this AlphaGo setting where we have a simulator that's very realistic and we can do these broad searches and planning all in simulation, in imagination, right? So to try out different actions to see what happens. And we can do the same now with robotics tasks when we have this realistic simulator. So I want to dive into a bit of a detail as to why we want to do planning with Unison, right? What are some other alternatives? So if we think about robotics tasks, often the times the goal is to derive some low-level control actions from A1 to A7, conditioned on some high-level inputs such as the task, make a line, and some initial image frame. So of course we can try to just learn a policy, right? Using behavioral cloning to do this in one step. But then because this task is very difficult, mapping from something very high level to something very low level. So as a result, we actually need a lot of data. And for this particular task, we can see that behavioral cloning or imitation learning works quite poorly and rarely completes the task. So what are some alternatives, right? So this is also our work, Unify, what Unify does is it predicts these intermediate frames according to the language instruction, which is make a line. And now conditioned on these intermediate frames, we can use the inverse dynamics model to recover the low-level actions. And we see that the completion rate maybe increased a little bit, but it's still quite low. And so what this tree search algorithm that I just showed you doing is that it's essentially introduced another layer of abstraction, which is to use language to specify what the high-level tasks are. And we see that the completion rate further increases. So to give you more intuition as to why this hierarchy makes sense, there are a few benefits to having this hierarchy. The first benefit is that we actually have internet-scale supervision for the first two levels of mapping. For example, going from language plus image to language, we actually have internet-scale trained vision language models. And from language to video, we also have internet scale text video data. So we pretty much get these top two levels of mapping from diverse data sets. And the very bottom part, right, to just like recover the action condition on 2 frames is made much easier. So we broke down this complex task into simpler components while using internet scale data sets to assist with the top levels. And another benefit is that we can actually use language to search quite broadly into the future, right? Because these low-level control actions might be executing at 100 hertz. And it's really difficult to tell whether, moving like this tiny amount is, having any effect of the long horizon goal of reaching that door, for example. But language actually allows us to search and plan much more efficiently into the future. And lastly, we can do actually search and planning and verification during each of these levels of mapping. And some people often ask me, okay, how does Unisim work when we have these long horizon tasks? So I wanted to show you some example when we just repeatedly try to have different interactions. For example, like the first one is to put the can on the top. The second step is to close the bottom drawer. Like each of the new simulation is conditioned on the last frame of the previous simulation. And then, we're just doing this repeated rollouts, and you see that the model actually doesn't get worse as time goes on. It just continues to behave the way we expect it to behave. We're already at step 6, and maybe step 7, put the key in the top drawer, and step 8 to close the top drawer. And eventually I just got tired, so I stopped generating. But the point is that it can really generate long horizon videos just by conditioning on the previous generation. And in addition to long horizon planning, we can also actually conduct this multi-task planning because, as Sergey has mentioned, right, different robots have different state and action spaces. But now essentially we're turning planning into a unified interface, unified task, which is just to condition on language and some initial frame to try to generate the video. And we can do this for any robots because the pixel space is actually the unit shared observation and action space across different embodiments of different robots. And there's one other usage of Unisim, which is we can generate training data for VLMs because one of the bottleneck for VLMs is perhaps like the amount of labels that we have for this paired image and text. So in this case, we can actually generate videos for cutting pepper using Unisim. But then we can take these, because we condition on cutting pepper to generate this video, and that if the video generation model is good, then the videos that we get is in fact a video of cutting pepper. So we can use that paired video text pair to train a video captioning model. And the observation is that we can actually improve the transfer performance of these video captioning models when we train it on simulated data from Unisim. Okay, so that's the second part of today's talk, which is the takeaway is really once we've learned this real-world simulator, we can actually apply a diverse set of decision-making algorithms such as reinforcement learning and planning in the simulator to optimize policies. And okay, next I want to talk about some challenges and next steps in terms of how to address them. So one challenge, this video is actually from Sora, which actually was kind of developed 6 months after Unisim. It's something that's hard to argue because it's just so much more popular. But yeah, I just wanted to say like we kind of worked on this a bit earlier. And so in this example, you saw like the chair was just jumping around without people touching it, right? So this is really like violation of real world physics. And in fact, Sora has that, Unisim has that as well. If you look closely, you see that the carrot actually grows into the knife as opposed to the person cutting the knife, right? So you might be fooled by these videos, but it's really not okay to use these videos to control robots when they hallucinate a lot. So we so far don't have really good solutions to hallucination. Scaling helps a bit, more data helps a bit, but I just wanted to like give a more optimistic point of view, which is at some point, hallucination could also, depending on the definition of hallucination, but we also wanted a bit of an imagination in situations where we have unrealistic language instructions, right? So in this case, we have a tabletop robot with a robot arm, but the language instruction says wash hands. Right? So this is clearly unrealistic because there is no hands in this image. And I was really surprised to see what happened in Unisim, which is like the video that got generated was just that the view shifted from this tabletop into a kitchen and a person's hand shows up, right? So this is really showing something that the model is trying really hard to generalize to this novel language input by, using the training data to do what's most probable, what's most likely, which is to just turn away from this view. So I think in some sense hallucination, yes, it's bad, but in some other cases, there are these interesting observations. And the next question is, okay, we generate a video, but how can we know if it's good or not, right? So we can have humans look at it, but it's not very efficient. So in some sense, I actually think robotics or embodiment is actually a nice way to automatically verify the quality of generated videos. What do I mean by that is that imagine we, had this diagram from before where we had these search trajectories or generated videos, and now we turn these videos into actions and execute these actions in the real world. Then the question is, should good world models lead to successful robot executions? And then the answer is yes, right? So essentially we're trying to match these two parallel universes. One is the real world and one is the imagined, this world model that the agent uses to imagine into the future. And eventually if the world model is perfect, then the actions extracted from the world model should also execute in the real world and results in the same video as the one that the robot has imagined. And when there's something goes wrong, right? Like for example, the real world video that the robot gets actually doesn't match what the robot has imagined. This is like a realization for the agent to further optimize its video generation model or its policy based on this real world feedback, because clearly we run the robot and we see the robot crash or something. So this is additional thoughts on in terms of how we can evaluate video generations using robots and how to incorporate feedback from the real world, in addition to just human feedback. And thank you. I wanted to thank all of my collaborators from Google, Berkeley, and MIT. And I guess it's time for questions.
Any questions on the phone? Okay, yeah, I got one question. So it's a general thought on how to apply the foundation models into the robotics. So one paradigm is to apply what we have in VLMs or LMs and then fine-tune into the different kind of the robotic pathway. And another one is to utilize all the data pyramid of what we have in the robotics and create the robotic foundation model itself. So what kind of paradigm do you prefer or you prefer?
Yeah, I think the answer to that question really depends on the task itself and the data available. If you talk to some classic roboticists, they don't even think learning is needed, right? So, but then all they can do is that particular task, maybe just a screwdriver screwing this one screw, and once the shape of the screw changes, they can't do anything about it. So, but then what internet scale knowledge brings you is this generalization, right? Like the bartender example, which is something that's really only the internet scale data sets have these kind of knowledge. And if our goal eventually is complete automation without expert knowledge, going from language to robot actions, then we really need these visual understanding and linguistic understanding of the tasks. So this is when these internet scale data sets become quite relevant. If you're saying we already broke down the task, we already figured out the details, these classical robotics, then the question is how do they generalize? So I think this is where internet data helps.
I'm really interested in more about the foundation. I understand correctly what you mentioned to do closed loop evaluation. But imagine we are doing very large scale video generation simulation. Is that expensive? Do we have any way to foundation?
Yeah, so there are definitely these proxy metrics that you can use from generative modeling, such as FVD, which is the FID version for videos. There are also these clip scores. You can look at how the generative video, whether they're following instructions. My experience has been that these metrics are reliable to a certain degree, but sometimes it's also not because it's distributional information. So it's I could still get hallucinations and so on. So I'm just proposing, I'm not saying all videos should be verified using robots, because you might have videos that are just humans, or you don't have robots that you can't really turn that video into real world executions. But I'm just offering robots as kind of a convenient way to verify video generations when we do have generative videos of robots to test whether this actual generation corresponds to good robot execution.
I'm from remote, so we drive a car on the road.
Yeah, I guess another evaluation is like you can roll out your policy in a simulator and see how it performs. That's yeah.
What are some of your insights on the breakdown?
Yeah, so this is actually going back to like how we process the data, and it actually depends on like the task consumption. Like we have a fixed number of frames during training. We fix that number of frames, but then depending on the frame rate at which we sample, different data sets have different frame rates. But essentially what we need to do is kind of align the duration of the video and the language instruction, like roughly. And that actually gives us a lot of flexibility of incorporating data sets recorded at different frame rates and so on, as long as we can like actually have like a fixed window to capture what happened in the language instruction.
You observe any synergies between training on different tasks and domains, or the network basically encodes like different tasks?
The question is, do I observe whether the network encodes different tasks into subspaces? So I think the answer is yes. And to actually be very honest, like I think the current video generation model conditioned on the first frame doesn't work super well out of domain. Like when you give it like some really absurd image taken from really absurd angle, for example, and I try to interact with images and it doesn't really work well. And usually if I get an image from the internet distribution, it seems like the interaction works well. So which means that, you know, like the model is doing kind of something about these visual observations, and once we actually go beyond the distribution of these visual observations, we're actually in some trouble. And I think how to like mitigate or improve out of domain, by domain I mean image observation, generalization, I think is a very interesting direction to be worked on for these image conditioned video generation models.
Let me ask you in a different way. So you have this like log pushing task and like the Google robot opening drawer. If you train on both of the tasks, you get better performance, or is it like?
Yeah, we have some ablations in the paper that yes, we do have better performance metrics according to the simulated metrics. We actually didn't run real robot experiments to verify that because there are many things involved, inverse dynamics and so on. But according to the simulated metrics, including more data, does improve generalization on the test.
Yeah, please go ahead.
Thanks for talking. In regards to the hallucination, I'm wondering if you observe longer time scales, more complex hallucination. Because I don't get the direction of the camera, like when you turn into the dining room, you're now in a complete generative space that's completely different from your initial state. So if do those long range tasks do they affect the output, and you can maybe an issue going forward?
Yeah, so I guess the long horizon that I showed you did have a fixed camera angle and it's only doing manipulation. And my hypothesis, we haven't really run that experiments, but I guess one challenge for the model is to have long-term memory. So for the example that you gave, if the model didn't really encode, like for example, we only use 4 frames from the past to condition on to generate the new video, so which means that the model isn't able to turn to the dining room and turn back to still see a kitchen if the kitchen wasn't in its memory. So in that case, hallucination definitely happens. So these are more egocentric issues. There's also the issue if your language instruction is too abstract, something like, yeah, like if you don't break down the task into the distribution of language that was in the training data, if it's too abstract, then it's also hard for the model to generalize. So essentially, it's like the distribution of training data, whether like the language is actually in distribution. Yeah, I mean that's the whole tree search, which is like we can at inference time utilize language models and to kind of break down the task so that it's more in distribution. And I think like the text to video data set will probably get bigger and people will have very diverse labels. Like it will be something very specific, you know, something moves by 2 centimeters, or something very abstract like a person cooking. So, and we can, because the model is so flexible in that it can condition on very diverse actions or very diverse language to generate the frames that corresponds to those executions, we can actually merge all of those data sets of different granularities. Yeah.
video generation as the ground truth, like as the of like your language, right? So if the language says something stupid, then the video says something stupid. So something similar to enforce consistency in videos, like let's say the road, right? On the road, and the left. I do have a ground truth simulator like we're in the world. We can use something that can keep the videos. I know that.
Yes, I think so. And in fact, we already have something like that. So, we're generating videos and then we're using another vision language model as like a critic, like a reward model to tell which video generation was good, right? And so my understanding is that these text-to-video models and these vision language models are trained on perhaps slightly different data distributions. And as a result, they have slightly different knowledge about the world. And by just having these two models communicating with each other and correct each other and providing additional data and so on, we can actually get a bit of additive effect of performance. So in fact, yes, we do already do that. Yeah.
Sure, go ahead. We might have one last question.
So I personally feel like engagement and information has similar so I'm gaming data is by that field. So have you ever think about inject that field gaming data?
Yeah, not for Unison. We do have a follow-up work called Video as the New Language for Real-World Decision Making. In that case, we actually included game data. And my sense is that because there is a lot of game data, and oftentimes they don't have very good language annotations. Some of them are just like players talking to each other. It's not really capturing like what happened in the video itself. So we didn't like observe a drastic gain by including video data sets. But I think the fact that if we can just scale up the model infinitely and we can absorb more and more data, because the video data does also have this notion of keystrokes and response to keystrokes, which is pretty much like what robotics are. So controls and next alterations. So yes, I think ultimately including video data that would be helpful.
Yeah.
Thank you.
Yeah, let's Sarah again. We might have a short coffee break, which is 10 minutes, and we will resume like 10:40, right? Yeah, 10:40. And be careful with the exit. It's turns out that it's a one out and a one. Thank you very much.
Yeah, this hopefully is not working. I like the sound.
Yeah, sometimes it works, sometimes not. We might have a small game for people.
Oh, okay. Oh, thank you. Thank you.
Yeah.
Because no one wants to be in that situation long enough not to stall it. Everyone in America and I kind of move on it and make some match and somehow we still to end short and oh no sorry what do you do that
Oh, okay. Oh, okay.
Like officially 你是
Extremely
Oh.
diverse.
Okay, good to know.
I think that's like the whole reason why like I really want to highlight well the social and right? So because like that's like really starting like learning having it's kind of complex and like but then like the new observation that we have is
Hi, Alex. How's it going? Yeah. Oh, have you logged the tool? Sorry? Have you logged the tool? Have you logged in the tool? Yes, I have. Oh, yeah.
It really depends on in the case that I do have
Like directly in? Yeah. So will it go through here or does it? So the HTML goes through. Yeah. And then it's going to go through. Okay,
yeah, I guess that question about like
you can. No, you can.
and really what matters is those pixels. That you're not really pixel space like you don't have so I think also learning
right now it's look back on the road. To say that believe that that's like unit cards is sometimes yeah, but I
can't it's just like you have someone like you're listening to your words
yeah, and they made it so public, you know, they're also in Seattle, but you know, like they need the rain for everybody. Excited. Don't really in California. Happy. That'll be awesome. Good.
It's so formal, but that's thing.
We're going to Austin and Miami.
Oh, okay. When is that happening?
Right. Whatever.
I want to tell to Sherry. Sorry. I plan to.
You should go.
I see. So you California?
So we just buy a lot of the vehicles. Yeah. My old company is very close to it.
Oh, okay. We also have the Ferraris and
Yeah. The famous and yeah, because that completely changes the center. We also have limited.
I know, me too. Yeah, it was great. I think we know each other for like 2 years. And thanks for your recommendation. I will start the in October. I just received the official letter like 4 days ahead. Congratulations. Thank you.
It's good to finally meet this.
And also congratulations on your praise.
Thank you.
It's rock star and all the
We've got work to do. We can see that.
yeah, sure, definitely. You must be very busy now.
I'm socially aware. I think that's a little of really smart.
Okay.
Nice meeting from
I noticed you got a new hire from Professor Yang.
Yes, you know, yes.
Yeah, I know him, but he doesn't know me. I know him since I was a PhD.
You worked in reconstruction, right?
I worked in object detection during my PhD class.
It's going to be recorded.
So he is still in basically.
That's right. Yeah, we just opened.
Oh yeah. Yes, I'll be presenting abstract in tomorrow.
Yes, at our
yes. Okay, I will also during
yes.
On the general of the driving on Thursday, I suppose, and the other is by the perception. Right, and the
That would be done. That's very silly.
Okay, guys, we might start the talk in just 1 minute. Okay, sorry about that. We might start. Our next speaker is Alex Kundal from Wave, the CEO and the co-founder of Wave. And we all know Alex as Wave company, right? This is just a rock star driving and his talk is going to body AI. So let's welcome Alex for his talk.
Thank you, Hong Yang, and hey everyone. I'm looking forward to this. I hope it's the start of a great conversation this week. But today, I've got a number of things to talk through. Excitingly, today we've got some new research that we're sharing from Wave that I hope to give many of you a sneak preview of, as well as a data set. And this is actually a photo from that data set. We often talk about building embodied AI, and this is one of the driving scenes one of our autonomous vehicles went through in central London. And I think it really epitomizes the true challenge of this problem. If you look at the multi-agent complexity, the dynamic modeling scene, all the different both rules and culture that you have to be able to truly understand to be able to operate through a scene like this. And I want to start out by zooming out before zooming in. So today's talk, I'm going to talk through deep dive three interesting topics when it comes to embodied AI. But before we do that, I'd like to just zoom out and share a perspective about what it means to build embodied AI. Now, of course, across science fiction, we've seen this represented by many different characters, from Marvin the Martian to C-3PO. I'm not sure what your favorite one is. But for me, embodied AI, I think, will be the prevailing way that we interact with intelligent systems in the future. We live in the physical world, and this is, in many ways, the next evolution of tooling. From the wheel to calculators to computers, intelligent machines are going to allow us to free up more of our time for us to be able to trust and delegate tasks to these systems and ultimately improve the safety and sustainability of the world we live in. That's the vision. That's the opportunity with embodied AI. Now, we can ask the question what it will take to build such a system. But I also think it's interesting to reflect on how AI has developed over the last couple of decades. The interesting thing I've observed is that different topics have motivated different breakthroughs. When I was doing my PhD, I think it was fair to say that computer vision problems were really at the forefront with breakthroughs from batch normalization to residual connections. Like, everything was coming out of ImageNet and the recognition challenge. Although it's fair to say more recently, I think language has taken that crown, and we've seen language unlock new levels of scale, of interesting levels of feedback. And it's, of course, languages are more compressed with a higher signal-to-noise ratio information content than images. But I'm a big believer in problem-driven research. And what I want to argue is that I think the forefront of AI and where the next breakthroughs are going to come from is from embodied AI. Why is that? Well, embodied AI unlocks that next level of data. Of course, video data is orders of magnitude more, petabytes or exabytes, compared to text data. It's an open problem, open domain problem. We can't control the scenarios we drive in, the weather we experience. And so it really motivates a level of reasoning and capabilities that go beyond a constrained sandbox, but something that we can truly trust to exist in the open world. And safety is not a nice to have, it's a fundamental property we need to succeed. And so safety is paramount to solve. We need to solve the AI safety problem to make this a reality. And so how this motivates us from this problem-driven research, I think this will provide the environment for some of the most exciting breakthroughs in AI to come. So watch this space. I think this evolution will continue to grow. And of course, we're going to talk a bit today about multimodality, how it combines models across these spaces, but ultimately the problem, the data set, and the simulation, the measurement signal, is what has been driving AI breakthroughs over the last few decades. And I think robotics and autonomous driving will be the next frontier. Just to briefly introduce Wave, a lot of people ask me, are we truly building an end-to-end neural net? And the answer is yes, we are. We have our stack that today runs on vehicles, different types of vehicles around the world. It's truly one end-to-end neural network. Sensor input comes in and a motion plan comes out. It's fully optimized through data and offers many advantages over the classical stack of robotics that we've seen in the past. But I think this is starting to be well understood. The interesting promises that an end-to-end learning system provides the world is that, well, firstly, maybe this is underappreciated, but it is computationally homogeneous. What this means is that many different neural network blocks can be put together, and this makes it easy to port to different software stacks. It's not a bunch of multi-threaded microservices that need to have complex communications between them, but it is a homogeneous forward pass of a neural network. This makes it really accessible. It generalizes through data. This makes it scalable because we can expand to different geographies, vehicles, or sensors and have a representation that understands these. It's economic because it can avoid the use of an HD map, because we build the intelligence on board the vehicle that lets it understand the world for itself and make its own decisions. And of course, when it comes to safety and performance, we've seen this story play out in many other spaces. And with robotics, the same will be true, that a learning-based system will be able to outperform anything that we can hand engineer. So with that brief introduction, I want to spend the bulk of the talk deep diving three topics that are really exciting me and our team at Wave right now: simulation, models are enabling the future of autonomous driving, and with scale, how we bring all this together to build a day. Sound good? All right, so let's start off with simulation. So I want to talk about end-to-end simulation for end-to-end autonomous driving. I hope I don't need to provide a motivation for simulation because it's so clearly important for autonomous driving, for efficiently iterating, understanding performance, or covering the long tail of edge cases. It is a really clear tool. It's interesting how it's a bit of an arms race. You know, if you solve simulation, I believe you solve autonomous driving or vice versa. And so there's an arms race between these systems to be able to co-develop the driving policy and a simulator. But the interesting thing we are seeing is that the same arguments that are true in driving policies are also becoming true in simulation. An end-to-end data-driven stack is the way to address this. So let's start off with by examining what is out there today for autonomous driving simulation. There are many example systems today, some fantastic systems. I've called out a handful, but there are so many more, from our own Ghost Gym to Waymo Simulator, the open source system Kala, or Wabi World, or et cetera, many others. Let's first consider the desired outcomes that we want from simulation. So with simulation, I think the first thing we really want to see is that it closes the domain gap, but importantly, not just for perception, but also behavior. Closing the domain gap and measurably closing the domain gap allows us to trust such a system. Secondly, we need to be able to simulate dynamic and deformable and complex scenes, because this is where the edge cases lie. It's not just a rigid vehicle, but it's when the car door opens. It's when people step out onto the road. These kind of things is what we need to be able to handle. It needs to simulate the full environment. It's not just about isolating a perception or a mapping stack, but we need to be able to simulate the full world interaction of our embodied platform. Of course, we need to be data-driven and scale. We've learned this many times over. And finally, we need to be able to control it and be able to take adversarial steps to be able to find edge cases and these kind of things. I think these are the main desired outcomes when it comes to simulation. Now, I'm really excited because today, I think we're going to see a first glimpse of a system that can address all 5 of them. So let's see if we live up to the promise. Let's explore this more deeply. So first, some first background is in, of course, novel view synthesis or neural reconstruction. A first building block of such a system is that it's well known today that we can take camera sequences and produce really compelling reconstruction. You can see this play out here in the bottom right. So that's the first building block. Now, if we take such a system, the question is we need to be able to fully simulate the entire environment. And so taking such a reconstruction, it's not just enough to be able to, fly a camera through a reconstruction. We need to be able to simulate the robot, the vehicle dynamics, the full interaction of how this interacts from a and it's not just the dynamics, but also the latency in the system. There's latency in inference. There's latency in sensor message passing and all of these kind of things. And so Ghost Gym is what we call internally at Wave the simulator that gives us this entire package, the full latency and environmental simulation coupled with unparalleled realism of the world we interact with. So that's the foundation. This is something we talked a lot about last year, and I want to show how we can build on this to unlock all of those objectives I will open that again. Just give me 2 seconds. Suspense. Success. All right. Flaky conference internet. Hey everyone online. Sorry about that. Hopefully we should be back on. All right. Oh, that's a terrible camera angle as well. Can people online hear me? I'm going to assume yes. So let's jump back to Prism. So you can see the dynamic agents, right? This is complexity that's super exciting to us. Let me show you another one. So here we are providing a sinusoid input just to really show the novel view generation. And look at the lady with the umbrella. You know, this is incredibly complex. You can see her hand wave, you can see legs move. The level of reconstruction here is incredible. This is from one sequence of us just driving through the scene. We've now been able to entirely resimulate this environment to the point where we can drive back through it. If you look at the reflections, even the traffic light change, if you watch again, look at it go from red to green. It's another example of, simulation is not just putting rigid bodies through the world, but you've got to be able to deal with changing brake lights, traffic lights, other deformable and dynamic objects, making sure that there's a degree of realism when it comes to shadows and everything else. And that's what we're really excited to see with Prism. Here's another one where we drive through quite a complex and cluttered construction scene. Here you can see we can, pause time and look around the world, and you can see the quality of the reconstruction that can come out. Here's another one where we pause in space and we control the time dimension. And you can see here, this is really providing a robust path for full closed loop simulation. You can see on the on all of these examples, we're able the traffic light moving in the top left to pedestrians and vehicles in a rainy scene in the bottom right. Here we can really provide a closed loop driving simulation experience with the full complexity of, for example, urban scenes that we drive in. Even look at the lighting conditions. So on the right, you can see that lens flare that's coming from the reflection on the building on the right, or on the left, the reflections that we see in water. These are things that would be extremely hard to get through a rendering engine, and we can do them in real time through Prism. So that's a bit of background about the rendering engine within Prism, and of course that's one important part of it. I've got to stress that the full dynamic interaction, the full latency modeling and robot simulation is what really makes this powerful. So not just Prism, the second thing we're excited to release today is Wave Scenes 101. This is a new data set that we're excited to release to the community for a number of reasons. Firstly, we found when developing Prism, there wasn't a very strong way to benchmark these systems. A lot of the data out there was in very scenes with low complexity that lacked dynamic things from traffic lights to pedestrians to that photo I showed you at the very start. They lacked geographic diversity. And interestingly, they lacked a multi-camera view where there were cameras at significant baselines. And so we've been able to construct a data set here and even propose a benchmark where we have a held out camera at a novel viewpoint that's over a meter baseline from the other cameras. And so this is Wave Scenes 101. Now, here's some example videos from it. You can see here, the diversity in visual scenes from night to rain to day. And more interestingly, here's that scene at the top that I was talking about before. Now, I think this is going to set a true bench. Well, eventually people will overfit to the scene, but it's going to take some time because this is a really complex scene to dynamically render. If you look at how many moving pedestrians there are on the scene, I cannot wait to see progress in this. And we hope that this data set provides a new challenge for complex visual reconstruction. So that's the reconstruction engine and the data set. If you remember, the last thing I was talking about was being able to control the simulation, to be able to take adversarial steps, to be able to try things that perhaps are not present in the original experience. And that's really where we think a simulation can help close the gap and help boost the signal that we need from edge cases to be able to produce a safe and reliable driving experience. So let's talk about that. I want to start by recapping Gaia, a model that we released and talked about at CVPR this time last year. So Gaia is a generative world model that, to briefly talk about the architecture, it allows us to encode vision, language, and action into tokens to pass them into an autoregressive world model that allows us to, for example, decode and understand, decode and generate sequences of driving. And we can use it to we can condition it on various inputs, but we can use it to build a world model that can really understand scenes like the complexity that we've been looking at. And if you want to learn more about it, you should speak to Anthony, who's in the room, who led a lot of this work. But of course, Gaia is part of a full ecosystem of world modeling. This is a great figure from a survey linked at the bottom on this space. We started working on world modeling. We put a blog out in 2018 that showed how to build a model-based reinforcement learning system to our system Mile here, or Gaia, or there's many others now, right? This is a really rich and important area. If you have a world model, if you have a system that really understands the dynamics of the scene, it will be a representation that goes a long way to be able to drive robustly. And so just to, again, introduce Gaia, it's a system that can generate sequences that we can control. Now, all of these videos are synthetically generated with the world model from different weathers to different times of day. And it's all generated from scratch with this with the system. Now, how can we utilize this to control the simulations that we're building? Well, interestingly, in Gaia, we can control and inject edge cases. Here, we ask the ego vehicle, we condition it on forcing it to the wrong side of the road. And then you can see how the scenario plays out. You can see some realistic and interesting behavior result. And we can, of course, synthetically create edge cases like this. A sneak preview of what the latest system is able to do. Well, we can now even control dynamic agents within it, and even add on to simulation systems such as the Prism system I just showed, and add new agents. Now, this is fully generative, so everything from the shadow to the lighting to everything like that is coherent with the entire scene. And here you can see we've artificially placed the vehicle using Gaia in a driving scene. Here's some more examples. We've asked it to place a bus or other vehicles. And this is an interesting one where all of the dynamic agents in this video are rendered through Gaia. And you can see there's a truck in front of us. There's cars on our right and the other lane. Now, the interesting thing is these are 3 camera views. Now, if you look carefully, the car that drives, the sedan that drives on our right, it's coherent between the camera views. It comes through the middle one and passes to the right, and it's the same car. It's generated from a unified representation across the multi-sensor, multi-view stack. And that's really important. So Gaia lets us control and modify the scenarios that we drive in beyond what we've experienced before. I'm going to talk more about Lingo later, but in short, it's a system that can allow us to ground our driving experience in language. But just to pull this forward, you can see here that we've been able to, on the left, introduce a car in front of us and ask Lingo what it says about the scene. Here, it wants to increase speed to match the speed limit. And at the bottom, it wants to slow down to match the vehicle's speed. And on the right, you can see that it again, adjusts to counterfactuals based on us controlling the environment. And the final example is in Prism. Here you can see we can add and remove dynamic agents from the scene quite effortlessly. So the point being, I hope now that those promises or the requirements of simulation I laid out at the start, from complex dynamic deformable scenes to being controllable to simulating the full environment and embodied system, this is now a system, GhostGym, that can holistically address them all. And we believe provide a data-driven path to be able to scaling up simulation for autonomous driving. Great. Let's move on to the second topic on multimodality. So I want to talk about vision language action models here, grounding driving and language, and some of the work that we've been doing in this space. Now, why would you want to bring in language into embodied systems? Well, language allows you to unlock a new, greater source of training data. Text can be a really high signal to noise ratio of information. It's a lower bytes to intelligence form of data. It can provide general purpose reasoning from the wealth of human knowledge, and more interestingly, enable features that might provide a greater degree of trust and safety through enabling language interaction with robotics. There's a number of reasons why it's interesting to us. And if you want to read more, there's an excellent survey here, actually by some of the people in the room that you might want to read more about language meets driving. So this time last year, we were talking about Lingo 1. Lingo 1 was our first vision language action model that was enabled to do VQA around driving scenes. It could watch driving scenes and interact through language. Essentially, we encoded driving experience and passed this through a language model that we fine-tuned through both image input plus text input, and we were able to enable a conversation as a result about the driving scene. That was the core architecture. Quite simple conceptually, but a amazing challenge to train and assemble the right data for this. But the result was a system that could comment and explain driving, like you see on the left here, where it's describing that it's slowing down for a jaywalker and navigating through the scene like this. Or on the right, you might not be able to read this, but where it can actually answer questions. And we ask it, what are you seeing? What are you looking at? And it describes, I'm seeing a glass building. There's a risk of a van on the left, and there's a cyclist on my right. And it's able to actually give grounded answers of what's in the scene. Quite exciting results. We could even take it one step further, where it could do referential segmentation. This really reduces any tendency of hallucination because it asks it to ground its answers in the visual scene. So you can see here, our system is able to point to what it's looking at, the road in front. You can see it's labeled, or the car in the background. And we can even ask it, what do broken road lines mean? You can see it can highlight them on the screen. And so this is referential segmentation. What I want to talk about today is Lingo 2, which goes a step further. It actually brings this model for the very first time, we believe, in the world. It brings a vision language action model in closed loop driving a car. This is super cool because it actually means that this is not just commenting open loop, but it's actually the same representation that's driving the car and understanding the world. And you can read more about it in our blog. But this, so essentially the architecture is it's end-to-end trained, but we pass in vision data and feed in those tokens as well as text and other prompts like navigation into a VLA model that we can then use to drive the car or converse with in conversation. So that's Lingo 2's architecture. Let's look at some of the results. So if you look at this, this is this is actually driving the scene. So this is Lingo 2 driving in closed loop while also describing the scene. And if you look at that, you can see it's talking about, why and what it's doing. I can show you another clip here. This is quite interesting. You can see it's the road's clear. Now it starts to talk about, oh, there's a bus, and it's actually wanting to overtake the bus. This is quite a hard thing to recognize, but it's recognizing the bus is at a stop. Then it's going to come back in the left lane and then slow down for the traffic light. And so this kind of level of reasoning, I mean, this is a true generalization test, right? This is never present in the training data. We're driving in London here, and you can see how the system is grounded in reasoning about the world. Well, here's another example where you can see it's talking about, well, what's it going to say? The zebra crossing is clear, how it's driving through the space in central London. So that's essentially what Lingo allows. Now we can interrogate and learn more about it in Ghost Gym, which I just introduced. You can see here that we can prompt and ask it to follow the route, or we can slow down for the turn. And you can see that we can actually start to control the behavior of the vehicle through language. We can even ask it to stop behind the bus or overtake the bus. And you can see its behavior will actually change conditioned on text prompting. What does this enable? Well, we can start to talk to our car, have a chauffeur experience. We can ask it to drive in a certain way with a certain style, and it can be prompted by this. Of course, it will do what it believes is safe, but there's a large operational envelope of what you can do within what is safe driving. And we can start to control that quite naturally through language, really make this accessible. You don't need a research degree in robotics to understand this car. We can just talk to it in natural language. I think that's super exciting. And really, what we believe is that by using multimodal training, we can provide greater alignment and greater general purpose knowledge into our driving model so that it can be safer and a more performant driving experience. Let me, so that's on multimodality. Let me just move on to the third and last section on engineering to product. So we've talked about a simulator and why this is important for self-driving. We talked about multimodality. The thing that I'm really excited about at Wave is the opportunity we have to now take this work and really deploy it, to build the ChatGPT of embodied AI, to get the system out there at scale that can enable people to be delighted by an embodied AI experience. So what's it going to take? And I say this because often my experience in, when I've spent time in the research community is that often people dismiss engineering. Reviewers, of course, don't value research, don't value engineering as much as they do novel ideas when it comes to accepting papers. But I think engineering is, well, one, scale is super important when it comes to enabling AI, but two, it's often underrated, and it's the key thing that turns a demo into something that's truly robust. And for anyone who's a technologist, I think that's something to get really excited about. And so I hope that this section can talk about some of the problems and opportunities when it comes to building a foundation model for embodied AI. So let me start off with, again, a bit of the motivation of what we want to create here. Well, at Wave, we want to build a generalizable embodied AI platform, something that can enable not just driving, but domestic robotics, manufacturing robotics, essentially enable us to trust and interact with machines in the physical world. How are we going to do that? Well, we want to learn from the most diverse data across the industry. We want to be agnostic to the specific robot so that we can learn and deploy from various different data sources. We don't need a homogeneous fleet, but we can really learn from diverse vehicles. We want to be truly excellent when it comes to inference efficiency, so we can pack as much intelligence as we can into the compute. And finally, have provably safe and I think the more important word here is predictable behavior. We want to be really reliable with what we can and can't do, so we can set bounds and expectations of what the system can be used for. So that's the motivation. That's the North Star. How are we going about doing this? Well, at Wave, we're building a foundation model for embodied AI. So this word's thrown around a lot. The definition we use for foundation model is a model that's trained on a diverse set of experience that can be general purpose, used for a number of tasks. And for us, that's tasks across the embodied AI space. Now, there are many examples of this across language and vision. What about language, vision, action? What about embodied systems? Well, there are some unique challenges for embodied AI, right? Data is one. We can't just scrape the web. You've got to have interaction with physical systems. I think this is where self-driving has an advantage, because there are hundreds of millions of vehicles, if not billions, around the world driving today that can collect data, that are collecting data already today. And so this is, there's already a commercial setting for that. Training compute. As with language, we can't just put all the data locally on a compute node. You need to be able to stream petabytes of video to GPUs. And of course, actually embodying it in the world, from safety to the actual integration and interface, these things are hard. Now, there are a number of examples also in embodied foundation models, but nothing that's hit a sort of GPT-4 level of scale yet. And that's what we want to unlock at Wave. So the first one is with data. Let's talk about the data that we train on. Of course, there's the driving experience we have from our fleet, and we've seen a lot of that today. But there's a whole pyramid of this. And I think the base level of data starts with internet scale videos that give you that general purpose understanding of the world. There's, of course, embodied applications from many different types of robots. There's large-scale driving data that we work with our partners on, from Asda and Ocado to big fleets in the UK. And of course, the high-quality driving data that we collect ourselves. But together with our partners, Microsoft and NVIDIA, we are training these systems now at a level that I think the world hasn't seen before, and the results are incredible. Here's some example of just really how diverse the data is. And if you learn from this kind of data and can't learn a general purpose sense of reasoning about the world, I don't know what we're doing. I think this is truly, captures the full breadth of physical interactions that we experience. And of course, will provide general purpose knowledge for driving that goes beyond the edge cases that we will have seen in our training set, but the full breadth of the open set world that we need to be able to operate in. So bring this together, this is enabling us to train a foundation model that's trained on many different domains of data, many different sensors, from camera to camera radar LiDAR to other sources with many different outputs, and will just be the most general purpose embodied AI model that can be deployed for safe driving and other robotics applications. So that's the system that we are building, and it's enabling the kind of results that we're seeing. And there's many videos on our website if you want to check them out. But our ability to drive through areas as complex as central London is possible because of this kind of infrastructure and scale. And so the final point on this topic I wanted to make was about how we actually bring this into automotive. And part of this is about building a system that can be not just behaviorally safe, but also functionally safe, but also being able to provide an experience that can start as driver assistance, can see the system deployed at scale, before ultimately being evolved into an autonomous driving experience. And we've been able to put together an architecture that retains the benefits of being end-to-end and data-driven, while providing a full safety case that allows us to use data-driven methods to be able to put together a SOTA first, a behavioral safety case that allows us to provably and measurably allow for performance within a certain operating domain, plus enabling all the functions from L0 all the way up to L5, from driver assistance and warnings and active safety to perception, all the way up to autonomous driving in a generalized way, which we call L5 driving. And so this architecture is again a really important part of engineering. And while it's perhaps not as interesting from an academic or algorithmic sense, it's absolutely critical to be able to getting these systems deployed in real life automotive environments. Great. So let me conclude, and then I'll be happy to take a couple of questions on this material. But I hope that today's talk inspired some ideas in embodied AI. I hope it starts a conversation, and we've got a booth this year in the expo with a number of our teams. So please come and speak to us if you want to learn more. But for me, the main conclusions are: firstly, embodied AI is the next frontier of AI. It's unlocking the next level of scale and complexity of a challenge that will motivate us to truly solve the physical world and the safety problems with AI. Secondly, self-driving is the best path to build this. There is a commercial use case, there's a societal imperative to get this technology out there, and there is data and vehicle platforms available at scale today for this. We can build trust through multimodality and ground our systems in language. We can simulate complex dynamic scenes without needing scene graphs, but we can build an end-to-end simulator for end-to-end driving. And finally, I'm excited that Wave is now in a position to engineer a product at scale. And that's what we're obsessive about in our team. So if that's something that interests you, please come chat to us. We're hiring around the world, from London to the Silicon Valley to Vancouver are our main AI offices. And look, we're truly excited to have the opportunity to now bring this embodied AI system out there at scale. So thanks very much. Happy to take any questions.
Questions? Yes. Yeah, I have several questions. So you mentioned about Gaia as a world model simulator, and you mentioned several other models like Lingo. Have you used Gaia as a pre-training for learning the policy, your driving policy? Or are you mostly relying on the Lingo 1, Lingo 2 style vision language model to do the end-to-end driving? Is my first question.
Sure.
My second question is, there have been a general trend discussing about like how to best approach the end-to-end driving from we have seen using vision language model, or like people have been talking about using a machine learning planner at a higher frequency as a system 1, and using vision language model as a system 2 at a lower frequency. This kind of solution. What's your take on this? And does Wave believe that everything just need vision language model output that? And the third one is sorry, a lot of questions. The third question is you talk about foundation model and vision language. Obviously, it is very compute cost. And how are you going to bring down this cost and convince the OEM to take your solution? Thank you.
Some memory tests as well. So the great questions. The first one, if it wasn't clear, so we're building a single foundation model across all of these tasks. So a model that has language data, it's language grounded, it's got a world model in it, it's bringing together all of these tasks in one system, and that's the system that's driving the car. And so yes, it's got Gaia world model capabilities, it's language grounded. All of these systems together is what enables the performance that we have of driving on the road today. Second, let me take the third question while it's fresh in my mind around cost. So the exciting thing is that there are vehicles around the world today that have surround sensors, camera radar, they have a GPU on board. And as I mentioned, an end-to-end stack is more efficient. It doesn't need the you know, the 4 kilowatts of compute that you might see in some robotaxis around the world, because it's a homogeneous end-to-end system that can be very compressed and optimized for inference. And so, you know, we're excited that there are millions of vehicles being produced today that have the hardware requirements to run this stack. And so we don't need to convince the automotive industry to change their vehicles. We can deploy this AI on vehicles that have been built today. And that's why one of the reasons why I think autonomous driving is the way to scale embodied AI. If you think about humanoid or manufacturing robots, there's a whole fleet and hardware bring up problem. But for driving, it already exists today. I'm so sorry. The second question was.
Language model versus like using
the hierarchy. Yeah, I mean, we of course we're exploring a number of hierarchical approaches as well as just a single system. I think the jury's out. There's pros and cons to both, and it's an area of active exploration for our team. I'd love to. We should debate it. I'd love to debate that topic.
Yeah, please.
Thank you, Berto. The simulated data, do you use the scale for training, or I noticed that in your data slide it was not part of the data sources.
Oh, it was. Maybe I need to update that slide. If not, there's synthetic data here. So yes, we use our simulator for of course, for synthetic data for training, for evaluation, the full suite of things. Yeah, it's a growing part of our data source. I won't share the exact breakdown because it changes week on week, but it's certainly a growing part.
But what's the next? I mean, generating huge amount of simulated data. Do we see some observations as to the performance improvement in some like motion prediction or planning? So I haven't figured out what's the use of this simulated data. That's why it also confused me as well.
Yeah, I think there's many uses, right? Let me talk about one specifically I'm excited about, which is being able to create adversarial examples. Now, if you try to simulate the entire operational design domain of driving, you're going to use half the world's compute. Being able to more efficiently find areas where your policy is uncertain or broken, and being able to take an adversarial step to be able to learn from how the system's behaving. I think that's one of the most exciting opportunities with a simulator, is being able to boost the training signal in the areas where the policy needs it the most, which by definition are edge cases.
Yeah. Okay. That'd be great. All right. Go ahead.
So your second last slide or something is safety by design. You have secondary computer that the end-to-end driving model that can simply further. So can you talk a little bit more how that segregation makes sense, and does it like really guarantee that?
Yeah, I mean, the great thing about this architecture is it's an architecture that scales all the way from L0 to L5. Now, there are many ways you can change it. You can architect this to be on a single computer if you want, with various trade-offs and things like that. But this is one instantiation of it. And so, the important thing here is that we're able to make arguments around redundancy. We're able to make arguments about a Swiss cheese model of safety, failure modes that are anti-correlated, things like this, and we're able to show them empirically with data. So that's one of the exciting things about this architecture. But as I say, it's designed to be something that, it is capable of being deployed in production vehicles today, and it can address L0 to L5. It's really a function of data. The more data and that you can train the system on, and then of course validate that it can acceptably drive in a given area, will allow you to advance up those levels of autonomy. The secondary computer could be a ring-fenced area on an ECU. It could be literally a secondary computer. It's I guess a redundant piece of compute that doesn't that has some redundant failure mode. I wouldn't advocate for object detection. I mean, really, we're looking to use self-supervised end-to-end learn systems for safety. I mean, that could be one way of solving it. There's many signals that you want to get out, but ultimately we want to be having data-driven systems that provide antagonistic signals via to build a robust well, I guess trajectory decision as an output.
Yes.
Does multimodality result in just better action prediction, or it's just for explain?
Both. We've seen evidence that multimodality, well, one, it improves driving performance. Two, it improves behaviors. In particular, we saw some improvement in multi-agent interactions around busy intersections. And then, of course, it enables new features like you being able to prompt and a certain behavior, or actually debugging or asking questions around why the vehicle is making a certain decision.
Yeah, please.
Could you share a little bit more about this 4D reconstruction phase one? And I would like to know how you guarantee the consistency across different cameras. We have different cameras facing different directions, right? And for them, how that is very important, how you can the 3D poses of the dynamic objects can maintain those kind of consistencies. Also, 3D poses probably not important at all in this and eventually. And yeah.
Yeah, it's a super question. Let me jump back to one of these videos. So one I want to show is, I'm most excited about this one here, right? Because here we've got cameras that are, quite significantly perturbed in space and time. And you can see the consistency and the fidelity, fine features like the color of the traffic light, or the poles, or of course the pedestrian. That's, I think, the highlight of the scene. Yeah, so this was a lot of the really challenging work for us to get to this working. Get this result was to be able to have a unified representation from a surround camera rig, and more importantly was to be able to train a 4-dimensional neural reconstruction method that can respect the time domain. We're not yet ready to release any technical details of how we do it, but I can show the results and talk about the pros and cons of it at this stage. And but you've highlighted the key challenge in getting this to work.
You have to reach in more different camera parameters, visual camera and display.
You can resample and you can re-render an image with a different camera. You can just set a pose and a camera parameters and resample an image without retraining the model. Yeah, that's important because we drive vehicles that are vans and cars. They have very different camera poses, and so we can easily transfer between the two using these kind of models.
Yeah, the last one. So of the data we plot, there are few cases for the layer is learning from the data. I was wondering if you have whether how is this integrated for the opponent or how you look at that.
So the question is, how do we simulate corner cases? Yeah. Well, the first one is we can create corner cases. I was showing some work how we can insert new agents, or we can change behavior or features in the scene to be able to create an adversarial example. That's that's one way. Or the other way is you want to be able to find edge cases, and there, one of the other things I'm excited about is how good these foundation models are and using their embedding to semantically search across data and actually find the edge cases. We do this regularly at Wave in an unsupervised way, where we have petabytes of driving video that we can search through the embedding representation of our foundation model and use that to find, I don't know, if you want to find like going through a roundabout in the rain with a cyclist on your right, we can find many examples like that. Or if you want to find a pre-crash scenario or something like this. And so, finding those examples where they are is one way, or the other way is finding adjacent examples and augmenting them by adding or changing agent behavior to be able to create that scenario. Those are the methods that we employ. Super.
I think we might have the last one, yeah.
So there's a safety part in the performance system stack beside the main engine stack. To explain more about this part, why the system needed and how to build it.
Yeah, that's I'm probably not going to give a super satisfying answer here because we've spent 8 years building end-to-end learning systems for driving and 8 years studying how to make them safe. This is one of the hardest problems, is how do you build an architecture that retains end-to-end learning, being data-driven, self-supervised, all of the benefits of AV 2.0, while also being safe in a way that complies with automotive expectations. This architecture achieves exactly that. And it's it's a key part of what is required to be able to turn this into a product. It's something that is fairly fairly core IP to us, and so it's not something that we can talk about. I know that's a frustrating answer, but I do want to plug that in general. We are and have been and continue to be quite an open company when it comes to talking about research. I've been speaking at CVPR for the last 7 years straight, talking about the work that we're doing, sharing new results. We regularly publish papers. We're writing up work like this at the moment. Gaia and Lingo have both been published in full technical reports where you can read about them. And so we do talk a lot about our work. When it comes to building a product, we're super excited to have that opportunity, to have the compute, the capital, the data to now go and build a foundation model that can be deployed in automotive and crucially make it safe. And so that's a key thing for us as a business right now. So we're looking to balance those things. We are focused and heads down on building that out. But when it comes to scientific discovery, well, what we have today here is exciting and on the cutting edge. There's still a gap from here to really a general purpose embodied AI system. And so we certainly believe that continued publishing, discussions, debates, and communities like this is something that is really necessary and wanted. And so that's how we think about things at Wave, if that helps.
How do you compare your work or from the Wave, right? There are lots of interest in your work. We really do appreciate. And with other company or research institutes like Tesla or Vivo or NVIDIA, right? There are lots of other works from them. It's just for curiosity.
Yeah, well, there's two answers to that. The first one is that we've had the privilege of doing some things for the first time. And when you do something for the first time, there is no, there is no benchmark. I actually remember publishing a paper back in 2015 on localization with end-to-end learning called PoseNet. And there was nothing to benchmark. So I created a data set around it. Now, the benefit of that is the performance was so lackluster that everyone cited it as a result because it was an easy benchmark to beat. But you've got to start somewhere. So we have started somewhere in many of these areas, and it's taken us 8 years to build up to the level of performance now where, for those of you that have come for a drive in one of our cars, it's truly exciting and robust and generalizable. You can drive anywhere within the domain it's trained on, and it's it can drive through the most complex scenes, like the one that I opened with at the very start here. For when you are working on something that does have others working on it, and you listed some examples, Hongyang, of course there are KPIs you can benchmark. Distance per disengagement is a key one. Scenario success rate, going through, for example, like a unprotected right turn with medium density pedestrians around you in the rain could be an example of a scenario. You can look at the success rate of being able to go through that. These are the kind of things that we measure internally. And of course, there are somewhat well-known metrics around the industry of what great looks like in those areas. And yeah.
Sure. That's a controversial question. Yeah. I think we really did a good job to present a lot of ideas or provide new ideas between the research and the engineering or production. Okay, sure. Let's thank Alex again.
Thank you, everyone.
We might come to the next part as for the challenge.
Well, I will keep it short. Thanks so much. I'll keep it short because I'm here only for the introduction and I'm only some random co-organizer. I'll show you at the end the people who actually deserve the credit. So it's my pleasure to introduce the NEFSIM challenge. It's a data-driven challenge for evaluation of learning-based driving policies using BEV abstractions. We use a private test set of NuPlan in the challenge for computing the leaderboard. And what we do in this challenge is we evaluate over short time horizons using closed loop style metrics in an open loop setting. So, and the metrics are the actual interesting and challenging part here. The reason for this is that you cannot use simple displacement error type metrics for doing these type evaluations. And the reason for the problems with these metrics you can see on this slide, you can have cases where displacement error tells you actually what you want to have, like here, where going too far from previous trajectories in the data set actually results in poor driving. But there are also scenarios like this where actually driving faster will increase your displacement error, but things are actually still fine, while a smaller displacement error where you deviate only so slightly from the original trajectory results in a collision. So this is the reason why in these type of challenges, simply using on displacement errors to see how we deviate from original data is there. So our metric combines, or our score that we use in evaluation combines actually multiple different metrics. One metric is like collision avoidance, compliance with the drivable area, time to collision, or you can think of it as riskiness of driving, ego progress, so we don't want cars to stand still, and of course the comfort of driving, are people driving comfortable. And for each of these we compute a score between 0 and 1, and we integrate this score in this seemingly complicated looking equation. But what you basically have to know is we particularly penalize deviation from driving area, so you shouldn't go off the road, and we penalize collisions, and then everything else is computed using some weights that can be chosen to decide the trade-offs that you want to consider in your simulation. And this type of score performs on the example we have seen just now much better, because if you actually end up with a collision, you will see the score will be 0, even if this collision setting is very close to the original driving data that we have in the data set. So ultimately we get with this metric a much better evaluation of behavior. And because we look at short terms, we are still feeling confident that what we evaluate in this metric is actually what would have happened, because the reaction times are relatively slow. Okay, so overall in this challenge, we had 143 participating teams. The two leading teams were NVIDIA and Xeron, and NVIDIA has also won the innovation awards, two awards, and I am looking forward to them presenting their solution. Before we go and hand it off to NVIDIA, I want to give a huge shout out to the many organizers, particularly to Daniel and Kasia, who couldn't be here today. They did the main work. And thanks so much to all the teams for participating. I think these challenges really drive progress in the type we develop, the way we develop systems. And now, Team NVIDIA, we look forward to hear your solution. Thanks so much.
那个是共享的，不太感兴趣。
We might switch to the next track or your.
And maybe we will have the next track first. So the next track is also using the new pen data for the private data, and also here we give many thanks to the module to give us access to the private data for putting this two track and to enjoy as there and let's welcome the circle for introducing the model.
So let's move on to the second track of the predictive world model. And the reason for us to propose the predictive world model challenge in this year is because we wish to figure out a way towards the autonomous machine intelligence by using the world model. Because as illustrated by previous presenters, they all mentioned that the predictive world model is useful for building a simulator and use the simulator to train the RL agent or whatever agent. And actually, in this track, we wish to figure out whether we can directly use a predictive world model as the intelligence itself, whether we can use the mean of predictive by prediction pre-training, whether we can obtain a good intelligent agent to obtain the autonomous driving instead of trained by simulation. So in summary, we think that if we can use the predictive world model, if we can use prediction pre-training, maybe we can enable the intelligent agent to perceive the world and learns to react. And as a result, maybe we can obtain an agent to learn a way to study the counterfactual problem, which is the third stage of the human evolution as shown in the right. That is, if we have the ability of counterfactual imagination, maybe we can develop new things, maybe we can let our agent be better than humans. So another reason for proposed challenges because we have already proved in this VPR that if we use the mean of predictive work by prediction pre-training, we can obtain a huge improvement in perception, prediction, and timing for so this is another reason for us to propose this challenge. And we need to see whether we can use large scale of Newton data and whether we can obtain a foundation models for the end-to-end autonomous driving. So this is a second reason for propose this track. And to be specific, in this track, the inputs of our model is the multi-view images in historical 3 seconds. Given the Newton, the frame rate of Newton is 2 Hz, so there are 6 frames in the historical images. And the output are future point clouds in future 3 seconds. The reason for us to use to predict future point clouds from historical images is because we wish the model to learn how to build up the 3D geometry from the image, and then how to model the dynamic of the future dynamic, how to model the temporal inference of for future dynamics. And the metric for this track is transfer distance within the range of minus 51.2 meters to 51.2 meters. So here is a summary of the challenge stats. We receive a lot of attention, so this is a new track in this year. We have 69 teams from 13 countries ranging from academic to industry. And we obtain a solid improvement compared to the baseline. And also congratulations to the first place, which is a team from University of Science and Technology of China, and the innovation award and the innovative award is a team from Huawei and the Chinese University of Hong Kong Shenzhen. And the reason for give the innovative award to the second place team is because from the award committee is that their method is distinct. It's a distinct baseline to the official baseline, and they improve the speed of the point cloud prediction by decoupling the point cloud prediction to the occupancy prediction and flow estimation. And unfortunately, the team member of the second team cannot make it to present their method on in person to us, so they carefully prepare a video to us, and so let's see some video.
Chinese
So,
University.
The background. Serving as an abstract spatial temporal representation of reality, the world model can predict future states based on the current state. The learning process of world models has the potential to provide a pre-trained foundation model for autonomous driving and also can be a world simulator. This challenge simplifies the world model as a new visual point cloud forecasting task. Given vision-only inputs, the neural network outputs point clouds in the future to testify its predictive capability of the world. The challenges of this task can be concluded from 3 aspects. First of all, we need to learn the cross-modality knowledge since the inputs are the 2D visual images, while the outputs are the geometric 3D point clouds. Second, it requires the model learn the temporal dependencies and forecast the future states. Finally, the training samples of this challenge are so huge that we should design an efficient approach to consume the huge dataset in an acceptable time. As a newly proposed task, there is only one baseline solution VDAR. By introducing the latent rendering and future decoder, the VDAR could forecast future point clouds with visual images inputs only. However, VDAR is a training-unfriendly method as it demands long-time training with the high computation resources consumption. Besides, the autoregressive manner could not capture temporal dependencies enough, and the implicit decoding in VDAR could not maintain the explicit temporal consistency. Therefore, we reformulate the visual point cloud forecasting task as a 4D occupancy forecasting task. By taking the multi-view images as inputs, we firstly use an occupancy prediction model to predict occupancy, and then the carefully designed occupancy world model is utilized to forecast the future occupancy volume. After applying the rendering operation, we can obtain the future point cloud. For the occupancy prediction model, it has been well studied, and we adapt the LSS-based method BEV-DET as our occupancy prediction model. The other popular occupancy prediction approaches like BEV-Former and FBOCC are feasible as well. There are only a few recent efforts exploring the occupancy world model. Despite having the ability to be able to predict future occupancy, OCC world requires two stages of training. The first stage of training is unstable and severely affects the final performance. The second stage of iterative prediction does not take into account the spatial structure and temporal dynamics of occupancy. To overcome the aforementioned issues, we propose a novel occupancy world model, the D2 world. It is an end-to-end single-stage 4D occupancy forecasting pipeline and is able to simultaneously forecast multi-frame future occupancy in a non-autoregressive manner. And in order to make full use of the inherent spatial structure of occupancy, we leverage the flow information in our pipeline to further alleviate the forecasting problem. The historical 3D occupancy is pre-processed into BV-map and then becomes into space-time tokens after feature extraction. The spatial temporal transformer is utilized to capture the spatial and temporal dependencies, which is consisting of multiple spatial-aware local temporal attention blocks. After that, we leverage another spatial temporal transformer as flow decoder to forecast the flow information in each future timestamps. In this case, we could apply the warping and refinement operations to transform the current frame occupancy to obtain the future occupancy more easily. Considering the required future point clouds only contain 3D geometric structures, we choose to forecast future occupancy density volumes. Finally, the future point clouds can be obtained by rendering from these future occupancy volumes. Unlike the images containing redundant information, the occupancy is a high-struct and compact representation, so we introduce spatial-aware local temporal attention block for spatial temporal feature extraction. It has similar structure with vanilla attention, except that we utilize the 2D convolutions to retain the structural information rather than the MLPs. And the 3D CNN is used to replace the original FFN layer for capturing the local short-term variations. When designing our occupancy forecasting model, we found that most of the voxels in next frame could be easily derived from last frame, since most of them are static. So we choose to forecast the future flow map to alleviate the occupancy forecasting process. Further, we could leverage the occupancy semantics information to decouple static and dynamic grids, and then the flow map can be only applied on these dynamic voxels for better forecasting. Specifically, the flow decoder forecasts the future absolute flow maps with respect to the current frame. And we can use the future ego poses to current ego pose transformation to transform the flows and then warping current frame to all future frames. In actual implementation, we force the flow of static voxels to be 0 before warping. After that, a simple refinement module is utilized to revise the warped features. Therefore, this is our whole pipeline, including occupancy prediction stage and 4D occupancy forecasting stage. The optimization losses of stage 2 are the same with VDAR, and without any other tricks and models ensemble, we achieve competitive performances. The dataset of this challenge is OpenScene dataset, which contains more than 0.6 million full training frames and 40,000 mini training frames. Each frame has 8 multi-view images. The chamfer distance is used to evaluate the point similarity of forecasting point clouds and ground truth. The lower the better. And the other experimental settings are listed here. According to the challenges rule, we use 6 historical visual frames to forecast future 6-point clouds frames, and the size of input images is 512 times 1408. The BEV det with Swin transformer base as the image backbone is leveraged as our occupancy prediction model. And different with original BEV det, we use the class Waith cross entropy loss and the low Vaz softmax loss to improve performance. We train both stages within 24 epochs. Here are our point cloud forecasting performances. It is obvious that our method achieves state-of-the-art performances. Specifically, when training our model in the 1/8 mini training data, our model could obtain average 0.71 chamfer distance, while the VDAR baseline only achieved 1.58. Although without using the flow forecasting strategy, our method still obtains 0.89 chamfer distance. It validates the effectiveness of reformulation of 4D occupancy forecasting for solving this problem. In order to submit the results to the online benchmark, we additionally train an occupancy prediction model. Our best results achieve 0.79 average chamfer distance and rank second place in the leaderboard. This is a screenshot of our results in the official leaderboard. Although the performance of our method is slightly lower than first place, our efficient method has potential to extend to large-scale dataset. To compare the training efficiency of our method with VDAR, we compute the training hours and GPU memory usage for each method. From the results, we can easily find that baseline requires both long training hours and high GPU memory. In comparison, our world model requires much few training hours and acceptable GPU memory. And despite our training time is mainly spent in stage I for obtaining better occupancy prediction performance, this module already existed in modern autonomous driving systems and can be also as our world model's inputs. Conclude our work. We reformulate the visual point cloud forecasting task as a 4D occupancy forecasting task and propose a novel and flexible framework with decoupled dynamic flow in a non-autoregressive manner. The experimental results show that our method could achieve competitive performances and require less computation resources and much few training time as well. Although impressive, our method still needs further exploration. For example, the stage 1 and stage 2 could be end-to-end training for optimization, and we can further explore the performances of scaling up image backbone and world model networks. The code of our method will be released in GitHub. Please stay tuned. Here are some selected references. Thanks for watching.
After the session, we
Okay, sorry for the display error. My name is Zhenxin Li, and I'm very happy to represent Team NVIDIA to share our first place solution, HydroMDP, for this end-to-end driving at scale challenge. Okay, so our introduction mainly consists of 4 parts. We'll first talk about the background, and then our solution. Then we'll talk about the experiments and the conclusion. And Igor has just introduced this NavSim dataset. So basically, the datasets that were previously used to benchmark end-to-end planners, they have a lot of problems. For example, the major paradigm was imitation learning, and these methods are all very vulnerable, and the metrics like imitation errors that are employed to evaluate these planners are also biased. So NavSim here evaluates the planner with simulation-based metrics that can actually take into account how safe your planner's output is. And before HydroMDP, we conclude 2 prevailing paradigms. The first paradigm is called single model planning and single target learning. So basically, the model regresses a single trajectory, and we use the log replay trajectory that acts as the only positive sample to supervise the model's prediction. And the major problem is that the model receives very limited supervision from log replays because there is only one single positive sample. And the second paradigm is called multimodal planning plus single target learning. So basically, the model predicts multiple trajectories instead of one trajectory, which is also supervised by the single log replay trajectory. So it also faces the same problem as the previous paradigm. And the second problem is that it often uses non-differentiable post-processing to select the best trajectory based on the model's perception output. And the problem with this is that if your model's perception is imperfect, then it harms the final planning. And also, this process is detached from the neural network, so it does not really align with the spirit of an end-to-end model. And here we propose our third paradigm, which is multimodal planning plus multi-target learning. So apart from a single log replay trajectory we use to supervise our end-to-end planner, we also use a rule-based simulation engine to generate multiple trajectories, which are also used to supervise the planner. And since these generated trajectories are from a rule-based engine, So these trajectories are safe for each scenario. And the other benefit is that we integrate ground truth perception in training the planner instead of resorting to some non-differentiable processing techniques. So this is our overall architecture, and there are three parts for our architecture. There is this perception network, and there is a trajectory decoder that generates multiple trajectories. And we also, our major novelty here is this multi-target hydra distillation. For our perception network, we use this transducer, which is the official baseline in the NAFSM challenge. And for the trajectory decoder, we have this a fixed planning vocabulary that contains about 4,000 or 8,000 trajectories that are sampled from the new plan database. And we use a distance-based imitation loss to supervise this whole planning vocabulary. So in order to reward the trajectories that are very close to human drivers' behaviors. And then for the multi-target hydra distillation, it basically consists of two steps. The first step is the simulation of the entire planning vocabulary with ground truth perceptions, so that we can see here for each metric, we have a set of trajectories that best fit this metric. And we have a set of hydra prediction heads which are trained to fit these rule-based teachers. So the advantages of multi-target hydra distillation is that it does not rely on non-differentiable post-processing techniques, and it can also bring sufficient supervision for the entire planning vocabulary, because previously if we use imitation learning, then we only have one positive sample. And the third benefit is that the ground truth perception can foster planning in an end-to-end fashion. And during inference, since our model cannot fit each teacher perfectly, we use a weighted sum of all of these confidence scores to calculate the final cost. And we find that in this NAFSM challenge, it is necessary to prioritize rule-based costs over imitation because the metrics of this challenge does not take into account how close you are to the log replay trajectory. And here are our some experiments. We find three things that we think are very important. The first thing is that if we employ a larger planning vocabulary, the method can yield better performance. It's basically because if you have a larger vocabulary, then you have more candidates for the model to choose from. And the second thing is that if we try to teach the model to fit the overall PDM score, it leads to degradation in the final performance. And I believe it is because the overall PDM score is too random and it's too complex for the model to learn. So this also suggests the necessity of our multi-target learning paradigm. And the third thing we find is that if we involve an extra single learning target, we can get improvements on this corresponding metric. So this also demonstrates the scalability of our methods. So we can involve more traffic rules or like traffic lights or traffic signs in our model, and we can scale our model in that way. So finally, under the same setting, our version surpasses the baseline by 8.5% in the overall PDM score. And the other part of experiments is that we try to scale our model up with larger backbones and larger input resolutions, because previous literature like UniAD, it suggests that if we use large image backbones, it only leads to minor improvements in the final planning performance. And here we use larger backbones and we use larger resolution, and we can find that our methods reach a higher PDM score. And here are some visualizations. And for this one, we can see that the lengths here are very different. There are these small metal humps. However, our model can understand the map structure and stick to the lane it is driving on. And the second thing is our model here is trying to overtake a long-tailed object, which is a utility car that is probably traveling very slowly. And we can see our model here is trying to move to the right lane to surpass this object. And the third thing is also a very interesting example. I think basically the Eagle vehicle is placed at the center of two lanes. So even for human drivers, we may not be able to predict whether the model is going to the left lane and make left turn or going to the right lane and make right turn. And this is the ambiguity in intentions. And we can see that our model here is slowly moving to the right lane and make a right turn instead of going in the middle of these two lanes. And that's basically our presentation. We have presented HydroMDP, which is a teacher-student model leveraging human and rule-based teachers. And it is also a framework that learns how the environment influences planning in an end-to-end manner. And HydroMDP achieves the state-of-the-art performance on NavSim. And we want to thank all the contributors and the entire NVIDIA team. And that's our presentation. Thank you.
And in this year's challenge, except those check on autonomous driving, we do have a check on embodied AI, the multi-way 3D grounding track, and I will give us some introduction.
Hello, everyone. I'm Tai from Open Rover Lab. It's a great pleasure to be here to introduce this new track, multi-view 3D view grounding. And this is a new track that is coordinated with Open Drive Lab. And now let me introduce this track. First, let's have a brief review of this roadmap on 3D perception. As we all know, 3D perception for off driving and also indoor scenes have made great progress in past few years. There are many popular datasets and benchmarks, such as KT New Scenes, Lyft Waymo Argoverse for driving, and StarGD ScanNet, 3R Scan Multiple 3D, HM3D for indoor scenes in the global view perception. And now transferring from the auto driving to indoor embodied AI, as we all know, except for learning interaction, learning from the interaction, the embodied AI needs more multimodal egocentric 3D perception for holistic scene understanding in enclosure space. So we established embodied scan that is collected from the previous raw data in ScanNet 3R Scan Multiple 3D, and then annotate over 1 million language prompts and 160,000 instances with oriented poses. And for different perception tasks, including 3D detection, occupancy prediction, and real grounding. And also for egocentric inputs, we also support monocular image, multi-view images, and continuous frame. So in this track, we mainly focus on multi-view 3D view grounding, and the setup is the model is selected to take the multi-view images input given a language prompt about the target object and output the grounded objects that is represented with a 3D bounding box. The metric is a conventional 3D LU-based accuracy that is similar to 3D detection. And there are some statistics for this track. There are also lots of tension on the newly introduced tasks from over 60 teams, participants, or 12 countries, regions, and 150 submissions. We also observe a solid improvement by the outstanding champion, and we will welcome the winner team to introduce next. And so congratulations to the first two teams from Tsinghua University and Lenovo and Xiaomi Robot. Last, we will introduce what's next from our team. That is follow-up of embodied scan to build a multimodal 3D dataset with hierarchical language annotations for pushing forward the training of 3D LLMs. Maybe no voice. It is the largest ever multimodal 3D dataset with hierarchical grounded language annotations. That you can see the model trained with this dataset. It can achieve basic grounding and dialogue abilities from 3D LLM. You can see some counting problems and also description for objects and regions. Sometimes we need to distinguish different objects from a long video. For example, here distinguish from the white and black chairs in the room. So this is a data set that is built upon the previous embodied scan, but more focused on hierarchical grounding annotations for different aspects of these things. And also the language prompts are more complex. So because the time is limited, let's see more details from our project page and our paper. So next, let's give the time to the winning team and welcome Jiaheng to sharing their solutions. Thank you.
Hi, good afternoon, everyone. I'm here to represent my team from Tsinghua University and Lenovo AI Lab to present our solution for the multi-view 3D grounding challenge. So our solution is called DenseG, alleviating vision language feature sparsity in multi-view 3D visual grounding. And it's presented by me, I'm Henry Zhang, and our team consists of people from Tsinghua University Leap Lab and Lenovo AI Lab. First, I'll discuss backgrounds related to this challenge, and then I'll show some motivations that we develop our method, and then we'll discuss our method and experiments. So first, the multi-view visual grounding, it aims to locate objects in a 3D scene based on the natural language description. It is a fundamental task of embodied multimodal 3D perception. And as Taiwan discussed, I won't discuss this again. And the baseline that we use is the embodied scan, also discussed earlier. So basically, we have a visual inputs, the point cloud and multi-view image sequence. Then we get a language prompt. Then we have to locate the object in the scene following the language prompt. So the some problems we found in the previous methods is that they use a scene level inputs from the global view, and embodied scan improves it by using real scan inputs from multi-view, which is more like a real life data sets. But the problem here is the way that the embodied scan fuses the visual inputs is through a sparse fusion method. And this method, the problem is, let's say for a small object, only a very few point clouds will be representing this small object in the point in the scene. So it is very difficult to identify this object in a point cloud with such few point clouds, but it is easily recognizable in the RGB images. So the motivation is, of course, what we said earlier, lack of to the visual sparsity problem, and then another one is the language sparsity problem. Let's say there is a prompt, find the chair beside the table. But as you can see in the scene, there's a lot of chairs, which is very is a ambiguous prompt. There are some cases that has this kind of prompts. So we improve it by giving more context to the models. So of course, insufficient anchors, it can lead to ambiguity in localization. And then, of course, the language context is insufficient. So with these motivations, we develop our method. Here's an overview. First, for the language model, we first perform augmentation by using LLM. Then we develop a by TV module that enhances the visual features. So for the LLM augmentation, there's 3 steps. First, we construct a scene info database. For this scene info database, from the original data set for the same scene, we collect all the language prompts. Then we formulate a scene info database. Then this provides a context for LLM to augment the text prompts given to it. And then of course, we want to make sure that it is consistent with the info database. So we verify the results again using LLM. So the prompt principles are, we want it to be sufficient and reliable anchors. And then of course we so we follow a view refer to use an opposite view only for view dependent text. And then of course we want a high confidence for the anchors. And then we also propose another module called by TV. This is to enhance our visual features. So what we did is first we extract the global features from each of the views, and then from the views we perform self-attention for interaction between views. Then we perform cross-attention with the text models, and then it's to reduce the multi-view semantic information loss during the 2D 3D fusion, because we already extract the 2D features and then we add it back to the fusion module. And for our results, we use we follow the embodied scan. So we didn't change the backbones, and we use the ResNet 50 for a 2D backbone, the Minkowski-net 34 for the 3D backbone. And then for the text backbone, we changed from Roberta to Clip. Then as seen on the mini validation data, 1/5 of the full data, by simply replacing the Clip encoder, we already gain around 1% MAP improvement, as shown on the left column. Then with our LLM augmentation, we achieve 3% MAP improvements. And then for by TV, we have another 1% gain. And then for the full data set, just by using this, we are trained on 8 epochs. We have 47.23, and then ensembling different models, we get a 59.59 MAP for the IOU 0.95. And with this result, we got to the top 1 in this challenge. And some tricks we use, these are the tricks that we found most helpful in our method. One is CVGS, the class balancing, grouping and sampling. This is during the pre-training stage. For the object detection, we do a balancing for the long tail distribution of classes. So this kind of alleviates the long tail problem. Then we also use an NMS-based ensemble. That's what we use for the final model we use to submit to the leaderboard. So as a conclusion, we propose the DenseG. For the language modality, we enrich the language prompts via a scene information database and LLMs to reduce the negative impact of distractors. For the visual modality, we propose a ByTV module, the text and view image interaction module, to reduce the loss of multi-view semantic information. And here are my collaborators. We thank them for the contributions to this work. And if you want to know about work from our lab, THU Lib Lab, you can scan the QR code to visit our GitHub. Thank you.
And here we come to the last year in the morning, the occupancy and flow check. Like in the last year challenge, the occupancy check, the most attention worldwide. So this year we keep it and we add some additional flow annotation to the data set. And Jiajun will give us some more detail.
As this is the last track in the morning, so it will be very quick. Okay. So the 3D occupancy, the motivation of introducing this test is the problem of the current commonly used 3D representations, like the 3D boxes, bounding boxes. The 3D bounding boxes closely represents the geometry shapes and the position of the objects in the scene. However, it easily ignores the fine-grained and detailed geometry shapes of the irregular object or open-world objects. Instead, 3D occupancy greatly catches the geometry shapes in a unified manner by representing the objects in the scene as a set of voxels, whether occupied or not. As a complementary representation, flow also captures the dynamics of the whole scene. That is a vector of each voxel. And the occupancy and flow has also been integrated in commercial solutions like the Mobileye and Tesla. So for this challenge, our evaluation metrics include two parts: the occupancy prediction. For occupancy prediction, we use MIOU, which is commonly used for semantic segmentation. And for flow prediction, we easily adapt the L2 distance of the predicted and ground truth flow. The final evaluation metrics was the average, weighted average of the both metrics. So we would also like to thank our collaborator LiveWheel AI for presenting their good data set, LiveWheel occupancy, which can be used to augment the data diversity of the nuisance data set. For the challenge status, we have in total 97 teams this year from 17 different countries and regions, and there are a total 153 submissions in this track. And the outstanding champion goes to the IEIT team, and the honorable runner-up goes to the Harbor Chips teams. Congratulations. So due to the time limits, we will leave the solution of the winner during the lunch break, and please come back at the 1:30 p.m.这就放声音大点。
接上这个吧。
I've been doing this project. So basically, try to see. So we have this report. We have.
It is a, yeah, so, and then we have gamers who down with the robot drive the robot. So gamers anywhere in the world. So and as right now the gamers have money. So my understanding in gamer can anywhere in the world. Computer, exactly. I can show you like from theater perspective of yeah, something like this. Say so this is what the game is doing. So this is what we see. So it's just driving around and then we're giving points. It's like exactly. So right now, but as we it's just so we've actually open sourced about and so
human gamers doing. Yes, I'm your front camera, back camera, speaker, microphone. So, and I think going forward, we want to continue to open source a lot of this data. So that's one aspect. The other thing is also we are actually organizing a competition at IROS this year for the over childhood. So because right now we have all these human gamers that we're playing the game, so they form kind of a human band. So the idea is that we have gamers, teams from around the world who compete. I think and basically they drive around.
I think we have another colors here, so you can see the dogs.
So these are the different
or maybe we can print it out.
Yeah, this is so they and so the goal is basically they navigate from point A to point B, and then when they successfully complete, then they get the points. So we are actually organizing this with a bunch of researchers from DeepMind, like Berkeley and US. So basically, these two things will open the data set. And also this competition that we are organizing
for the panel.
I would love to explore to see because I've never organized. I've never organized a competition like this before. No, so this is happening in October. So you began. Yeah, in Abu Dhabi.
I think that
this year IROS is Abu Dhabi. So, but I know you guys are very familiar with organizing competition. Yeah. So I would love to explore to see whether there's any way we can work with like OpenDrive Lab. Actually, I don't know much about OpenDrive Lab except that you guys do a lot of this.
Okay, so they need to be here.
Okay. Get teams to.
So like we have 4 chairs, 5 chairs here. We need to have 3
actually. Yeah. So he's actually one of the 4 organizers. Yusha, I don't know whether you know him, like the big model, circular bin. So I think we have good co-organizers. But again, I look at what you guys have done over Drive Labs. I'm very impressed, like, all the So I mean, I'm from a small little company, so I just happen to have the data. So yeah, I'd love to find out, like maybe introduce myself properly to the team and actually how is OpenDrive related to Shanghai AI Lab? Like, is it
something we are just a small under the lab.
So OpenDrive Lab is a bigger thing, is it?
No,
it's a small thing. So the Shanghai AI Lab is a bigger thing.
It consists of many labs, the open and the open lab. So we are doing based on
I see. Yeah.
The lab began with the Shanghai AI is forming a system with lab. Open
Got it. I see. So, yeah, I mean, who do you think I should speak with from your end? I don't know, like basically because I look at you guys professional how to organize. This is our first time organizing. Although we do have people on the line, but again, like, I think we can use more like help. So I was wondering whether you guys.
And do you know how the microphones work? I think they are working when we are during the morning. They are working. So right now, Sherry, I think Sherry used one of these.
I think by October we should have about 10,000 hours. So I would love to work with two researchers to actually open source the data during the next round.
Yeah, but I cannot go to. I'm managing this with go to my phone.
Yeah, like
Yes, yes.
Hong Yang, okay. Maybe I think he can be. I mean, he should be coming back maybe. Okay, okay. Yeah, maybe if later on if you can introduce me to him, I can share a bit more, and then yeah, I want to explore and see whether like there's something we can do together. Yeah. So you are based in Shanghai?
Yeah.
Oh, okay. I'm based in Singapore. Yeah. But we have a small team, small hardware team in Shenzhen. That does the robot. Yeah, in Shenzhen. Yeah. So my brother is doing have a small team in Shenzhen doing those robots.
Yeah, it's fine.
Yeah, but the rest of the team is we're doing basically the game, right? So we have like people around the world. Yeah. But the company is a Singapore company. Yeah.
Actually, we don't invite anyone.
Right. Nice speaking with you, Hui Jie, right? Okay, Michael. Yeah. Okay. Bye. Thanks.
Social capital and people that saw in and decided to join the competition. We can talk to some guys about and make that what kind of
把这个视频播了。这个视频播了。对的，这个视频播了，然后下一个还有另一个视频。
啊？这不能设置一个循环播
啊？
能设置一个循环播？
没事，这手动就好。
每次手动。
嗯。
那个人要找你的票。哎，对，我太记得了。
Yeah.
Yes. I when I saw you, you already said to introduce them. But much. Yeah. Yeah. With what do we do? I don't think you. There are yes. Do you have any waterfall?
Our company, one of our and yes, we will. Okay. Um, I do. Okay. Uh, right. The picture. Either. Ready? Thank you.
你讲的是吗？我不知道，我不确定，我不确定。
Criteria of the score are different, right? Yeah. That's not the vacancy. The daytime data. In circle. The manufacturer comment will have a cooperation relationship with any Chinese manufacturer. Yeah, university still that they don't actually, yeah, we understand that um function and in and they are much better than Korean students in Korean industry. So I want to teach them. Teach me all the other and electron. Not sure. Not something like that. Yeah, it could be kind of sharing the results of the research. Yeah, it would be useful now and yeah. Yeah, yes. Um, yes, yes, yes. Yeah, since the and get up from the and speak. Yeah, 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 yes. So I like him. It won't get that. Yeah. So, yeah, culture, culture would be fun.
There is no audio here.
Yeah. Okay, yeah, I'm Raj. Yeah.
Rajesh? Rajesh. Nice to meet you. I'm Crystal. And your last name is pronounced Ambrush?
You are chairing the afternoon.
Yes, yes, exactly.
Yeah, I wanted to, like come in and take a look in the morning, but it was packed.
I know. And many people were kicked out, all the people who were standing.
Yeah, there was a lady
For
who
security
told
reasons.
me to start the talk and just sit down or get out.
Yeah. Well, you don't want. Don't worry about
Okay. Sounds good. Yeah, but very successful. Congrats.
Also,
Well, let's see. But, like in the morning, I check another room.
Yeah, I'll be actually I have the top version.
Yeah. Ah, you changed it.
Like just talking about.
Yeah. Yes.
So then now I'm doing like.
You're presenting.
I think so, yeah.
Or gather speakers, please.
No, I wasn't.
Yeah, so that's yours.
This one.
This.
I should probably test it. So I think.
Yes, we have also we have the Zoom link normally.
That's going to be interesting.
Yeah. I can try to share.
I think I got it. Yeah, you this one I devoted back to your and then audio you can link here then you have which one this one on the back.
Ah, yes, I'm there.
You can press when the Zoom.
Yeah. So do I have like, because I think there are not really so many slides for this part. Here you can see. Poster, and then this is
This is another video. The left side.
So this is already the challenge, right?
Yeah.
So I don't have any slides for introducing so I can like just do it without the slides.
Yeah.
And then we have the camera. So yeah, I mean it should be audible by the microphone.
Yeah.
I can have the microphone perhaps to introduce. Connected. I'm not on Zoom.
不是，然后12分钟，不是2分，不是放这个呗。
We need here immediately use more like Microsoft the Teams.
Yeah.
You don't use
You need to share your screen.
Yeah. So
you can copy your screen at the monitor.
You're right. And, oh, good. Okay, good. Do you have any videos, perhaps? I have, yeah, I have lots of videos. Okay, seems to work. All right, it's not the whole presentation. Yeah. Okay. So. And I should share the screen on the. Yeah, share screen. Yes, and then you can also hide the, this control. Then hide the video part. Yeah, that's good. Show video time? No. Hide number. Wait, 10 minutes of our we'll just move this guy also here. Yeah. Okay, that's great. If we have most people already here, because anyway we cannot take more, right? Yeah. Beyond those who sit. Maybe we wait a couple of more minutes and then we start, because I see only 4 or 5 empty spots, right? So yeah, there might be we can perhaps gain some time from the later part. Yeah. Okay. Yeah. Okay. So maybe it's a good idea that I also enter the Zoom for this time. See your slide normally. Yeah, perhaps it's a good idea to check that. Zoom. Yeah, like as a backup, but then I will leave that to Raresh. Maybe if one guy can go outside and say that we still have like 4 or 5 free spots, okay, because I see some people are waiting outside. Yeah. We have some spots. Because you also have 2 interesting works here now, right? Yeah. Okay. You're talking some of them. Okay, great. Some of them are supposed to be on Antep, but they're not on Antep. Oh, IP things. Oh, okay.
Also is helpful. Also is helpful.
So maybe we can
get started.
Good to introduce you.
Hi everyone, welcome back to the workshop. Next speaker we have is Raresh Ambrush. He leads the computer vision team at Toyota Research Institute, and his interests lie at the intersection of robotics, computer vision, and machine learning, with the aim of discovering visual representations for embodied applications in areas such as automated driving and robotics. It's very nice to have you with us, Raresh, and we're interested to hear your talk. The scene is yours.
Thank you very much for the introduction. Can everybody hear me at the back? Okay. I was also told that when I start the talk, I should ask everybody to sit down, and we're not supposed to have people not on chairs. Okay. So the title of my talk is Visual Foundation Models for Embodied Applications. And can everybody see this? And on Zoom, I wonder if everything is.
Yes.
Okay,
Yes.
good. Thank you. Yeah. So first, before diving in, let's talk a little bit about the vision that we share at TRI. So our goal is to create new technologies that are going to enable Toyota products, existing products and future products to improve quality of life, both for individuals and for society as a whole. And TRI is structured into a number of different teams and divisions, each addressing a different fundamental challenge. The computer vision team, which I lead, is part of the robotics division. And as a computer vision team, of course, we're in the business of training visual representations. And the idea is that we take these representations once they're trained, and then we plug them into various downstream applications. And of course, we aim to find the best kind of representations that will then enable quick adaptation and eventually generalization to any kind of downstream task that we care about. And so, of course, there are many different ways to train visual representations. And over the years, we focused on a few key properties, which we think are important for visual representations to enable downstream applications. The first thing that I'm going to talk about is understanding 3D structure. And here what I mean is, given some set of sensory data, typically an image or a set of images, we want to encode these into a latent space from which we want to be able to decode the geometry of the scene or the 3D structure of the scene. And not just decode, we want that to be metric because we want embodied agents to use these quantities basically to operate in the field. The second thing I'm going to talk about, the second key property is motion. And motion is a rich signal for learning, not just for embodied for ML models and embodied agents, but also for humans. And it's key to how the brain develops and how we learn to perceive and understand the world. And if embodied agents are to be successful in interacting with the real world, they should be able to understand things like static versus dynamic, concepts like object permanence, making predictions about the future, and so on. The third property is this idea that representation should be object-centric, and we believe that objects are a useful abstraction in thinking about the world. And object-centric representations basically allow us to use perceptual content for action and for symbolic cognition. And modeling these objects with high accuracy is also important for embodied agents in the sense that if you learn to do an operation on a particular object with a particular geometry, then transferring that to similar objects with similar properties should be easier if you have a nice, well-behaved object-centric representation. And finally, I'll also talk about interpretability very briefly. We would also like these representations to be explainable and interpretable, and we would like to understand what they learn, what they miss, and where we should correct things so that we get them to behave the way they should. Okay, so the talk is going to have four broad chapters, and I'll dive into 3D structure, which is the first one. So the ability to learn 3D perception from cameras has been a key research direction in our team for many years. And in particular, we focus on depth estimation, which is a fundamental challenge both for driving and for robotics, where basically agents need to be able to interact with the world, which is three-dimensional, from just images, which are basically 2D arrays of faces. And so learning how to predict depth from a single image is an ill-posed problem, but we have centuries of geometric priors, which we can leverage derived supervision and self-supervision to be able to train these networks. And so what we normally do is we use camera models and projected geometry and multimodal consistency to apply top-down supervision and train these bottom-up networks so that they can learn to infer and predict depth from a single image or from a set of images, depending on the situation. And so I just want to spend a little bit talking about how this works in the self-supervised setting, which is something we spend quite a bit of time looking at. Basically, what we have
You can continue.
No microphone, but it's okay. People in Zoom are
yeah.
maybe cannot hear, but maybe people at the back can hear.
Yeah.
All right. Is it working?
No.
Yeah. Is it not working? It's
No,
working.
no, it's working. Yeah.
All right. So basically what we have is a sequence of images, which is captured by a moving camera. And what we want to do is we want to derive some kind of self-supervised loss where we don't have to use labels or annotations, which are usually more suited to capture and so on, and require hardware and things like that. So what we do is we take 2 consecutive frames from the sequence. We use one to predict the geometry of the scene, and then we use 2 consecutive frames to predict the angle motion. And then we can use these 2 quantities to basically derive loss by reprojecting pixels from one camera to the next and taking a photometric difference. And this actually works surprisingly well in practice, and we published a long list of papers. This is just a subset on this topic, and this line of work is led by Vitor Ghizzellini, who is a scientist in my team at TRI. And basically, up until 2022, we focused mostly on the self-supervised aspect of things. And we basically proposed new architectures, new losses, extensions to different camera models. We've also looked at different downstream tasks, and so on. And we've pushed the boundaries of what's possible with self-supervised learning to the point where in some situations, with some assumptions, self-supervised methods are even better than supervised methods, basically. And so what we see on the left over there is a typical output of a system like this. The top left is the input image, and then we have the predicted depth, and then we have the point cloud right next to that. And it's this is actually HD, and it captures most of the details, the structural details of the scene. Code and papers and all that are available on GitHub as well. And so we've also looked at combining self-supervision with different downstream tasks. So we used simulation heavily to generate data for tasks for which annotations are expensive, like semantic segmentation. And so while it's easy to generate this with simulation if you have the right simulator, there is a domain gap, which is an issue when trying to transfer these methods to the real world. And what we found is that self-supervised learning basically proves to be surprisingly effective in overcoming this domain gap when we combine it with synthetic data sets. So what we show here in on the bottom right is a GIF from Gouda, one of our methods, where we basically train a semantic segmentation network in simulation. We combine that with self-supervised learning in the real world, and we minimize this domain gap. We also looked at combining depth estimation with 3D object detection, and we saw that this helps improve performance, particularly on tasks which have fewer labels, so pedestrians and cyclists. And this is a snapshot from DD3D, one of our papers from ICV 2021. And this line of research is, of course, useful in theory because we can derive self-supervised losses without any kind of ground truth. It's also useful in practice. And here are some examples of where we ran this method and some of the common use cases that we're looking at. This is an example of a static camera, and we're trying to find pedestrians. There's a more challenging scene with a snow-covered street. We also looked at more extreme situations, like this motorcycle, sort of an extreme sports scenario. Here, there's a collaboration with the robotics, one of the other teams within the robotics division, where we basically run Monolith inside a very small range, inside a bubble gripper that the robot is using to basically push against some object. And finally, this is one of my favorites. We also ran this method underwater, and we're reconstructing basically part of the seafloor. And we can do that because one of our methods estimates the deformation of the lens. And so actually underwater, you get all these interesting deformations. And it worked. And so the question is, or one of the questions is, have we solved all of the relevant issues in 3D perception? And sadly, no, there are a few limitations that remain. In most cases, these resulting models and the predictions are unscaled. And this is sort of a byproduct of learning on videos, where you basically learn quantities that are sort of arbitrarily scaled or unscaled. A second limitation is most of these methods are trained for a particular domain. So you want a network for outdoors and parameter for indoors, different situations. They also tend to overfit to camera models and so on. And the third is they don't really output uncertainty, at least not in our the methods that we looked at. And so in 2023, we transitioned from the more typical sort of CNN style approach, where we have one image as input and one depth map as output, to training implicit representations, also called neural fields. And this was also inspired by recent breakthroughs at the time in neural radiance fields, light fields, and so on. And so the way these words function is we first encode available information into a latent representation, and then we can query this latent representation from any new viewpoint to generate the estimates that we care about. And what we found is that these implicit representations are much more flexible than CNNs, and also much more efficient. And so I'm going to very briefly talk about 3 recent papers and their main highlights. And I'll mention that they're all based on the perceiver architecture, which we like because it's very efficient at encoding and then decoding lots of different types of data. Okay, so the first method I'll talk about is called define, which is short for depth field networks. And what we looked at over here is how to encode multiview geometry, or how to learn multiview geometry implicitly in the neural net. And over here, instead of enforcing geometric constraints, such as cost volumes or bundle adjustment and things like that, we let the network learn these constraints or correlations directly from the data itself. And what we do is we use knowledge about the camera extrinsics and intrinsics to create these geometric embeddings which are passed to the network along with the images. And what happens is these embeddings condition a latent space, which is a global latent space shared across all the samples, across all the data set. And once we condition this latent space at inference time, we can basically decode it from new viewpoints and obtain, in this case, depth estimates. And what we show here is a nice visualization where basically we have 2 gray cameras. Those are used to condition this latent space. And then we have a red viewpoint, which is moved around. And from that red viewpoint, we decode novel depth views, which we wouldn't have been able to do with CNN, where you basically take as input one image or a set of images, and then you decode what corresponds to them. Another cool thing about this is that it basically takes about 5 milliseconds to decode one of these novel views once we've encoded them, because the perceiver architecture is very useful at these kind of tasks. The next method I'll talk about is called Delira, and I'm staying very high level over here, but obviously there are many technical details in getting these to work properly. So Delira stands for depth, light, and radiance field, and we made 2 main contributions over here. The first is we showed that the self-supervised photometric objective can be used to improve volumetric rendering. And basically what happens is this helps fix the shape radiance ambiguity that's sort of an issue with radiance fields. So for those of you who are familiar with nerves, you know that if you have just 3 views of a scene, for example, or 2 views, then you can encode them into a latent representation from where you might be able to render nice images, but the geometry is usually very, very poor. So it turns out that when you use self-supervised photometric consistency, you can render new views and add additional information and constrain this latent space so that the geometry actually looks much better. And the second contribution is we basically decoded from the same latent space multiple tasks. We looked at depth rendering, so depth fields, light fields, and also radiance fields. So that's photometric rendering for one task and single gray rendering for multiple tasks. And finally, zero depth is a very recent method. Here we move back to monocular depth estimation, and what we want to do is we want to tackle scale ambiguity. And so in addition to that, and unlike our prior works here, the latent space is also variational, which means that we can then get estimates with uncertainty. So what that means is we keep the mean and the standard deviation, and then we can sample multiple times from the latent space. And so we trained zero depth on a combination of data sets, and we found that we achieved zero-shot transfer to multiple domains, which is very good. And to conclude this first part of the presentation, I just want to highlight zero depth and the fact that the code is basically available online. We think of it as a foundation model for generating 3D structure from images, because you can basically run a zero shot across multiple domains. You get metric depth, And it's very easy to use. You just load your image with intrinsics, you pass them to the network, and then you get the depth map and the uncertainty estimates. And so I guess to conclude this section, if there's anybody out there who's using just 2D images, you should give 3D a try, because you can basically just get it for free with these kind of networks, and they're getting better and better at operating zero shot across multiple domains. Okay, so that wraps up part one. I'll move on to part two, which is motion. So changing gears a bit, I'm sure we've all seen all the impressive recent results in 2D segmentation, and in particular the segment anything model, where you basically click anywhere on an image and the model gives you back a pretty good 2D segmentation of that part in that image where you clicked. And so the question that we asked ourselves is, what about tracking? Do we have something that's similar and that works as well for tracking? And sadly, no, or maybe I should say not yet. Basically, what we want to do is we want to indicate any target in the video, a point, a box, a mask, and we want the system to just be able to track that over the video. And so instead of a general system like that, what we have is a series of these bespoke solutions for different types of inputs and outputs. We have something called star for boxes, we have masks for masks, and then we have pips for points. And they all work great for their particular task until you get into a situation where basically they don't work so well anymore. And one of the intuitions behind the limitations is the fact that these pixel-sized entities, like we see in the image over there on the bottom right, basically grow to be full regions. And so if you have a tracker that tracks points, by the time you get to the third image, maybe it's not going to work as well. Then a second issue with existing methods is, perhaps by design, this idea of an information bottleneck. So if you think about this image on the left, what the tracker actually sees is this associated correlation map, which is what's correlated from the first image and the second image. And because most methods reason on this kind of compressed representation, they miss out on crucial information. So what happens here, in fact, is the horse is not going to go forward. It's going to have to jump over the fence, because obviously there's a fence, but the tracker doesn't see that. And so it's not very good at estimating this kind of nonlinear motion. And this is a serious limitation in some cases. Maybe a similar analogy is if you think about the rat in a maze. When the rat hits a wall, it's going to have to turn left because it can't go forward anymore. But the tracker doesn't really have access to that information. It just sees where the mouse was before, and so it tries to learn and predict something based on that. So this is kind of a limitation. And building upon these two intuitions, we propose TAG, which stands for tracking at any granularity. And this is a work that's currently under review, so it should drop on archive one of these days, but the paper is up on GitHub. I'll have the link later. And this work is led by Adam Harley from Stanford. It's a collaboration between TRI, CMU, and Stanford. And this slide basically shows some of the cool results of the method. Red is the estimate, and green is the ground truth. It works on wide variety of domains, zero shot, and I'll go into some of the technical details, but keep things at a high level. Basically, we think of TAG as a foundation model for tracking, or more generally for understanding motion, because it unifies a bunch of different paradigms into one umbrella. And the key idea is basically that we treat all targets as boxes with optional masks. And we see here input videos and the corresponding ground truth next to them. And basically, the way it works is, at its core, TAG is just a massive transformer. So for this method, we went with a tried and tested recipe of deep learning, which is we simplify the architecture, we operate directly on the pixels, which we expect to solve some of the issues that I mentioned. The model then outputs 5 different types of predictions, and we supervise whichever one we have ground truth for. And then the second ingredient of the tried and tested recipe is, of course, data, lots of data, and Adam has led a valiant effort to collect basically all the tracking data sets that he could find, so we could train on them. And the image on the right basically shows the list of these data sets. The total comes to somewhere around 24 million frames. with different kinds of labels as we show over there. And so we find that tag learns to estimate uncertainty in a very nice and sensible way. So you see on the bottom, the uncertainty of the key points flares up when the key points get occluded, which is very nice to see. We also find that tag learns accurate nonlinear motion during occlusions. As we see the key points on the robot on the left or on the bunny on the right, and the way they move. And basically, to conclude this method, tag is it unifies a few different tracking paradigms, and thanks to its flexibility and the fact that we train on this massive amount of data, it gets us one step closer to what we want, which is this system where you can just click on something, you can or draw a box around something, and then it just works and it tracks what you want. Or in other words, it's a foundation model for understanding motion. And this video should play. These are some more results of the method and what we track in different situations. So this is all thanks to Adam and finding all these data sets and putting them together. All right, so the code should be available very soon at that link. And the paper is currently under review, but it's going to be available on the website. All right, so that wraps up part 2. Next, I'm going to talk about this idea of object-centric representations. And first, I want to talk about representing objects with 3D neural networks. And the way we think about this in the work that we've done is we start from a set of meshes, like you see over here, in this case, a set of cars. And what we want is we want to represent each one of these shapes with a vector which lives in a high-dimensional space. And we want this space to promote some kind of interesting or useful property like smoothness or compression or reusability and so on. And here's an example of such a latent space, courtesy of Sergei Zakharov, who is a research scientist in the vision team at TRI and in this room. And basically what happens here is there's a red dot that moves across this latent space, which is represented as a sphere. And whenever it reaches one of the points on the sphere, it gets decoded into the corresponding shape. And you see we get nice smoothness, and everything is projected onto this sphere. And here's a second example from another paper from a couple of years ago, Chapeau, where we applied a similar idea to indoor objects, and we also modeled colors. And so we applied these learned latent object spaces to a few different applications. So we looked at auto labeling in outdoor environments, as shown on the left. We also looked at auto labeling in indoor environments, as in the bottom center over there, where we basically find and reconstruct novel shapes. And in both of these cases, the way this works is we make an initial guess about what's in the scene. We then compare the guess with what we observe, so what's in the image or the depth map if we have it, and then we iterate until we find something that best matches the image. And so this process is called analysis by synthesis. It's similar to a cognitive process in the brain, and it resembles the way the brain perceives and understands speech and language. Finally, we also look at scene reconstruction. So unlike monodepth and predicting 3D structure, here we also predict the occluded, the invisible parts of objects, because these object spaces encode complete shapes. So we can reconstruct what's not visible as well. And so despite these many downstream applications, one challenge remains, or many challenges remain, but one in particular that we looked at is how to obtain an expressive latent space where we can efficiently and accurately encode lots of different shapes of lots of different classes. And the state-of-the-art methods in this field basically offer an interesting trade-off where you can model one shape extremely accurately, or you can model many different shapes not so well. And so this is something that we looked at, and in our paper, ROAD, that stands for Recursive Object Autodecoder, we tried to address these limitations and we propose a differentiable lightweight network that stores multiple shapes and then recovers high fidelity geometry in real time. And what we see on the slide are a bunch of shapes which we can encode with the same network, and then we can decode them as well. And we have very, very high accuracy in terms of the geometry that's stored. And the key to our approach is the fact that this representation is recursive by design, and it allows us to efficiently and accurately encode large data sets of complex shapes. And the way ROAD works is we learn hierarchically structured latent space, and we use an octave representation which we traverse iteratively, going from a coarse level to a finer and finer level. And so each shape in this work is parameterized by a single latent vector, which denotes the root node of an octree. And what we do is then we traverse this octree recursively up until we reach a predefined level of detail. And what I show over here is how this works in 2 dimensions, where we use occupancy prediction to prune unoccupied cells, and then we continue expanding the occupied cells until we reach where we want to get. And then we extract the shape. And similarly, this is how it works in 3D, where we basically keep iterating through this octree, and we use the same network at all the levels. So all of the latents that are stored in the octree get projected into the same latent space. And here we see this expansion or traversal of the octree, and the fact that the encoded shape gets finer and finer in terms of the geometry captured. So some of the nice properties of ROAD is we managed to achieve 99% compression compared to the input shapes. And at the same time, we also managed to achieve very high reconstruction accuracy, and this is thanks to the fact that the network is basically recursive and is designed to be efficient in its implementation and reuse geometric primitives. So what we show in this GIF is basically iterating through a bunch of shapes. Each one starts on a latent vector, and then we keep recursively expanding the octree, and we get to finally the shape that's encoded. We also did an analysis of what happens in this latent space. So like I mentioned, each shape is parameterized by a single vector, but then each part of the shape as we traverse the octree is similarly parameterized by a latent vector. And we projected all of them in the same latent space, and we tried to see what the configuration looks like, and it turns out that the network learns to reuse geometry at different scales. As you go from coarse to fine, the geometries become represent smaller and smaller parts of objects, and the network learns to use them interchangeably for different shapes. And that's what leads to this very high degree of compression. There were a couple of limitations here. We basically only encoded SDF signals, and we used a discrete structure. We used an octree, which meant that we couldn't encode continuous signals, which is something that we would want to do, particularly if we want to encode something that's represented as a field or a radiance field in particular. And so, of course, these are the limitations we address in our follow-up work, and this is called REFINE. It stands for Recursive Field Networks. What we want to do here is represent many shapes, again in a lightweight model, and we want to represent them with high accuracy. And unlike ROAD, what we want to be able to do here is represent multiple signals continuously, so not just SDFs, and we want to be able to capture colors as well. And this paper is just freshly released on arXiv and is going to be presented in SIGGRAPH, I think in a few weeks. So how does REFINE work? I'll go to a nice GIF that shows the method. Like ROAD, we start from a root latent, and then we pass it to a recursive network, which keeps expanding this octree until a particular level of detail. And then, unlike ROAD, we now support continuous trilinear interpolation. So we take latents from 3 different levels, we fuse them, and then we pass these to 2 different networks that decode them into the quantities that we want to represent. So in this case, geometry as SDF and color. So it sounds easy, trilinear interpolation in Fusion, but actually, in this case, the devil is in the details and keeping track of all of these free and empty cells in this octree data structure, and being able to do this in a bug-free way is actually quite tricky. And so once we interpolate a latent, we can decode it to any signal as you saw. on this slide. And so with Refine, we can basically represent entire data sets, this case with colors as well. And we think of Refine as a foundation model for 3D shape representation. And we are going to release multiple models that encode various commonly used data sets. And we think that we are going to start in the future from a model like this and use it to extract the shapes as opposed to downloading the data sets, because the quality of reconstruction is very, very high. And in particular, we recently trained Refine on Observer's LD split, which is 10,000 objects. And the size of the network was 290 megabytes compared to the size of the dataset, which is 360 gigabytes, I think, including the textures and everything. So that's quite a significant reduction in terms of space. In this case, the reconstruction accuracy isn't as high as in the other datasets because this is much larger, but we're working on that, and we hope that in the future we'll basically be able to, swap out datasets for something like this that encodes all of the shapes, and we can then extract them and use them differentially in pipelines like auto labeling and finding objects and reconstructing them in real scenes. Okay, and very briefly, I'm going to talk about interpretability, which is the fourth chapter of this talk. So we, from the early days of the team, we have treated videos as first-class citizens, and we've learned from them. And one question that we asked ourselves is, what do video transformer models learn? And it turns out that there aren't actually many papers that look at interpretability for transformers or for video transformers in particular. And this is basically what we propose in our paper, VTCD, Understanding Video Transformers via Universal Concept Discovery. And this was led by Matthew Cowell, who is a PhD student at York University and is actually going to be presented as a highlight in this conference. And so a very, very high-level overview of the method is it consists of three different components: concept discovery, concept importance, and concept analysis. So for concept discovery, we basically take a set of videos, we pass them through a video transformer, and we obtain intermediate representations, Z, which we then cluster with slick or simple iterative linear clustering, and we obtain tupelets. We then repeat this process for several videos in dataset, and we obtain a dataset of tupelets. We then cluster these tupelets, and we obtain concepts. Next, what we want to do, given a set of concepts extracted over a data set of videos, is be able to rank these concepts and say which ones are more important with respect to model performance. And so what we do is we perform this concept discovery process for all the heads and all the layers of these transformer models, and we obtain more concepts. And then to calculate their importance, we do Monte Carlo sampling, and we randomly mask multiple heads simultaneously while computing the drop in performance. And after several rounds of masking, the final concept importance is the averaged drop in performance over all the masks. So there's many technical details in the paper, and we tried a few different ways of computing the importance. It was quite difficult to disable concepts that were in particular heads and actually see a correlation with respect to performance. This finally worked quite well for us. And so at the end of this step, we were able to correlate concepts with model performance and say, if we remove this particular concept, this much performance drops. And we looked at a few different models that I'll talk about in a second. So using these concepts, we looked at a few different transformer models, and we tried to figure out what are the most important concepts and what do they do. And so we looked at the segmentation TCAL model, which is trained to track occluded objects on the Kubrick dataset. And the most important concept is found in layer 5. It tracks the target objects as well as objects with similar appearance. And so this suggests that the model learns to solve the disambiguation problem by first identifying possible distractors that are similar to the target object that we want to track. The second most important concept for this model was in layer 9, and it tracks the target object throughout the video. We also looked at the most important concept for the supervised video MAE model, trained for action recognition on something V2 for the task of dropping something into something else. And so the most important concept was at layer 11, it tracks the object being dropped until the drop occurs, after which it tracks the container. And the second most important concept was found at layer 8, and it captures the container without the object. Finally, the third most important concept was similar across these two models. It is temporally invariant, which suggests that positional information processing occurs in the early layers of both of these models. And so we found it interesting that these models that are sort of quite different in the way they're trained share some concepts, and this led us to ask the question, are there more concepts which are shared by these models and indeed more video transformer models? And are there concepts which are universal across similar models? And we were inspired by this Rosetta Neurons paper, and we tried to discover what's called Rosetta concepts. And the way this works is we looked at 4 different models: the segmentation model I mentioned, action recognition, self-supervised, and video language. And we identified these Rosetta concepts by looking at the IOU of the tubelets for a given concept. And if this IOU is above a certain delta threshold, then we consider this concept to be universal across all 4 models. And we also looked at subsets. And so, interestingly, we found quite a few similar or universal concepts. Here's one that's shared by all models. It captures rolling objects. And we found quite a few others. So in the early layers, we found spatially and temporally invariant position concepts. In the middle layers, we found object-centric representations that capture rolling objects and hands. And in the deeper layers, we found spatial-temporal object-centric representations that capture objects or containers before dropping objects. So it was very interesting to see that these kind of object-centric representations emerge and are shared by all of these models, despite all of them being trained, or none of them really being trained for this particular type of signal. Okay, and so to find more information about this paper, you can go to the website or the archive link, or come to our poster later during the conference. All right, so that comes to the end of the talk, and we basically talked about 4 different key properties of these visual representations. We looked at 3D structure, we looked at understanding motion, we looked at object-centricness of these representations, and we talked about interpretability. And in particular, I talked about 4 different methods that aim to be zero-shot and work across multiple domains and achieve their generality in the way foundation models should. So zero depth for zero-shot metric depth, tag for tracking anything in any domain, refine for modeling 3D shapes, and then VDCD for understanding these video transformers. Finally, I want to take a second to thank many of my collaborators and to conclude with questions. Thank you.
Thank you very much. Thank you very much, Arash. Are there any questions from the audience? Please.
Comment about the tag, like this in real time.
I'm not sure about the runtime. I think the model is quite big. I'm not sure about that.
Yes.
Yes. Okay. So, working or
Yeah, that's a good question. Basically, because we use neural fields, we parameterize images as rays, which means if we have the intrinsics, we go from an image which is a set of pixels to a set of rays. And then the camera model doesn't matter anymore. You can have any kind of geometry the model just sees rays, and then those rays get encoded in the latent space, and they can be decoded in any kind of configuration as well. So we can process sparse rays as well, which is actually key to some of the methods where we have sparse supervision. So it does, yeah, it does. That's one of the reasons why we can generalize to new camera configurations. But we do require intrinsic supervision.
Questions at this point?
Well, it's very important that these kind of like object-centric representations come out of large systems, and obviously this is important for intelligence. But the question is more on the side of what are the pathways in the future that we can introduce inductive biases for the models to learn object-centric representations by design. Sure that like I'm not super familiar with that part of the literature, but I think it's
yeah. So I think there are many different ways to like induce this kind of bias. One that we've looked at is this idea of motion. So if you're learning from videos, then you will naturally see things that are static and that are dynamic, and then you can learn how to cluster them just by sort of observing videos. So that's one way in which these kind of representations arise. I do think that these days, trying to learn them from scratch is maybe, not necessary, because you do have methods that work for semantic segmentation and like instance segmentation quite well. So you can get, some kind of an initial estimate of objectness and then use that as a cue. We're looking into that as well. So training at scale, but also combining some of these ideas.
Maybe I have a question for you, Raresh. So you showed some geometric models with also like representation of color, but then this makes the assumption that we have a Lambertian surface, and also for the neural fields, right? It's important to model materials and non-Lambertian effects. So do you have like any intuition how we could go about as a community in that to that end?
Yeah, so I think that is a limitation of some of the methods that we looked at. In the standard NERF formulation, you can take into account the viewpoint, and then you can model some of these things. When we moved to single view rendering for define, and then Delilah, which was a combination, that was one of the things that we couldn't model. So those are extensions that we want to look at. As an aside, there's another work that I didn't mention called PNDR, photorealistic neural domain randomization, where we actually model these the way a scene. So you represent the scene. You look at the geometry of the scene and you represent it with a neural network, and then you use a light source, and you learn how to render the effects that light source casts on the scene based on where it is. And it turned out that we can do this quite well, and we can get photorealistic renderings extremely fast, without having to do, blender rendering and things like that. Yeah, I didn't have time to mention that, but that's one.
Yeah, sure. Thanks a lot. Perhaps we have time for 1-2 final questions, if there is more. Yes, please.
We talked a lot about getting that data from Interpretability. Yeah, what can you do if you already have some incredibly noisy board that then the model?
Yeah, so that's not actually. We did an experiment when we looked at using radar data. So I think we're of the opinion that you should use whatever you have, and then the noisy signal is going to nevertheless give you some kind of supervision, as long as it's we have an idea about the distribution of the noise. I think we can use it to supervise. So depth anything is similar to zero depth, right? It's a zero shot depth estimation method. So you can have synthetic depth, yeah. You can definitely have synthetic depth. So we train on synthetic depth as well.
Okay, let's thank the speaker again.
Thank you.
Thank you. Now we have more parts about the challenge.
Okay, let's start it. Hi everyone, my name is Chong Hao. So I'm gonna host a free branch this year about driving. Basically cover some hashtag that industrial side, maybe interesting, which is autonomous driving. This requires model to reconstruct or predict the high definition map from onboard sensor. This is very important in the industrial side because, as you know, many in the driving system today they rely on a very good HD map to navigate the vehicles. And then we will have another track called driving virtual language. This is more of a research-oriented track, so people might wonder, okay, now we have very good visual language model. What if we put that into autonomous driving scenarios and could it drive ratherly good compared to human driver? Is it possible or not? Yeah, this track is to do a research-oriented for this purpose. And then finally, we have the color challenge. The color challenge is for now it is the only one closed loop simulator that people can do closed loop evaluation of their models. This is very different to the current well-known open loop one. Okay, the open loop one might not give a very concrete or solid ideas of how well your model perform in many corner case scenarios. But while Kala, this year they put a Kala version leaderboard 2. This has many corner case scenarios. Hope later the organizer will introduce it more. Okay, so let's welcome the organizer from Mapless Driving, Hui Jie. He will introduce what about the Mapless Driving law. Thank you.
I will just take it short. And in this chart, we most focus on the data element in the driving scenario. And at the very beginning of this data element, people usually focus on the 2D name. Now the original method is to detect the name line in the perspective view and then use the IPM to project them into the 3D space. But due to the assumption of the background assumption, the error is unreliable. So in 2022, we come up with the first real-world large-scale dataset of 3D lane detection. We make some 3D annotation in the 3D space based on the Rainbow dataset, and many people from the industry have already using this data. But at the same time, we noticed that we might miss some elements on the road, like the road side or the lane topology. So next year in 2023, we come up with the second edition of the OpenLane dataset, the OpenLane V2 dataset. In this dataset, we mostly focus on the topology relationship between the main center line and also between the main center line and the track element. In this dataset, we use main center line instead of the main line because we think that main center line is a more proper representation than the main line. For example, if we have two labeling lanes, the main line in the middle is shared by these two lanes, and then we cannot attach some semantics information to it. And okay, so in the last year's challenge, we also we already have a challenge on the OpenLane V2, the OpenLane topology challenge. In this track, many participants from the industry have already participated in it. And after the challenge, they give us some feedback that the mainline is still very important for the industry users. So in the late last year, we make some update on the OpenLane V2 dataset. We include the mainline in the dataset. The way we do this is to bound some mainline to one single center line. So maybe one center line will have two mainlines on the side. And also we have add some more annotation on the pedestrian crossing and the Java area to make this annotation more close to the HTML. And also we add some SD map to the data set so that people can use this estimate as input to their model to see if the estimate can interview the model performance of it. So in this year's challenge, we use the OpenMV2 update as our topic, and then we also update our matrix that we calculate the average sum, weighted sum of the link segment detection score, and then the area detection score, the traffic element density score, and also the topology score inherit from the OpenMV2. So as for the result, this check is the second most popular check in the challenge. That is surprisingly because we do not anticipate it. I think most of the participants think it is from the industry side. And as for the challenge, this the team from the Longer Technology has won the challenge. This is a company in Hangzhou which is focused on HDMap. So, and unfortunately, they can make it to America, and then they prepare a video on their winning solution. So, I'm happy.
This is the overall model. A traffic elements detector, YALO, a lane topology, LLT, and a lane T topology, LTT. For the lane topology, we use the topo MLP method. Firstly, we pass the centerline coordinates to MLP and add them to the refined query features. Finally, we apply MLP to perform topology classification. For the lane traffic topology, we use the coordinates of centerlines and coordinates categories from traffic element bounding boxes. We train topology model using ground truth data of lane segments and traffic elements, since the feature embedding are not used. By decoupling with the upstream detection model, the training and prediction process of topology becomes more convenient. Due to the complexity of intersections, we use self-attention to facilitate information exchange among elements and obtain relative relationships. There are mainly two types of view transformation: forward projection and backward projection. Lift splat shoot, LSS, takes advantage of the depth distribution to model the uncertainty of each pixel's depth. But the drawbacks of forward projection is discrete and sparse BEV representation. BEV former projects 3D points back onto 2D images. As a backward projection, one limitation of BEV former is false correlation between 3D and 2D space due to occlusion. To address these issues, we introduce a symmetric view transformation. The depth map of each camera is generated from synchronized LiDAR point cloud. The LSS utilizes depth supervision only at the training phase. Given the SD map of the scene, we evenly sample along each of the polylanes for a fixed number of points. With sinusoidal embedding, BEV former apply cross-attention between the SD map feature representation with features from vision inputs on each encoder layer. In order to fuse BEV representations, we use the channel attention-based fusion module. Here are stacking strategy and streaming strategy, which are same as stream map net summary. The streaming strategy facilitates longer temporal association, as the propagated hidden states encode all historical information, but a temporal fuser such as conv-GRU may still face the problem of forgetting. The stacking strategy may integrate features from specific previous frames, offering flexibility in fusion of long-range information. The computational cost is linearly related to the number of fused frames. We propose a novel hierarchical temporal fusion, HTF. The hierarchical temporal fusion fully leverages local fusion capability of streaming strategy and long-range fusion capability of stacking strategy, and it minimizes memory and latency costs compared to the stacking strategy. Here we present two variants of HTF, streaming strategy and streaming stacking strategy, as shown in figure. For streaming stacking strategy, we random select in frames from the latest and previous frames for the stacking mode layer during the training phase, and select n frames by a certain distance strides during testing phase. In order to demonstrate the effectiveness of long-range stacking for streaming stacking strategy in figure, The stacking previous frame interval parameter is set to 2. Stacking strategy only fuses one previous frame in this figure, and actually it may fuse more than one frame. As shown in table, streaming strategy and streaming stacking strategy are adept at both short range and long range without linear computational cost. Inspired by MashMap, we simplified the PET crossing by for corners. Then we unified the for corners into the MapTR form of endpoints. The main difference is that MapTR uses 20 evenly sampled points, MashMap uses 4 points, and we use 6 points evenly sampled on each edge, as shown in figure. Our PET crossing representation keeps for corners as key points, which are essential shape priors. What's more, the permutations of PET crossing are simpler than MapTR. Compared to MapTR's 40 equivalent permutations of 120 points polygon, LGMap only requires 8. Instead of point-wise permutations, we only use corner-wise permutations. Lastly, preserving corners is beneficial for instance query embedding. We examine the efficacy of SVT component through ablation studies, utilizing the OpenLane V2 dataset. Starting with BEV former and LSS as baseline, the best score is 40.36% on the validation set, as shown in table. Compared to the best baseline, the integration of BEV former and LSS increased 0.5% MAP after adding image data augmentation and BEV data augmentation. The model performance has improved to 43.75%. We build a single-frame baseline model by training 72 epochs with raised net 50 checkpoints, and then all experiments fine-tune the baseline model by 12 epochs. We use single-frame mode to fine-tune the baseline model. Model can reach a score of 52.93% MAP, as shown in Table 2. For the streaming strategy, we use one conv-GRU as dense fusion encoder. It has a performance improvement of 3.7%. And for the streaming strategy, 2 layers of conv-GRU are used instead of 1. Unfortunately, the performance increase only 0.56% compared to single frame. For the streaming stacking mode, we select for frames out of latest 10 frames for the layer of stacking mode during training phase, and a certain distance strides of 5, 10, 15, 20 meters during testing phase. The performance reaches 57.13% MAP. We use the hierarchical attention-based decoder same as MapTR as baseline. The model performance reaches score of 33.6% DETA, as shown in table. Then we change the decoder to instance attention. The model performance increased 0.45%. Finally, we utilize PET crossing resampling to improve the performance to 35.42%. YALO V8 with data augmentation can reach a score of 79.42% on DETL, as shown in table. Applying resampling has a performance improvement of 0.64%. TTA further improves 1% score. We utilize pseudo label to improve the performance to 81.81%. Finally, the model ensemble of YALO V8 and YALO V9 improved the performance to 82.4%. We trained 3 versions of models using different backbones, VIT, InterImage XL, with different input image resolution scales, 0.5, 0.75, 1. During the ensemble process, we utilize an ensemble strategy that incorporating predictions with low similarity. Initially, the models are sorted by their evaluation scores. The best model is the base model, and the other 2 models are subsequently integrated as proposal models. From the table, it can be seen that the more models ensemble, the more remarkable performance improved. In this work, we rethink the pipeline of 2D, 3D elements detection and topology reasoning of mapeless driving. Firstly, we employ a symmetric view transformation, SVT, to combine forward projection and backward projection to form complementary advantages. Secondly, we introduce the hierarchical temporal fusion, HTF, to integrate temporal features from local to global stably. Moreover, we improve PET crossing representation by a novel resampling method. Finally, LGMap is the first place solution on the mapeless driving track, which achieves 0.66 Uniscore.
Okay, thanks for their thanks for their talk on their methods. I won't say there are many of the tricks listed here are novel or so, but these tricks are really useful when you want to improve your model and you get better score. This is very useful in this stage.
In this video, we introduce.
Okay, then here I'm going to introduce
about driving with language tracks. So this is more research-oriented one. Okay, let's start it. So we start with a very simple concept about end-to-end driving with language. So first of all, so what is end-to-end driving? So people now think that there are three components that is really important in the end-to-end driving system, which is the perception, prediction, and planning. Perception requires the model to answer what are the wrong, basically object detection of the surrounding environment. Then when it goes to the prediction stage, it will tell us how will the other vehicle or other pedestrian go in the future. So it's more like a future prediction task. Then based on these two tasks, we will tackle the final task, which is planning. It is more of the ego vehicle planning than where should I go. Now this is a very simple concept in the end-to-end driving, but we have an answer on this. Like if we have a visual question answer data for each stage, how can a vision language model drive under this context and have better performance or on-par performance compared to previously conventional driving systems? So why, before asking how to do it, let me ask why do we want to do that? Because intuitively, vision language model, they are retraining on an internet scale data, having more explainability and generalization. These are the motivation, but I think this motivation is really important, but more important is how can we make this happen? So so then we have a human label data set on all the visual VQA data in the driving scenario. This is an example of what the data looks like. So it basically interpret the idea of perception, prediction, and planning with some human label question and answer in these scenarios. And we have a very strict data labeling pipeline to ensure that each scenarios and each vision QA pairs are following the main idea of the driving of the human driver. Then it follows the human driver to some extent. And we both work on this both on the nuisance and Carla, which are two prevalent data sets in the driving community. And actually, the driving with language task didn't come from nowhere. Actually, from when we date back into 2018 or 2019, there are some data sets working on it. But as you know, after ChatGPT released their work, there are so many works working on this, and people are buying that, okay, we put vision language model in it, and we will have some potential to do better reasoning or better logical thinking in the driving scenarios. And there's some stats about this. Seems like this track is the most attractive one in the worldwide this year. So we have 152 teams ranging from academia to industrial, and we have a total nearly 1,000 submissions. And interest that didn't come from academic only. There's many industrial friends also interested in this track as well. So like NVIDIA, AMD, Tencent, and so on. And here's the leaderboard. I'm a screen you can see on the website. And this is the most important part, I think, about this challenge. It actually tells us about two insights about what will be the future of driving with language. The first one is how to align humans' preference and the VLMs pick up on the important objects. We see that there's a super misalignment on these two things that we actually ask the human driver to annotate many important objects in the scenarios, but vision language model usually has a different understanding on that. So how to align these two things is very important if we want to really adapt the vision language model in a driving system. So some possible way to do this might be we could strong alignment or test time adaptation, which is very prevailing these days. And the second thing is that, okay, how do we explore the visual reasoning with the current vision language model? So as you know that for now, vision language model doesn't have a really in-context learning. The in-context learning part ideally comes from the language model itself, but it didn't have to interview with the vision part. So how to do that in the driving system? This is first of all, this is very important because you need to do the reasoning between the perception, prediction, and planning part. But how to do that, we still see a very clear roadmap to this. And also about some limitation of the current work, like the vision language model couldn't handle complex sensor configure like LiDAR, MIU, and so on. And also we will want to do this in a closed loop manner to
get more solid conclusion. And then the final reason about final point of the vision language model is the runtime friendly. And let's welcome the first place of the driving with language track from Nanjing University. Here, Zhixi will give us a talk about how their methods reached the first place. Let's welcome.
Okay, hello, I'm Zhiqi. Today I will introduce our champion solution. I'm on behalf of Jiaha and Tonglu. Firstly, I will briefly introduce the dataset DriveLM. You can see that DriveLM is a typically weekly type task, and it evaluates the model's capability in perception, planning, and prediction for driving scenarios. There are 4 types of quotients on this data set. We can see that different type of quotient, they have different evaluation metrics. It's worth noting that DriveLM represents the object with its center point. Actually, we are not satisfied with this representation for the following 2 reasons. Firstly, the point representation is not more accurate than bounding box representation. And the second reason is that existing VLMs like Lava or InterVL, they use the bounding box representation. If we want to increase their perception capability, so we better to use bounding box representation rather than the point representation. So in this solution, we employ a simple strategy with the segment anything. We use a point as a point form to get the corresponding masks and then the bounding box. This works well for the most cases, but it may fail in some cases like traffic site. For our base model, we use InternVL. InternVL consists of LM, InternLM V2 20 billion, and the vision encoder InternVIT 6 billion. And the connector is MLP. To support high resolution image input, InternVL employs image division strategy. It splits the high resolution image into the many smaller image. So we can see the performance of InternVL in the commonly used benchmarks. InternVL rank first in typically used benchmarks such as MMB or MassWestern. So we can see that InternVL is one of the most powerful open source VLM, and we choose this base model. For this DriveLM dataset, there are several adaptations. Firstly, nuisance has multiple views, but InternVL only support training with one image. So we simply combine these different views into one image, and we also add corresponding text on this image. We also should resize this image to 448 times 896 so that one view will be split into 2 sub-images, so while no information broken. So with this simple strategy, we can tighten InternVL on this DriveLM dataset. We also indicate the layout in our system prompt. We tell this InternVL model it will be autonomous driving task specific. For our training setting, we use a 4-parameter fine-tuning strategy and train the model with 1 epoch, and the visual token is around 3,000. We also use a deep seed 0.03 strategy. So after that, we can directly obtain a very impressive performance. For V1, we only use 10% of data. For V2, we use the full training data. We can see that with V2, we achieve a score of 0.6, which ranks first. We found an interesting thing is that in this challenge, it used GPT as a referee to evaluate the similarity between the predicted natural language and the GT language. This is their code. It's very simple to understand. So we found an interesting thing is that if our predict answer is, we can play GPT by changing our predict answer. Like if I set my answer to be, my answer is same with GT, both GPT's 3.5, GPT-4, it will directly give me a 100 score. For GPT-4, it's a little bit smarter. It may give a score like 0, 41, or 28. So I think this using GPT as a referee maybe should be reconsidered in the following competition. So that's all. Thank you.
Thanks for Zhixi's talk. Then we have a second place talk from Team NVIDIA presented by Zhiding. So he will introduce what their method is about. Wait a second. Okay, let's welcome Zhiding from NVIDIA to introduce driving with multimodal large language model.
Okay, thanks for the introduction and apologize for my broken voice due to the cold. So yeah, I'm from NVIDIA. My name is Zhiding, and we are presenting the second place solution of the driving with language challenge. Yeah, so here's a brief overview of the challenge. So in this challenge, there are mainly four types of questions. So important objects, for example, decision making, motion prediction, and grounding. So the reason why we are interested in participating in this challenge, besides what Chonghao has mentioned, internally we found that we could use language models for a lot of very interesting applications for AV. For example, we can do offline data auto labeling. We could also do high-level decision making as an auxiliary information for the planner. We could explain our planning decision as a confidence view. And finally, we could also do like planning-oriented data curation and retrieval. So these are only a few applications, and there are many more. I want to briefly introduce two works from NVIDIA on multimodal LM, and our challenge is pretty much, our challenge solution is pretty much built on top of these two works. One is called Eagle. It is a 2D multimodal LM with state-of-the-art performance. The second one is OmniDrive. It's actually a multimodal LM that is able to take multi-view camera input, and it's a 3D multimodal LM. So in this case, it's pretty much hello. Okay. Thanks. Okay. So yeah. So multimodal is a 3D multimodal LM. So I want to show some also very interesting cases. I feel these cases are very difficult to be addressed by regular rules. If you write if-else, if you try to write a lot of these cases, there will be many of these in the wild cases that it would take you forever to write rules. So in these cases, LLMs are very good toolkits to handle these cases. For example, choosing which lane to take. And on the right is also a lane merging example. Sometimes your cars need to make these high-level decisions. And the model, our Eagle model is able to make a pretty decent reasoning by looking at the traffic signs and also recognizing there is a left merging sign on the lane and tell you, okay, you should be prepared to merge to the left lane. There are also some more hard cases. For example, when you have a plane on the road, which you have never seen, or you are in a you are in a parking lot where it's highly unstructured and it's not like a regular urban driving scenario. We also show an example of OmniDrive where you can like drive, you can give the reasoning, joint planning and reasoning, while at the same time reason why are you making such a decision. So this is one example where it sees the pedestrian and it's able to say, okay, I need to stop. This is another example. It's following the car, and it knows, okay, it's you should not overtake the front pickup, the truck, delivery truck, because it's dangerous. Okay, so so our challenge solution is built on top of these two works, but with some modifications. So we found we will share some of these tricks, and we found them useful. So as you can see in this figure, so we incorporated temporal information by reading multiple frames. We also incorporated ego pose as pose token to the language model. And finally, we also leverage detection models, 2D detectors as specialist models, and we can input their detection results as tokens, also as part of the tokens into the language model. So overall, here's how we started from the baseline with a 53 score, and we added temporal information. This will bring our score to about 54, and then ego pose. And then we use Llama 3 AB. We actually didn't use a very huge language model here. If we use a bigger language model, for example, E34B, possibly we could get a higher GPT score. Use a 2D SFT web data from the that's a SFT data used by the Ego project. And also we found that a lot of the driving scenarios are very simple, straightforward driving. So if we try to balance the data better and try to read more about the corner or difficult cases, it will improve accuracy greatly. Finally, we add a 2D object detector, and it can further boost the performance a lot. Okay, so I think that's all for the presentation. Thank you.
Okay, thanks for Jading's work. So next we will, since the Kara group couldn't come to our event, so they prepare a video as well to introduce the Kara challenge.
Hello, my name is Matt. I'm the technical writer for the Carla Simulator development team. And I'm delighted to welcome you all to the workshop for the Carla Autonomous Driving Challenge 2024, hosted as part of the Autonomous Grand Challenge at CVPR 2024. We're very grateful for the excellent participation in the challenge and your attendance of the workshop as well. We'd like to express our appreciation as well to our sponsors for their ongoing support of the leaderboard challenges, which enables us to host one or more challenges every single year. This challenge has been made possible by the dedicated work of our organizers from within the Carla team itself, as well as Eval AI and our partners and sponsors, Synchrotron. So let's start off with a short introduction to the leaderboard. The aim is to provide an open testbed for evaluating the driving proficiency of autonomous driving agents by challenging them with a common series of routes, driving scenarios, and traffic situations. Each agent's behavior when confronting these challenges is then captured by a series of metrics quantifying driving proficiency in a consistent and repeatable way. Thus, we aim to accelerate progress in the research community through collaboration and competition within the leaderboard. And for this reason, we ensure free access to researchers, engineers, and enthusiasts through an open source distribution model for Carla and the leaderboard itself. The leaderboard works in the following way. AD systems are presented with a set of routes that they have to navigate under varied weather conditions while properly addressing a number of complex traffic situations, like, for example, merging into traffic, moving around obstacles, or emergency braking. We synthesize as many of these traffic situations as possible into a set of short routes. You could think about these routes as being like the most challenging day in your life as a driver. The leaderboard has two challenge modalities, or tracks as we call them. The first is the sensors track, which provides data from a standard simulated AD sensor suite with up to 8 cameras, 2 LiDARs, radar, GNSS, acceleration data, and speed. The second map track also provides privileged information about the road network from the OpenDrive map, placing more emphasis on planning and reducing perception complexity. Once the agent has completed all the routes, the leaderboard then uses a set of metrics to quantify driving proficiency. This includes assigning scores and penalties for the amount of each route completed, infractions such as collisions with other vehicles, pedestrians, the environment, or traffic signal infractions. Driving over cautiously, agents are expected to maintain a minimum speed, and scenarios also have time limits. Agents are also expected to deal with evolving traffic situations, for example, yielding to an emergency vehicle when one approaches. These scores and penalties are then combined into an overall driving score, which is representative of the driving proficiency of the agent. Now let's move on to talk about this year's Carla Autonomous Driving Challenge. We've had excellent participation with over 20 teams approved for the competition, around 280 total submissions, and more than 50,000 virtual kilometers driven by autonomous agents. So it gives me great pleasure to announce the results of the challenge. There were many excellent entries from around the world, with scores far exceeding those of previous years of the competition. The top scores in both tracks were taken by 2 teams, with LLM4AD taking the first place in the sensors track with an impressive score of 6.87, while Tübingen took second place. Tübingen AI then took first place in the map track with an impressive score of 5.56, while LLM4AD came in a close second. Therefore, the honorable runner-up prize is awarded to Tübingen AI for taking first place in the map track and also second place in the sensors track. So congratulations to Tübingen AI for their impressive performance. And finally, to the overall winner, the Outstanding Champion Award is awarded to LLM4AD for taking first place in the sensors track with an impressive score of 6.87, while also ranking second in the map track. And additionally, the LLM4AD team is awarded the Innovation Award for their innovation of using a combination of large language models in their autonomous driving solution. And I'll finish with another thank you to everyone for participating in the competition. Many congratulations to all the teams that competed and especially to the winners. Next, we'll enjoy a presentation from the winning team, LLM4AD, about their impressive solution. Thank you to everyone for attending, and we hope that you enjoy the workshop.
Thanks for their introduction. So let's welcome LLM4AD for their talks on
Hello.
the. Oh, sorry. Okay, here we go.
Yeah, hello. So my name is Katrin. I'm doing a PhD at University of Tübingen, and this work is part of my current internship at WAVE. So yeah, I'm gonna present our winning solution to the Carla challenge, which is Carlava, vision language model for camera-only closed-loop driving. So we heard also in the previous challenge a lot about like language models for driving. So I think there's like quite some hype and interest around that. But I still want to go a bit into like, why do we want to do it? Why do we want to use language models for driving? Why do we want to combine those fields? I think there are quite some open problems still in autonomous driving. And one big thing is like generalization to unseen objects. We have weird things maybe on the street. And we still want to be able to handle those objects. But not only objects, also weird situations like an earthquake, a flooding. I don't know, it's not happening very often, but we still want to be able and make sure that our vehicle is handling those situations and not like randomly crashing into things. Then reasoning, a big thing. So maybe some of you have seen this example of like a man wearing a t-shirt with a stop sign on it. And then there was an autonomous vehicle stopping for this man standing there. So we don't want to have this happening. So the model needs some kind of reasoning ability to reason about, oh, this is a vehicle, a person wearing a shirt and not like a proper stop sign. Then there's like this whole explainability topic. And we still care about performance. So we don't want to have like explainability. We don't want to have the model outputting language, but therefore getting a decreased performance. So we do care about driving performance in the end. And that's also why we try to make a model for the color challenge, which we can test closed loop, which gets a good performance in the end. And then we can use this model to do research and to do more work into the direction of like generalization, reasoning, explainability, and so on. So our entry is basically the basis for everything, everything else. So what did we do? As I mentioned, we have like a VLM baseline for driving on the Color Leaderboard 2.0. And as the organizers already introduced this, I think I don't need to go into too much detail here. So I directly go to our architecture. Our model is based on like roughly the architecture of a VLM, like the Lava VLM, which is like the vision encoder is based on the CLIP VIT. And the problem with like a CLIP VIT is the largest trained model has a resolution of 336 times 336. But we need, like for driving, we need a higher resolution. And that's what also Lava proposes is, okay, we just split our image into multiple patches, and then we encode those patches independently. We concatenate the feature maps afterwards, and then we have, again, like the feature map of the whole image. So this is basically what we are doing. So we have here our front view image. We split it into two parts, and then we encode it. And here also, an additional note, we only use images. We don't use LiDAR or any other modality. So then we have this vision features, and then we have a Llama architecture in our case, which does like the planning part. So we linear project the vision features, and then in addition, like in the middle top, we also encode like our target point so that we know on an intersection, for example, if you want to go left or right, also the ego speed. And then as our output representation, we have the path and we have waypoint. So basically for each waypoint for the path, we give like an input query, and then we encode this waypoints, and have like a loss on that. So we split basically the representation into a path and waypoint. So path is space condition. So every meter we have a waypoint, and we use that for lateral control. And then we have the time condition waypoint. So it's like every 0.2 seconds is one waypoint, and we use that for longitudinal control. Then because we use like the architecture of VLM, what we can do is we can just add language to our language model. So in this case, we just like after we predict our waypoints for driving, we just add like language tokens, which is basically commentary. So it just comments on what the model is currently doing. But that's not all. Like, I think the architecture is a big part, but to get like state-of-the-art performance on Carla, there are also a lot of other steps you need to have a look at, and which are quite important. So I also want to quickly talk about those. So first of all, because it's just a simulator and not like a data set you just get and you can use, you somehow need to collect data. So you need someone driving through the simulator to collect data. And because I don't want to sit there for hours and hours and drive through the simulator, we basically need an algorithm, like an expert algorithm, to drive through the simulator. So we used PDM Lite here. It's part of another project, and it's basically a rule-based privileged expert specifically designed for the Kala Leaderboard 2.0, which can basically solve all these scenarios and all these like edge cases and so on. Then with this expert, we collect a data set in like different towns, different weathers from all these different scenarios. And in total, we collect like 2.9 million samples. For training, we split those samples into different data buckets. So one bucket could be, okay, I stop for a red light. Another bucket could be, okay, I need to heavily steer into one or the other directions and so on. So basically all the buckets contain like some kind of interesting data that we don't need to train too much on like just driving straight, because to be honest, like most of driving is quite boring. So it's just driving straight, not much is happening. So we want to make sure that we train on the interesting data. Then, of course, one big thing is like the pre-training of our model. So we use this clip VIT. So we have some kind of like internet scale vision language pre-training. And here I also have some results. So our model in the end got like the 6.87 driving score on the leaderboard. If we remove the pre-training stage, so we train completely from scratch, we get 0.45 driving score. So here we see how important this pre-training step is. And then we also have an ablation on using a ResNet 34 pre-trained on ImageNet, which was like commonly used on the old leaderboard from most of the state-of-the-art models, which also got like only 2.7 driving score. Then another thing is the metric. So there is some like caveat in the metric that because the routes are so long, so the routes are 10 kilometers long. And for models that are like, I think below 96% solving each scenario, it's better to not solve the long route, basically the whole route, and to stop a bit earlier. So this is something super specific for the Kala challenge and for this metric, but it cared in the end for the end solution. So I thought I still want to talk like very shortly about it. So here we have like the driven meters, so 1.3 kilometers and so on. And you see how this matters for the end score. So this was also something quite important to have a look at in the end for the end score. And then last thing I want to mention, there's also quite some variance on these long routes. So there was also a tiny bit of luck involved to get like a good run. Yeah, but results. I think we saw already the leaderboard. So we got on the sensor track this 6.87, which got us the first place here. But I also want to show some qualitative examples. So this is the model I just presented, which also generates the language. So we have here, for example, this the scenario where we have a construction site in front of us, and then there is oncoming traffic on the other lane. So we basically need to wait for a gap in the traffic and then swerve around this construction site. And our model here says, okay, the ego vehicle is waiting for a gap in the traffic before changing lanes to the lane with oncoming traffic to go around the construction site, which is in this case correct because there is this vehicle coming. And I also have it as a video. It might be a bit fast. That's why I showed first the image. Yeah, so we want to go around the construction site. We're waiting for the gap. And then when the gap is large enough, it says the gap is large enough, so we can basically change lanes. Yeah. And this also works for like pedestrians and so on. So yeah, if you want to have a look, whoops. Yeah, first, also like thanks for the whole team who was involved in this work. And yeah, if you want to see more qualitative examples, we have like a video on YouTube, so you can just have a look there. And also for more like technical details, you can have a look at the tech report. So yeah, thanks for the attention.
Great. So there was also a question on Zoom for this talk, I think. So maybe Catherine, you can take it offline. And then we continue.
Sure, thank you. It was a good approach. So hello everyone. Thank you, Krista, for the introduction. So I'm a research scientist at Valeo, and I'll begin a bit with what is Valeo because it might be unknown to many of you. So Valeo is actually quite a big company working in the automotive industry. It's what's called in the typical jargon is a supplier. So essentially making all sorts of making most of the things that are in the car except the car itself. So these things can range from headlamps, wipers, electric engines to sensors, which is the focus of my talk today. So across the years, Valeo has been present in the ADAS revolution, starting since the early 90s with the first ultrasonics sensors for parking, and then all adding up all sorts of functionalities that we have in the majority of the vehicles on the road nowadays. And we see that as we approach our current days, we ramp up our sensor stack with LiDAR and with all sorts of perception functions that are making our vehicles more and more autonomous. So as I said, currently we provide the sensors, but also the software and the perception solutions for autonomous parking, for safety and for assistant driving and general parking traffic, but with all the things that come around it. So the processing units, the cameras, the next generation sensors, but then the solutions and the validation that with it. So in terms of scale, we make a lot of sensors, as I said. So in the past 30 years, we have produced about 1.5 billion, and in the next 5 years, we're forecasting that there will be a same amount of sensors deployed on all sorts of vehicles. As I said, it's not just for high-end vehicles, it's for all the vehicles that we have on the road. So to give you an idea of the type of sensor that we have, especially for ADAS, so we have the ultrasonics, which are very short range, near field radars and mid range radars, cameras, surround view cameras, which are fisheye, and the long range cameras, which are typically peephole and can be either in the front of the car, but also on the rear, and sometimes on the side. And of course, we have a range of LiDARs, out of which the Scala one is it's so far the only one that has been validated L3 on the European and Japanese roads. So based on these sensors, we foresee different configurations depending on the level of autonomy that we may have. Again, a thing that is specific to a supplier is that it's not always that you solve the entire sensor stack. So a car manufacturer like BMW or like Mercedes or like Ford may select just our cameras and the LiDAR for someone else, and the radar for some other supplier. So we're always modulating a bit the architecture that we have to provide it to our customers. And here we are, just inside the Valeo. So there's this Valeo IT, which is the team that I'm working in. We're about 25 researchers and PhDs, and our scope is our objective is to do research, open research, publishing code and papers. Releasing all the reflections that we have upstream in the future of ADAS. So we have several collaborations with different labs in Europe and institutes. We have 2 offices, one in Paris and then one in Prague. And in terms of topics, well, we're moving to some extent with the community. So topics change across the years, but as main target, we always deal with perceptions, with data efficiency. So perception the camera, LiDAR, multi-camera, radar. We deal with data efficiency, self-supervised learning, annotation efficient learning, active learning, these types of things, but also driving, forecasting, reliability, and explainability of our models. So we can find more info on our website where we have most of our papers released. So coming back to the topic of today of foundation models in the industry. So we look at them as models that we train once and we use several times. I will not remind, I saw that already Sergey reminded a bit the definition that we have of foundation models in Ramasani et al. But essentially it amounts to that, finding a way of training the big model
on a lot of data without much supervision, and then we use it as much as possible. So my background is also a bit in self-supervised learning. So whenever I pick up foundation models, I remember the pipeline from self-supervised learning. And there you usually have two stages. So we have one stage of pre-training. So you pre-train with your network on a prefix task that does not have human labels. So here I'm giving one of the early examples that we have, which is rotation prediction. And this is a paper from my colleague Spiros Vidalis. And it's really simple. It's just to illustrate you need a very simple dumb task for which you can extract automatically the label. You train the network for enough of time on a lot of data. And then in the second stage, you take your network at theta and you fine tune it for whatever task of interest you may have with your label. So in general, today I will be following a lot this type of philosophy of two-stage. And you'll see a bit how we can offer some solutions for the first stage and for the second stage of pre-training. But before going into that, so why would it be a good idea to do self-supervised learning, especially in our case when we are dealing with driving data, urban data. So first, the data is enormous. So in self-supervised learning, we leverage only large amounts of unlabeled data. We saw that scale it matters more and more. So we have ChatGPT and friends showing it us. But also there are some specific cases to driving. Like sometimes annotation is difficult or expensive, and in other cases, like we saw with Rajesh before, for dense depth estimation, it's really difficult to obtain it, to annotate it by a human. So you need again self-supervised learning. And finally, and this is again something specific with people launching things in production, is that training data sets in the world are evolving continuously. To show a bit my point, so here it's the evolution of men's fashion from the 80s to the 80s in general. So we can see that the data distribution shifts over time. So there's different fashion trends, different colors. So it's impossible to annotate at all times in one them, but there's a change in the world to go back to the dashboard to annotate even more data. So to bring some examples from what we have in Valo, so we see a bit of a similar pattern. Right? So we are doing cameras since 30 years now, and at every new generation, we essentially almost double the number of pixels, and we have a new sensor. So what do? We have a new contract, a new company. We do acquisitions again. We have to label again. So these sensor specs are changing all the time. Same for lidar, same for radar, and same for all the sensors as we are progressing. And to prove you the point with something more specific, so I here have a map of the evolution of headlamps. So this might not be obvious. So actually the headlamps, there was quite a bit of revolution and they're changing also continuously. So we had regular car lamps before, then we moved to halogens and to xenons, and then with LED, and now we have a laser light. So these are getting increasingly sharper, but actually they generate different data distributions. So here I'm comparing halogen versus LED. So you can see that it gives a different distribution of the images that I have. And then again, I have to annotate again, or to take into consideration that there are cars with these types of headlamps. So, and another thing of why self-supervised learning would be a good idea is that now in the past years, in the advent of different foundation models, be it just simple vision, but also VLMs, visual language models, and even LLMs, we see a lot of use cases for the second stage that appear. So it's not just fine-tuning on some labels. We can do actually a lot of things. On few levels, we can do actually a lot of things with our pre-trained models. So one, in this case here in RangeVid, it's a method for LiDAR perception. Since it's a transformer, we pre-trained the transformer for images, and we use exactly the same architecture for LiDAR. We just adjusted the input and the output, and it works pretty well, and it improves performance against comparing from scratch by leveraging just the information from images. We can use these models for unsupervised segmentation. So here we learn to discover pedestrians, cars, all these classes, thanks to the help of LiDAR. And so by having just the input, the image as the input, here we use Dino features for active learning on point clouds. So we have pairs of images and LiDARs, and we can project the LiDARs into the image space, extract their Dino features, and then find the most relevant ones that I want to label. And we can see that in the very low data regime, our method is in red. With 1% of the label points, this leads to dramatic improvements compared to the typical active learning strategies force sets, entropy, and all sorts of uncertainty. And the last two, I'll be covering them into more detail, but they amount to ways of distilling one model into the other, one model from one modality into another with quite good results. So what I propose as vision and what we see in terms of how to approach things. So you saw the North Star that Alex made this morning about embodied and end-to-end driving. And I adhere to that. I concur to that. But by seeing a bit what happens in the whole industry and the amount of clients and the architectures and the solutions that we have, that each client has a certain setup, a certain chip, a certain constraints involved. So it's very heterogeneous. The way we see it is that, well, we want a modular pre-training. So we want to pre-train our image encoder in a self-supervised manner that it has some sense of specific data and some specific pairs of data. And then if you want to do bird eye view, we pre-train also this bird eye view projector. Similarly for the LiDAR and for other sensors, we can find ways to pre-train them on large amounts of data. And then when they're ready, we can bundle them together and continue training towards an embodied or an end-to-end pipeline to address different tasks that might be downstreams in the surround of the vehicles, be it forecasting or different perception modules. So in the talk today, I will do a focus on these three areas, and I will start with the image encoder. So as I said before, in foundation model, we want one model trained for a long time to be used for all. So in the language, sorry. So in the field of the imaging or self-supervised learning for images, so our team, well, there's so much activity there in finding different strategies for self-supervised training of image encoders, by using contrastive learning, by using feature reconstructions, by using dynos, so by math encoders. So there's a lot. We have worked as well on that, and the focus was always not necessarily to train on ImageNet and to have good performances on ImageNet, but also to see, having a mindset, a bias to a prior towards having good performances downstream on complex tasks like detection and semantic segmentation, or to enable few-shot adaptation. The thing is that this did work really well on ImageNet because it's balanced, it's a nice data set, so we pretend to do self-supervised learning on a labeled data set, but this is a very curated data set. So when we go to driving scenes, so I'm showing side by side some images, randomly sampled or almost randomly from ImageNet and on the right hand side for BDD 100K. So you can see there's some starkly differences. In ImageNet, you always have an object is centered. Usually, on streets, you have sometimes an empty street, a few cars, a lot of empty space. Let's move on. Again, some objects of interest here. Well, we have again some road, a few cars somewhere in the back. And again, yes, well, now this car is closer, some pedestrians, never one object like we have in the internet, where it's easy to identify that there's a main object dominating the scene, so you can devise differently your self-supervised training strategies, and I can go on and on and get at the point of the difference between the two. So actually, most approaches struggle to pre-train just on driving data compared to ImageNet. So there's some tentatives out there, but in general, I would say it's a bit of a wasteland. There's not so much thing happening there, interesting there on having a self-supervised strategy just for it. Because the data is boring if you compare it to ImageNet. There's not much happening there. So this has been the case for a while. The emergence of these new foundation models like Dyno, V1, V2, and Clip have rechanged a bit the focus of pre-training image encoders. So there's two ways of reusing them right now. So one is to have the pipelines that we have, these teacher-student pipelines that we have in the self-supervised learning, but using as a teacher one of these models. So you don't start from scratch, you start from Dyno, you start from Clip, and then you have your training data, and you are doing a lot better because these models have seen a lot, like really a lot compared to what you see in driving scenes. So in driving scenes, you get a lot of information and that's useful, but you will never get the diversity and the amount of things you can find either on the internet or on other data sources. So we want couple those and to use them together in such a pipeline. Then, if I look at the ways of using the other ways of using these models, we can fine tune them. Now, since they are so big, we don't need to fine tune them completely. We can actually freeze them or just train a subset of the parameters. Since most of them are now vision transformers, we can do what is called visual prompt learning or learning just for adapters to learn just a part of the network to fine tune it for certain classes of interest. And here I'm showing an example from a recent paper from CVPR, where they look at the generalization of semantic segmentation models across different data sets by training just on one. And we see that whatever I'm using a clip or a dynamic V2, in particular dynamic V2 is really strong for such systems. So they are to be used there in the user. So in another axis of the study, so this might be less known. So because you have, well, I think it's in the spotlight, the self-supervised learning on images is quite known. But another thing that we have been studying in the team is self-supervised learning for LiDAR. Essentially, we keep the same setup as before. Stage 1 pre-training, stage 2 on the pre-training on auxiliary task, pre-text task, stage 2 remove this auxiliary task and fine-tune our task of interest. So one of our early works on doing that is called Also. It was published as last CVPR, and there we want to pre-train a LiDAR network by using a supervision surface reconstruction. So we assume that if we are managing to reconstruct the entire scene based on these sparse points on the point cloud, we have some understanding of the scene and the relationship between these points. So I'm not going into much details, but the idea is that while I have a point cloud network, it produces some point level features, and then I query from them. I take some representations from them to decide whether a certain location in my scene is occupied or not. And this can be done quite straightforwardly by using the layout of the scene, so we know which space is free, which space is occupied. So whenever we touch on a surface, we ask to reconstruct the neighborhood, and we use this as supervision for our LiDAR network. And when we evaluated we evaluate purposely on few shot regimes to show the benefit of actually learning something with the network. So when we evaluate be it on new scenes or on semantics kitty with 1% of training data, we always see boosts with respect to the previous methods that we're trying to do self-supervised pre-training on for LiDAR data. In particular, we have point contrast, which is the dominant method, but for indoor point clouds, and in-depth contrast, which was one the first one that we did it for outdoor LiDAR, which is sparse and it has its own peculiarities. In other settings, we looked at other approaches to simplify further these pre-training strategies. Because before we had these point contrast methods, contrasted method at the level of the points, where you want to compare one point against all the others in the scene. But they are pretty brittle because you might consider, so you have one point and you consider different augmentations of itself as positives and the other negatives, but the other points might be lying on the same object, so this can introduce some noise. So to deal with that, we have a simplification here. We just squash the points in the bird eye view space. We define a grid, and we consider that all the points belonging to the same bird eye view cell in this grid are positives at different moments in time. So we do scans at different moments in time, and we compare the bird eye view features at the same location after the warping. So we consider these two as positives and the other ones as negatives, and we apply a contrastive learning approach. And this works quite well. It's more stable than the previous approaches in contrastive learning. And similarly, over the board, be 0.1% of the labels, 1% of the labels, 10%, we always see an improvement with respect to previous methods without pre-training or with a different pre-training structure. So with this, I'm concluding the first part of the talk, where I was speaking essentially of single model models, be it for LiDAR, be it for camera. Another thing that we see emerging, and that we have it's a specific of autonomous driving data, is that we have different sensors that come into different sensors of the same type. With a multi-camera setup with different cameras mounted on the vehicle, but also different types like LiDAR, radar, and so forth. So in the next, I will take a highlight on two types of models that allow multimodal training. So the first one is techniques that enable LiDAR to supervise image models. So just to make it easier, so whenever I have here, this is I'm dealing with an image model. So whenever I have the other one with the car and the LiDAR, it's a LiDAR model. Because the visualizations can be quite similar. So the first one is a method that we call POP3D, which was our take on doing 3D occupancy prediction in an open vocabulary manner. So we have as input here just the surround view images, the images from new scenes, and what we want from that is without human supervision to get an occupancy map in the 3D, but also with open vocabulary properties. And why is this interesting? Is because that it allows us in offline mode to do zero-shot semantic occupancy segmentation. So it allows us to discover new classes that we might not have thought in the initial annotation campaign. Because if I want to detect a new class that the client has, then I have to go back to my data and re-annotate. And annotated LiDAR is pretty expensive. And then I can also do retrieval. So since my network is producing 3D features that are open vocabulary like clip, I can query with text query. So here I'm just saying black hatchback, and it identifies in this 3D space the voxels that correspond to this hatchback. I've already mentioned some of the motivations. We have a lot of weird things happening in the world, and it's difficult to come back to our LiDAR to re-annotate it point by point, and it costs a lot. And again, my LiDAR changes, I start over. So how does it work with our method POP3D? So we, as I said, we want to do open vocabulary 3D semantic occupancy prediction. We just have training some unlabeled image LiDAR pairs and the pre-trained image language model, so clip. At inference, we just have the images and the text queries of what we want to find in our 3D scene. So here in an example I have an example of text-driven retrieval. So the pipeline is pretty simple. So for those familiar, we are using we are moving from the camera space to the 3D volume space with something resembling TP deformer. People might be familiar with that. So we go by using the information from the camera extrinsic and intrinsic, we project them into this 3D volume, and we end up with this 3D grid. And then once we are here, for each voxel, we plug in two MLP heads, which need to predict, the G head needs to predict whether the voxel is occupied or not, whether there's a surface there or not. And the H head needs to produce clip features for in this space. And in terms of supervision, how do we do that? We have two losses. So in the occupancy head, it's easy since we have the LiDAR, we can generate, we project the level, we can voxelize the LiDAR space, and with the given granularity of our space, I can decide whether a voxel is occupied or not. It's occupied if it has a LiDAR point in there. It's unoccupied if not. And I have a simple loss for the occupancy. It's typically used in segmentation, the low pass and the cross entropy losses. Going on for the 3D language head, again, it's in a similar approach. We take advantage of a pre-trained visual language model, clip, then the other. We densify those, and we get the features at the last convolutional layer, or at the last layer before the projection into 3D. We project the point clouds into this space, so we have them aligned, and each point will have this corresponding feature. And then my head needs to predict for each voxel, needs to predict the corresponding features at the places where in the image where the point clouds were projected. And doing this without human labels for a decent amount of time. So we train the new scenes. In this case, I think I forgot to mention. So this part here is just for training. Right? So this part here, and I'm not changing my visual language model. Right? I just learn to imitate these visual features. So when we look a bit at the results, we compare with methods that are supervised. So here, this is a benchmark introduced into the Informer, where you generate this volume of semantics but you use the LiDAR information just because you know it's segmented, and you use just it's a tweaking of the LiDAR semantic segmentation benchmark, and you essentially see in which wherever you have a voxel, the point cloud falling in a voxel, you look at the class and look at the prediction of this model in the 3D space, then evaluate it like in the semantic segmentation manner. So starting from a mass clip, this is a model for doing semantic segmentation where we project them in the LiDAR point cloud. So we get like 23% MIU, but this is a bit cheating because we know where to project in the LiDAR. Our method that does not use any LiDAR at runtime, it gets into 0.26. So this is in zero shops, right? So we just give it the text queries that we want to have. And when we compare with methods that have exactly the class level information and they're trained for these classes, we see that we're actually not that far from them. Another interesting finding is that when we look at actual occupancy, it's thank you. Okay, thank you. So another thing that we looked at is on the occupancy. So here we do it in a class agnostic manner, comparing with the supervised method is deciding predicting whether a certain voxel is occupied or not. So interestingly here, we're actually better than the method that was trained in the supervised manner. Like having access to semantics, but was trained to predict exactly the classes and the location. So in purely occupancy, we're better than that. When we go to actually comparing the classes, so this is the MIU, we're lower, but we're in zero shot. Right? So it's not a great performance, but it behaves differently. It performs differently compared to the supervised method. And another task that we looked at is retrieval. So we annotated a small data set of voxels, and there we essentially annotated with some classes, and we did the nearest neighbor classifier, taking a certain voxel, a query voxel, and looking across the data set where these voxels corresponding to this object. With them also the example with the black hatchback, that we have quite a few classes annotated specifically for this task of retrieving the voxel that corresponds to this class in the data set. So some cherry-picked results on what we get. Again, this is what we have as input, just the cameras. We predict this surface in the 3D space, and these are the text queries that we apply in a zero-shot manner on each voxel. And the results look relatively nice. Of course, it's not the supervised thing. It's just the thing that gets you to mine some patterns that are unknown in your data set to retrieve whether you have something of your interest in the data set. And similarly here, we discovered this bus here. So this is another scene from new scene. And you can see that it identifies some voxels belonging to the bus. So again, Clip was trained to see buses, but it was not to be trained to predict features in the 3D space. And in there it recognizes this bus. And same from the retrieval benchmark, the black hatchback has shown it to you before. And I have another interesting one here, stairs. So again, this is not an annotation in new scenes. It gets to fire to identify it to some extent. So here, blue is lower similarity, red is higher similarity with this text query stairs. And another way of using, kind of related to that. So POP3D is to be used mostly for offline, but we come back and revisit the idea of self-supervised pre-training. So this is a work that was the read group that we presented today at the WEB workshop. We want to pre-train a network for bird eye view perception. So here we don't do a 3D volume from the beginning. So we are having the typical bird eye view pipeline, be it L lift slash shoot, simple web, form, or whatever you want, and we add this auxiliary head, which predicts again the occupancy in this volume. So here in the bird eye view space, we have lost the height information, and we recovered here with unsplatting, and then we have a similar approach of attaching a linear head on top of each voxel to predict whether it's occupied or not from the LiDAR. And in this case, we use Dino V2 features. We want to imitate Dino in this space. And then in the second stage, we completely remove this yellow part, and we fine-tune for 1% of the label data. So we can see that this is the ImageNet pre-training in yellow. I'm showing here two architectures, simple web and web format. on vehicle segmentation and map segmentation, and we see that on 1% of the labels, we always get boost with the occupancy, and whenever we add also the dyno, we get even further. And what's interesting is that when we look at these benchmarks like new scenes where you simulate the distribution shift, you actually have you see that across different corruptions, so we jitter. So you have all sort of corruptions like adding fog, adding motion blur in the input images to see how is your model behaving in conditions it has not seen. So we can see that our model in green is better than without the model that does not have that better. So as I said, there's a second model that I wanted to show you today. It's image to LiDAR. So this is related to a paper that we're presenting right now at, in the main session, in the main track at SPPR. So here we are looking at ways of distilling a pre-trained image model into LiDAR, into a LiDAR model. So I want to train my LiDAR model to imitate whatever my foundation model on the image side is predicting on the line images. So previously, the state of the art had a relatively complex approach where you essentially have an image, a point cloud encoder, an image encoder. You do a segmentation of all you do a super pixel segmentation of the points of the pixels in the image space, and you group when you project the points in the image space. You want to group these points together. Pixels about points that fall in the same segment of the image space are considered positive. The others are considered negative. So this was state of the art at the time when we released the paper, but it was a very complex approach. Nothing like it is also our previous one. I'm not bashing that percent. So the state of the art at that time with these types of features, I mean, this in essence it's a very simple setting. Just the architecture ended up more complex, but it's a really easy thing. You want to distill an image model into a LiDAR model, and it works pretty well. However, at the time, when we look at the gap between a fully supervised model on semantic segmentation and all the models that were pre-trained on the same data set but with a linear flow, we have a gap of 33 points. With the method that I will present you in a minute, we managed to narrow this gap to 10 points. I remind you, we pre-trained the network and we just fine-tuned the last layer, linear flow, and we compare with the model that was trained on the entire dataset with full supervision. So we are still not there. We still have 10 points, but we are narrowing the gap. So just to tell you how we tiered apart the original approach that was state of the art at that time. So we simplified dramatically. So this is a paper by my colleague Gilles, where he and the colleagues proposed a dramatic simplification of the pipeline that I've shown you just before. So before we were using 6 cameras as the new scenes and the full LiDAR cloud, the surround view 360. A simple thing that we started with was actually to do 1 camera at once. So this simplifies your data loader. We don't need to load 6 images to have the point cloud in mind, and it reduces quite a bit the memory load. Another simplification that we did, it was this linear head on top of our of the image encoder, and we added here this initially to reduce the dimensionality because we have big ResNets at that time. They have 148 2000 dimensional features for a point cloud is quite a lot. So we had to reduce those with a linear head. The downside is that actually per term we didn't have access to the actual 2D features that were learned by this model. So we removed that, and then we looked a bit at the contrastive loss. It's complicated. You need to keep negatives in mind. You need not to match positives with positives and so forth. So we removed that and we replaced it with a simple cosine linearity loss. So we essentially want to align the features of a point cloud with the features of the pixel in the place where the point cloud falls into the image space. So that's it. And when we look at the impact of all these simplifications, so here we have 2 architectures for point clouds, MinQNet in Waffle Iron. So this is the baseline where we have well, this is the reference of one point memory in time. So we will be looking in relative with respect to that. So as we remove the 2D head, we can see that we get an improvement immediately, right? So we remove this 2D head, while still keeping your contrastive loss. In the next step, we remove the contrastive loss and we do a cosine similarity, and again, the performance improved further, a bit less on MQNet, but quite significant on Multimodal. And finally, you see here, I have the number of camera images. When I remove, for the MQNet, when I remove the number of cameras and use just one view, I gain quite a bit in time and memory, really a lot, while losing a bit of the performance. But I can train for longer if I want to achieve that level of detail. So when we study the influence of these three pillars, we have three pillars that we study based on the modifications that we made. So the choice of in the scale of the 2D network, the scale of the 3D network that we want to train, and also the mix of data. So what we notice is that when the choice of the scale of the network and the 2D network actually are quite important. So we looked at different teacher models. They're all pre-trained on images in a self-supervised manner. So the first one is MAE, then we go with Dino V2, Dino V2 bit base, and Dino V2 large. So as we go to more recent models, sorry for that. Yes, installation. That was related to me. We were here, sorry for that. Well, the idea here is that the bigger the teacher model, the better. So this was not a factor that was studied before. And well, all the findings that we have are pretty simple and ready to use, in fact. So I will not spend too much time on them, but similarly for the scale of the 3D network, so the one that we actually pre-trained, we looked at different sizes. So we look at this waffle iron architecture for which you can control the width between 96 to 768 dimensions. So the green one is trained with the small teacher, a bit S, and the blue one with a bit large. And again, we see very obvious improvements across with bigger scale and bigger features. And then finally, we looked at the impact of the training data set. So what we did, we gathered all the data sets on LiDAR that we have available, new scenes, MTD, semantic kitty, Panda 64 and Panda GT. We made a data set, and we first trained pre-trained on each individual one, and then fine-tuned on the other ones. We can see that when we pre-train and fine-tune on the same data set, it works well, but then when you go on another data set, for example, see like pre-train on new scenes, it works well, but when I fine-tune on semantic kitty, the performance is relatively low with respect to the original data set. But when I pre-train on all these data sets and then fine-tune on a specific data set, we can see improvements quite well. So this generalizes across architectures and settings in our work. So in general, with optimizing these three pillars, we've seen that we got improvements over the board, be it in linear probing, the fine-tuning with 1% of the labels, and using on semantic. I will skip a bit the qualitative results. So just to conclude, so what we notice is that scalable and simple pre-training strategies were long known to help a lot in the mainstream image classification and image-based settings, but we see that they're becoming first-class citizens also in driving data. If we have data outside of the autonomous driving domain, it's really helpful. It can be internet, robotics, whatever. You really want to have this intelligence and this richness of data that you have seen outside of the roads. But if you want to go to generalize to outer distribution and to have robust features, it's not enough to have just the driving data. So if we train on different datasets and camera configurations, we get promising results. So I highlighted here Scalar, which was trained on different LiDAR datasets, but we have another work on trajectory, on motion forecasting, where we assembled all the datasets existing there and trained a foundation model on all this composite data. And again, it improves things, and you will see. And we tested it in the Argoverse 2 end-to-end forecasting challenge. We used both Scalar and Unitraj. So what we did is the approach that I was mentioning before. We had a modular pre-training, so we pre-trained all the modules on trajectory forecasting on Scalar. So in the case of Scalar, actually, we just added the Scalar features without any fine-tuning on this Argoverse data, and it led to a significant improvement of the forecasting properties with respect to the previous works in the one last year. So we were 13 points above the previous methods for forecasting, to stress on the importance of the pre-training, whether your pipeline is end-to-end or not. To give some perspectives, so what we see, and we saw also today, so there's different forms of world models that are taking over right now. There's different tastes with different flavors. According they're all interesting, and they're all paving the path towards the so what we see here, and I appreciate especially you guys for releasing some data sets in the community. So we have the Open Drive YouTube data set, which is 1,700 hours. Right. So all the public data sets that we have so far were like 300 hours. Also, New Plan is a nice data set, but it's just 100 hours. It has calibration, it has LiDAR, it's really nice. While the Open Drive YouTube is 1,700 hours of non-calculated data, but it's really useful. So what we need is a lot more. The Gaia 1 has at least 5,000 hours. And I think they will have even more. And there's really a need to run more open research in this field. It's nice to see the nice models and their performances, but if we cannot touch them, if we cannot collaborate together or work with them towards improving them, it's a bit of a missed opportunity. So we really need to do that. We're doing our part, releasing everything there, what we do, and we hope that others will do. And I think that I forgot to mention is that there will be even more downstream phases, stage 2 that I was showing before here in the new generational foundation model.
Thank you very much, Andrei. Are there any questions from the audience to the speaker? Yes, please.
So already, it's to get back to the slide. So, in contrastive learning, you have a lot of moving variables, like the number of negatives, and something that we did, because in these settings, because it's quite difficult otherwise to scale, is that the negatives are from the same scene. So and you won't often end up by contrasting pixels, points from the same object. It can be the car, or you have points landing on the same car. So since they're in the same scenes, you end up contrasting. Or if you have multiple cars in the scene, you don't have any way of doing that. So this ends up confusing your model, and it also is more unstable and trades for longer. While just aligning one point with itself, you don't care about the others, and it's much simpler. So you don't need to have a bunch of negatives.
So I have a question. So regarding the design, because it's like doing the topic,
Yeah.
it's very common to where like you visit the applications or some concept values all have some dimension of that.
Yeah. So this issue of motion, well, the like feature collapse arrives usually in indeed in methods that do cosine similarity, but it's methods that have a teacher-student architecture, right? So you have but the teacher is an exponential moving average of the student. So you end up predicting the same thing. Why we are not vulnerable to that is that at the input of our teacher, I have images, while at the input, and they are always changing because I have a Dino V2 or I have, so that thing I know it produces all the time good features, and they're not the same across the images. And on the LiDAR part, I train to imitate that, right? So I train to imitate Dino or Clip or whatever. So I don't have this risk of feature collapse. Usually you have this when you give the same input to the two models.
Maybe I have a question. So you showed a lot of nice results with leader point clouds versus images, but we see this dichotomy between the representation spaces for these modalities. And so what is like your take about like the actual space that we need to use for driving scenes for our presentations or for our outputs, for example? You showed also some occupancy results.
That's a good question. So in terms of alignment, we have some experiments on scalar, but we didn't show them here. So actually you can distill even a clip into scalar, into LiDAR, so we get open vocabulary LiDAR features, right? So we have the same things that I was showing you on POP3D. We can use it on the LiDARs to query by text. So you can align these features with sufficient supervision. I think the alignment that we want really depends on the end task. So if you are speaking in bird eye view, then again it's easy. I was showing you the modular pipeline, and then it's really convenient in bird eye view to do a la web fusion to align them, because then it will be helpful for downstream if you do 3D of detection or if you do forecasting. The same actually applies even if you want to train an image encoder. A front cam encoder. So there are some data sets. For example, if I look at the Pandar GT, so Pandar GT, it's a data set that, it's a LiDAR that looks exactly like a front cam. It has a narrow point of view. And actually, even our LiDAR, at Valeo, it's the Scala LiDAR has this type of camera-like look. Yeah. So then you can align them in this space. It could be bird eye view. It could be. So my take is that we can align them quite well. It's helpful if it's in the 3D world in a space that is common for them, but it also depends on what you want to do downstream.
Yeah. Thank you. I think, do we skip the coffee break, or because I think we're a bit behind time? Okay, so then we'll just take like a couple of final questions from the audience, perhaps, to Andre. Otherwise, we can directly move to our next speaker. Okay, so let's thank Andre again. Okay. Okay. So yeah, well, maybe we can have a short break if somebody wants to.
Is there a break?
Yeah, we said that because our next speaker is in the restroom.
Oh,
yeah.
yes. Okay.
Okay.
You have to go.
So,
I'm connected to the Zoom.
yeah, just connect here. Take your time, like you're having a short.
Now. Yeah. Cool. Can I share my camera as well?
Maybe I tell the attendees to try to find a spot because then we'll have again the same issue as during morning.
I think also because the ladies have changed several times.
Oh.
They did not talking about everything.
Yeah, but it was still like less people.
Yeah. Because in other rooms,
They're violating this rule. Okay, I see.
why just ask and
Yeah.
but
Yeah.
but if we not talk about the brand.
Yeah. Let's pretend that it's okay. Okay, so would you like to also comment?
比如说 panel 说这里要清空一下，他们就坐在这旁边，就坐围着这张桌子。OK， 可能对。你把这些拿着呗。但是拿着。对。
Wait, you know Rohan? I know Marco from Boner.
Oh yeah, and you've been using microphone.
Yeah.
This one, can you test it short?
Testing.
You can start with this one, just there, but this might break.
Okay.
Yeah. Let you know if problem. We'll start with this one first.
Yeah.
So I think we're pretty much still. Okay, so yeah. Okay, let's resume. We have two more speakers, and then we'll have finally the panel discussion. So first we start with a talk by Ted Xiao. So Ted is a senior research scientist and on the robotics team at Google DeepMind. He works on problems in scaling robot learning, foundation models, and reinforcement learning. He obtained his Master of Science in Electrical Engineering and Computer Science from UC Berkeley in 2017, and he has focused on machine learning and control theory, particularly in sample-efficient settings. Welcome, Ted. It's very nice to have you with us, and we're all ears for your talk.
Thanks so much. Yeah, really happy to be here. The title of my talk today is What's Missing for Robotics First Foundation Models. And to preface this, I think I really want to emphasize the absolute amount of energy right now that's happening in embodied AI and robotics specifically. Even today at CVPR, I see so many times roboticists, which this is their first CVPR. I think it's the general trend of a lot of converging trends in different fields from language modeling and computer vision and embodied decision making. So I think it's really such an exciting time right now to be working on these problems. But the purpose of my talk today is to really try to paint a picture of what I view as the bleeding edge of modern trends that are ongoing in robotics, and more importantly, ask some provocative questions about how understanding this bleeding edge can point us to the missing pieces and open challenges that are on the path between us and really solving general purpose robotics. The work here that I'll discuss today comes from a great group at Google DeepMind, And the controversial opinions are only my own, especially the wrong ones. To give a brief glance then at today's agenda, I'll first motivate what is a robot foundation model. And I think you've heard today from so many great speakers, so I'll keep this brief. But most importantly, I'd like to focus on a few missing pieces that I hope will paint a path for what are the most important problems to solve before robotics become generally accessible. And finally, I'll save some time for the horizons of how the field might evolve at a meta level. First off, some very brief preliminaries. The modern sense plan act paradigm in robotics as such is a pipeline system, right? You have perception, understanding the world, you have planning, how you synthesize different types of information, especially semantics, human intent, etc. And of course, control and actuation, moving robot to influence the world. And what this has looked like in the modern era, and I use this to broadly, the loosest sense in the last 10 years, is that robotics has been very interdisciplinary, a very full stack effort, where advances in perception, in language, and other domains are quickly adopted and utilized by roboticists to drive progress forward. This usually looks like taking the state-of-the-art bleeding-edge model from CVPR, plugging that in as a perception stack, taking some kind of off-the-shelf great planning system, either symbolic or recently a learned system, and then really focusing on the control part is the last mile. And this has worked pretty well, I think, especially when we were working with like scaling up CNNs or scaling up initial smaller scale planners. But in the age of foundation models, I think some of the lessons that we've really taken to heart as robotics people in the last 10 years may not continue in the next few years. One issue you might think of is that it's great to keep taking these off-the-shelf state-of-the-art models, but of course these are frozen, they're pre-trained, they're not optimized for control, they're not optimized for decision-making. And the same for the language model planners, which again, these days, if you really view emergence as a phenomenon that only exists at scale organically, well, maybe the types of emergent capabilities, intelligence you need for low-level control are not the same ones that you need for internet-scale text modeling. And of course, the second part, which is related to that point, is that the bottlenecks between these modules are very narrow. They're very they're heuristic-driven, they're expert-defined, and they're not expressive enough, perhaps, to encompass the benefits of scale and transfer that we all know and love from foundation modeling. And so how do we tackle these two issues then? Well, maybe we could take some lessons from trends and practices that have worked in foundation modeling. I'm sure all of you guys know this story, but from language modeling and from vision, there's all these separate tasks and data sets and specialties. And the insight of scaling large-scale, internet-scale foundation models is that by treating these problems all as interoperable or homomorphic, is that by breaking down the barriers between the strict definitions of what you call sentiment classification versus what you call summarization, you get a lot of benefits and really great scaling trends. And then in robotics, right, going back to the modern sense-defined fact loop, where we today still have these very big brick walls between these modules. Is there a way we can break them down? And if we can do so, that would be a robotics first foundation model. And again, I think we have some ideas of how to do this, and I'll talk about in today's talk. But I think even beyond that, there's a lot of questions that we don't yet have answers to, which I think will be very exciting to make progress. So why do we even want to do this? Okay, let's say we break down these brick walls, we have a robotics first foundation model. What does that mean? I think there's three missing pieces that are really nice properties that we see in today's language models and vision language models that we, as of today, do not yet see in robotics. One is really positive transfer at immense scales, where you basically can assume by default that positive transfer and scaling will work, as opposed to in robotics. These days, it's more rare than that you see positive transfer in cases where you get negative results. And again, when this happens, you can start making predictive scaling laws about how much you should scale, how much compute, how many tokens you need, and robotics is far from that today. Another one I think that is very close to my heart is steerability and promptability, right? In my opinion, this is what really made me see the light between GPT-2 and GPT-3 eras, where you saw that few-shot learning, where you saw prompt engineering really start to take off at a massive scale. And in robotics, I think we're far from that. And finally, I think scalable evaluation is an aspect where I really enjoy the progress that's been made in foundation modeling, with everything from very realistic, meaningful evaluations to predictive benchmarks that correlate well with how users actually would leverage the capabilities seen in these models. And my claim here is that these properties are not just nice to have, but we actually need them in order to tackle the full unstructured wilderness of the real world. Again, robotics has kind of sped run the scale up from one bin for indiscriminate object picking to one room to one lab building, but to go from here to all the VC-funded humanoid companies and home robot companies and assisting the elderly and playing with your dogs and kids, this is kind of a huge gap, I think, that you don't get by just incremental progress, but by fundamentally transformative paradigm shifts, which can leverage emergence scale generalization. And the hot take here is that I think while we see signs of life today, I think if you froze technology today, you cannot solve robotics. And again, I think there's companies and startups and academics betting on this, of it's just a data problem, it's just engineering. I think there are still fundamental paradigm shifts that are algorithmic or maybe data breakthroughs that are needed until it's going to be tractable to try to go and solve robotics. And let's then jump into the nitty-gritty of these missing pieces then, right? So the first one I mentioned was positive transfer from scaling. And I think, to kind of illustrate what this means, I think we can just point at all of the kind of forerunners in language modeling and VLMs, right? You see these great large-scale internet-scale data sets. You see great, scaling laws and chinchilla optimality. And again, I think this is building off of the fact that passively scraping the internet gets you a lot of great properties that are good for language modeling and vision language modeling. But in robotics, that's not the case, right? So I think in robotics, in order to study how you can get positive transfer, you need to first scale the data. And there's probably two ways, which I'll dive into shortly, is one, maybe you can just make robot data look more like internet data. You can just treat them as the same data source. And the second is maybe your specific robot, there's not enough data, and even with $1 bajillion, you can't get enough. But maybe if you pull together all of the robot data that's been collected across different embodiments, tasks, environments, maybe you have a better shot of seeing some kind of positive transfer and scaling loss. So again, vision language models. This is kind of the golden standard for what we want to model the properties we'd like to see in robotics off of. This is one existence proof of concept of what's worked, and VLMs capture both visual and semantic knowledge of the world. And then you put it side by side here. This is the raw network architecture for a model called RT1 from our team from almost 2.5 years ago, which is kind of like a homebrew GarageBand transformer model that has these components of a perception vision encoder, some kind of like a cross-modal attention, which we use film for, and then transformer blocks to do the bulk of the reasoning, and finally some kind of action token output. Again, these are design choices that were really optimized at our scale on our problems, which were still pretty large scales by academic domains on hundreds and hundreds of robot tasks. But again, if you kind of squint at this, these components start to look like the design decisions that are used in state-of-the-art vision language models, right? And you can kind of just like try to think about how you would fit the kind of design choices we have to make at the small RT1 scale into a large VLM, and you see a lot of properties that are the same. Again, these are discretized tokens. They're very similar, just maybe with some slight output differences and input differences. But maybe you can just use the VLM as a policy. You don't need to iterate at small scales on your homebrew GarageBand policies. You can just leverage the kind of great work and infra and data from vision language modeling. And then the main question becomes, well, how do you align the action domain? How do you align the action manifold? And again, this is what our actions look like. They're kind of robot specific, but they encompass things like positional change and rotations and gripper open close and terminate action types. But that's broadly, going to be specific for a robot, and you can choose to discretize them. But I think the main point is that these look still a little bit different, right, from like the text you find on Wikipedia articles or on image captions on the web. But maybe there's ways you can just make them the same by just turning it into a string, the most naive thing you can do, and see how that works. And that's exactly what we did in this work called RT2. We just converted the tokenized, discretized robot actions into a string, such as this list of 8 integers, and you can just treat that as a caption. So robot action prediction is now just a VQA text. Of course, there's alternatives and that we can think of, such as maybe we use floats, but then there's more tokens and inference latency is a thing. You can use extra IDs or like least use extra tokenization. You can use strings, and I think these are all very compelling choices. But I think the most simple thing to start with is just turning your raw robot actions and just casting it as a string and seeing what happens. And this is what's now called a vision language action model that treats actions as just another modality represented in text. For the backbones, we looked at polyx models, which is a vision language model from Google, as well as PaLMi at the 5v, 12v, and 55v variants. And importantly, we co-fine-tune it. We co-train the robot data at the bottom along with the original VQA data, the internet data that the original VLMs were trained with to start. The robot data is this offline data set that we iterated on for RT1 and many other works. It's a large expert demonstration data set that we've saved offline. And what we see then is that when we train this large VLA model, we start to see some emergent skills. And I use emergent in the sense that these were not specific capabilities, such as OCR or recognizing flags. These are not any concepts that we collected data for in our robot data set, but kind of emerged via positive transfer from whatever semantic concepts were present in the internet scale VLM training, the VLM data. And quantitatively, right, post hoc, we can kind of try to squint and see what kind of these new capabilities are, and we roughly group them into things like symbol understanding, reasoning, or human recognition. And we see that this is indeed positive transfer happening thanks to the VLA paradigm. And again, though, those were kind of like canned evals, right? Maybe you don't necessarily care about if you're a roboticist, whether or not your robot foundation model recognizes Taylor Swift. Maybe you do care about, though, is generalization to distribution shifts like lighting conditions or new objects or new background conditions. And here we see that actually the VLA models, the web scale data, also gives you some of this for free just by treating robotics as the same as internet data. Switching to the second part, though. So we've treated robot data now the same as internet data, but oftentimes maybe that robot data still isn't enough. Would you get any additional bang for your buck by training on all the robot data, even if the robots look different than the one you have in your lab, in your factory? Here we had a cross-institutional collaboration called Open Cross Embodiment, where we pulled together the data sets that were open source from more than 30 robot labs and aggregated together and see whether or not we could get some nice scaling properties by treating all the robot data as the same. And this data set is very, very heterogeneous. We have many different robot morphologies and embodiments. We have many different environments across the world and many different semantic tasks that each of the individual researchers I care about when they collected their original data set. It's different from clock folding to this like cable routing where you have to put a cable very dexterously into this small socket. It's really quite diverse. And with this diverse data set, we studied kind of the scaling properties as two model classes. One is the RT1, the small homemade transformer that we had 35 million parameters, as well as RT2, the full VLA 55 billion parameter VLA scale to see whether or not, treating these different robot action, data sets as just input is some robot images, output are some robot actions represented as strings, what would happen in this case? And here, surprisingly, we actually see signs where the generalist policies, which are trained on all of the robot data, outperforms the specialists, which are optimized for each of their evaluation settings. And in this case, right, it's actually, I think this was to me very shocking because for each of these individual kind of, labs here, each of these logos correspond to a lab. There, generally, I think the best accepted, understanding of roboticists is that if you care about maximizing performance on your specific task, on your robot and your setting, like you should just train on robot data from your robot because adding any other data is going to be, it's just going to your policies will not be robust to those. They're going to overfit to them. It's not going to help. But in this case, it seems that training on all the data actually improved performance, even if you only cared about performance on your specific setup. That was pretty, exciting to see in robotics because this is a trend we've seen in other fields, but in robotics is really, really rare so far. And again, the improvement gain was almost 50%. Another interesting trend that we found is that actually we were getting to the point where we were seeing that smaller models would underfit this large heterogeneous robot data set. And again, overfitting is normally not something, I think that, sorry, underfitting is not something that we usually see in robotics, because usually the data amount is so small that model capacity is never an issue. And here it was very surprising that model capacity actually was required to kind of soak up all of this diverse robot data. And one big question though was that, great, you had all this robot data from all the robots, was it even needed? You already had all the web data from RT2. Does adding all this incremental, process volume data add anything at all? And the good news is that we did find there was, a lot of these spatial reasoning skills about the motions and the precision of specific tasks, like whether you put the apple on the clock versus near the clock. These were tasks that only adding the robot data would enable the policies to do, whereas the internet data alone wouldn't give you these understanding capabilities for free. As a brief recap then, we've seen attempts at data scaling and positive transfer in two projects that I just highlighted. One was taking our robot data set from RT1, putting it alongside internet data and treating them the same. And then we scaled it up even further by taking all the robot data from many different embodiments. And we saw that in both cases, by treating robot actions and robot embodiments as just another data modality, you did see signs of positive transfer. And again, for RT1, this was great. We do well on the train set and in distribution. For RT2, this was we start to get internet scale semantics. And for RTX, we start to understand spatial precision and concepts like that, which are important for action and for physics. But I think that's where we got to maybe end of last year, I would say, the state of the world. And since then, though, I think there's many open challenges and things which do not work that I want to highlight. One is that VLAs in current training paradigms still overfit to robotics data distributions. What I mean by this is that we take a VLA, we kind of query it on V2A tasks like an internet image prompt, internet prompt, and it does well. We give it a robot image, ask it for actions, it does well. When you try to mix and match across these data distributions for both the visual latent space as well as for the text input space, it doesn't really seem like you're getting a ton of transfer. And this is a very, interesting failure mode, because it suggests that, there are still fundamental issues with how we're doing co-training, how we're mixing robot data with internet data. We also see that reasoning, right? We oftentimes see that reasoning stems from the power of language model backbones, from language model pre-training, and it seems that how you can mix this kind of reasoning process with low-level, physical action reasoning, that's also not, going exactly as expected, because we see cases where, for example, here, your reasoning and planning works well when all the objects are out of distribution, but when you add one in distribution object, such as a cocan, your model starts to revert to what it knows and just immediately, even though it can kind of knows, hey, if I want to hammer a nail, I should use the rock. It's never picked up a rock before, but it's picked up tens of thousands of cocans. So even though it kind of reasons that it should use a rock, it still goes for the cocan. Examples like this are just, they're everywhere, but I think they're not as normally as visible. So I just wanted to highlight this as interesting failure modes. And finally, right, how we actually, the model architecture decision, the design decisions are also not well thought through. Recently, there's a paper actually just from 3 days ago studying how you tokenize and how you represent your action, continuous, discrete, classification, what actual token choices do you use, that I think is a great step in the right direction at making, VLA training more of a science and less of an art. And moving on then, let me just check I'm doing it on time. Okay, great. So the next missing piece then is steerability and promptability. I think this is very interesting because in robotics today, oftentimes we kind of, historically, due to the scale of the relevant policies we've been working with, we've really tried to constrain the amount of entropy and information that can be fed into the policy's input, right? Usually it's just one image, or maybe you frame stack some history of the past images you've seen, and then you convey a goal in the simplest way possible, right? A one hot ID, a very simple, late English sentence, or maybe a goal image. But generally, you're not really expanding the throughput of the bandwidth of your information input to the scale of like an open-ended chat interface as many language models see today. And again, I think we've seen in language modeling how large context windows enable so many great emergent capabilities, such as two-shot learning, such as, really being able to hone down and do chain of thought reasoning and or reflection, all this kind of good stuff that we can't really have in robotics because our input domains, interfaces are just so constrained. And I really want a promptable robot, which you can just say, hey, can you try again? Can you move too far right? You know, can you just adjust it on your next try? We don't have any meta learning like that right now, and it won't naturally emerge by just adding, you know, more of the same types of robot data and more of the same types of internet data. There has to be a paradigm shift in order to get from us, where we are today, to a promptable, steerable robot control model. And here I think, you know, maybe one hypothesis here is that maybe it's language that's the bottleneck, at least language the way we approach it today, right? We've been kind of taking all of the recipes that have worked in other domains and we've tried to say, okay, let's just add language as a conditioning modality for robots. Let's just add language data sets. But this maybe misses a lot of what makes robots hard, right? What makes robots different and unique and an interesting problem to study are the motions, the physics, the causal nature of interaction with the world. And when you try to condense everything into something that, you know, a language model Wikipedia article might look like, maybe you just lose a lot of that in translation. And so towards that, you know, maybe honing in on the motion of robotics is what this work tries to do, called RT trajectory, which takes the idea of, you know, hindsight experience replay. You take the goal image, you turn that into the target for your policy learning, but does that for the motion of the trajectory that was executed. When we collect robot data, oftentimes the end effector, like, you know, or proprioception for all your joint states and your motors are kind of stored, and we kind of just toss all that away when we just save out RGB action trajectories. Maybe you can actually utilize, you know, the motion of what happened in the real world and use that to condition your policy, because you already have this data for free. We just currently toss it out. So what we do in this work is we take that proprioception and effector data, we project it into 2D RGB space, and that just becomes a kind of visual hint, a visual chain of thought, if you will, of not just what you should do. You should, you know, put the chip bag in the drawer, but how you should do it, how you should approach it, from what angle, where you should close, how you should avoid obstacles, at what depth and what heights you should be operating at. And then we feed it into an RT1 policy. And what's nice is that even though training this was automated, at inference time, then, you know, maybe getting this trajectory from scratch would have been hard, but the policy is agnostic to what trajectory you give it. It doesn't have to be hindsight. It can be hand drawn by a human. It can be, you can take a human video and do, you know, pose extraction with the hand and then get the trajectory out of there. Or you can even give foundation models, either, you know, generative image models or language models, to go and predict what the trajectory should be. And then that can condition your pre-trained policy, which is only trained on hindsight trajectories. And what's nice here is that we start to see signs of motion generalization, right? This is where you have tasks which have fundamentally, maybe they're operating at different heights or different motions, just combinations of state action transition, which were just never in the training data, which has been traditionally hard for some of our policies, which were just kind of overfit to pick up the Coke can and that's all I know. And you can't really generalize to Coke cans and vastly different motion profiles. But we start to see that here with tasks such as swiveling chairs or folding towels or picking objects up from the chair at a very low height. But most interesting for the topic here is that this was the first project I worked on, at least, where I really got some kind of shadow or some hint of, I felt that prompt engineering was possible. Here, we'd sometimes try out, you know, evaluations in very different settings, in like a home setting, like an IKEA-like setting with dark wood furniture at different heights, and the robot would sometimes be able to generalize these out of distribution settings. But then just by drawing a prompt trajectory differently, the human can kind of learn the failure modes, the eccentricities of the robot, and just by, like, you know, a trained operator could then learn to draw better trajectories and then start to zero shot new tasks. Again, this was no other policy that we have today, where the input is always something as simple as, you know, hey, pick up a Coke can, pick up a Pepsi can, close the drawer. Going from that to, like, you know, hey, you're in this brand new setting, the drawer is going to be 5 centimeters lower than you're used to, and there's also clutter. Can you go and do that? Like, there's no way any policy could be responsive to that. Yet with trajectories, it seems like sometimes we would get that. And concurrently, it's been really great to see over the past 6 months, a lot of other works also kind of adopt similar paradigms using, you know, point tracking, optical flow, using other kinds of motion representations to also have, you know, touching upon the same idea, is that what makes robotics unique? It's physics, it's motion, it's trajectories. Maybe adding this information to our foundation models can unlock things which language cannot. Which is very excited to see, but I think overall it's still very nascent, and none of these methods have been scaled up to the level of, let's say, a 55 billion parameter vision language action model. Next up, though, one other interesting question I was asking, you know, maybe a year ago was, I have all these rights of language. In the section of this section, right, was like, what can we do beyond language? But maybe language was not the problem, just the way we were using language, that we're using language in too simple of a way. And if the language was more grounded in motions and physics and what makes robotics unique, if it would be more hierarchical and granular, we could get the benefits. And so in this project called Archie-Hierarchy, we would kind of do a chain of thought prediction where you turn the PIC-COCAN, the very abstract, very like long horizon task, into intermediate, very grounded language motions, like move your arm right and rotate it clockwise and then close your gripper, into like language that's very grounded towards very short horizon actions. And again, this can kind of be viewed as like chain of thought, still using language as the chain of thought medium, but doing it in a way which is much easier than perhaps the generalize. And what's interesting then is that this unlocked learning from a category of tasks we had been collecting for over 6 months that no other policy was able to use that data from because they were just so hard. So it's kind of like tasks related to the serial task where there's like a small gap, you have to put a bowl and you have to push a lever, and then there's this like cluttered thing of oatmeal packets, and it's like a slightly more dexterous and precise than the task we'd seen before, but policies were just really struggling to kind of work at the entropy of these systems, which was just a little bit more complex than before. And then these language motions are what unlocked the ability to work on those types of tasks. And talking about like pumpability and steerability, we also saw that having interventions in language of, hey, actually you're doing the right level control. It was just your intermediate plan of translating closed a pistachio jar. You wanted to move up when you should have moved left. Humans could correct this in a dagger-like setting in a much more efficient manner than it would have taken for low-level action interventions. And this was a way to kind of scale up this chain of thought level improvement where you don't always need to make your, iterate at the action level, which is the most expensive level. Maybe sometimes you can, intervene at the language motion or hierarchical planning level. That was also kind of steerability and probability that were the rare pieces that I saw. And to kind of summarize here, RT1 and RT2, even though they were scaled up so much, they were still shoving together all of the foundation model knowledge, all the large data sets through a very narrow bottleneck of simple language instructions. And by widening that kind of bottleneck via either things like time-centric trajectories, via motion-centric representations, or even via language, just better language, seemed to unlock more of the intelligence that's contained in these internet-scale foundations. And the question here becomes is that I view these projects kind of as proof of concepts. I'm very excited about the results, but again, we haven't scaled them up yet to the full internet scale. And the question is maybe to scale them up to a full vision language action model, maybe we need more robot data. And my hot take here is that actually this is not a call to action for me to, a lot of companies, for example, right now are convinced that algorithms are solved, it's just data, and maybe this slide would have suggested that, but I think we don't actually know what kinds of robot data you need. And so if you prematurely try to scale, deploy robot and you were connecting were not correct, maybe sometimes that wouldn't have been a recoverable mistake. So again, I don't think I'm suggesting to not do that, because I think we definitely need to do that, but I think there's also work that robot researchers need to think about on, can we figure out the right types of modalities and data sets and tasks and skills and labels that we need when we go about collecting these like society scale data sets. And finally then, I think one missing piece is scalable evaluation, right? This is, I think, generally a problem throughout all of AI right now. We see that all of these different benchmarks and leaderboards are oftentimes a lot of hype these days because they're very easily gameable. But they're good attempts, I think, at least in foundation modeling broadly, to try to capture various representations of capabilities that we want. And the challenge here, however, is that all AI models across the broadly the field are everything wants to be a generalist these days, right? And that's a very high claim. If your generalist model can do everything, how do you back up rigorously that you can actually do everything and be robust at that? And I think this is clearly already an issue in foundation modeling, but I think things like these ELO-based leaderboards or just getting these models out and deployed in open source or even as close, source APIs, these are ways where you can just leave it up to, the court of the public to kind of say, hey, are your models actually good? And in robotics, this is kind of hard, right? Because robotics target physical data distributions. And it's not really clear whether or not some representative small set of evaluations can capture all of the properties you want to measure, or if there's just a lot of stuff that you need to do before you get to a product that's out. But I think regardless of what the answer is, the problem is very clear. And the problem is that as our policies within our team at Google DeepMind have scaled, the amount of evaluations we've had to do have also scaled, right? And I think this might not sound like a lot, 3,000 or 6,000 trials, but if you consider that each trial can take up to 10, 15 minutes, this is quickly going to become intractable if we add another order of magnitude to what we claim our policies can do the next year or two. That's just not going to be tractable for any industry or academic lab. Maybe one way is we can decompose the kind of attack space of the claims you want to make about these robot foundation models and break them down into particular axes that are meant to represent policy generalization that encompass properties that we hope to measure, such as maybe different backgrounds or adding distractor objects and clutter or changing lighting conditions, adding new objects, etc. And maybe we can measure generalization gaps from our training set to our test set. We did this in the real world, and we indeed found that maybe some of these like axes of generalization, these factors of distribution shifts, were harder than others, and would have these kind of scaling curves as you kind of added more of these to your training. But I think this was kind of just an initial kind of attempt at codifying or formalizing what it means for your robot foundation model to be a generalist foundation model. And it's definitely a challenge now because every new foundation model robot policy that comes out kind of has to do all this on their own again and define their own evals and define their own benchmarks, and it's just kind of hard to compare apples to apples in today's academic landscape. Maybe another path, however, is of course using simulation. And today there were so many great talks on world models in sim, especially for AV and in robot manipulation. It's been a bit harder because manipulation, right, with context forces and physics and visual distribution shifts, and oftentimes data sets are very tuned to one limited setting, which raises the bar for how realistic the sims have to be. This has been an ongoing challenge. So an insight in our recent work here called Simpler was that maybe you don't need a full fidelity digital twin in order that you would need for sim 3.0 training. Maybe all you need to do is optimize for correlation between the ranking of policies in sim and how they would rank in the real world if you had evaluated them in the real world. And by doing this, we would try to just get a minimal viable sim that gets you a useful signal of which checkpoints you should use, which kind of policies you should devote your very expensive real world evals to. And again, I don't think it's perfect, but I think it was working well for various classes of generalist robot policies that we were operating on, such as RT1, RT1X, RT2, etc. And maybe, again, a shout out to concurrent work or kind of related works, right? I'm the Prism one related today from Alex, Unisim from Sherry, also Genie, which is a latent action conditioned video diffusion model from Google, DeepMind. These are all kind of, I think, directionally where we would want to go for seeing if these kinds of approaches can also act as good offline policy evaluation. And my hot take here then is that I think despite all of these great progresses, I think real world evals will always be the gold standard. You can never replace them. I think these evals, offline evals can help you decide which, how to spend your limited bandwidth for real world evals, but it won't replace them completely, right? And then so if you actually need real world evals and you need them at scale, that becomes a very challenging problem, right? And it's perhaps one that will be solved by products deployed in the wild where you actually get scaled eval from actual user deployments, like people actually using your robots and your robot policies. And finally here, I'd like to talk a bit about maybe what this means for what we can think about for how we can predict the next year or 2 years of what my robot foundation model might look like. And the first one here is a recap. We talked about positive transfer and the scaling laws of robotics as we increase our data sets and our model capacities. The bleeding edge here from what I talked about today, I view them as the vision, language, action modeling paradigm, and a lot of improvements in process embodiment training on many different types of robot data. Here, this is my grade, again, just my own opinion. I would give the field a 6 out of 10. Is it how much we progressed and how much remaining kind of unknown unknowns we have. I think, as you saw, the failure modes, we're still overfitting. It's still, BOA training is still more of an art than a science of your data training mixtures of how you go about doing that, your action tokenization of decisions. And I think there's a lot of science that still needs to happen here. For steerability and promptability, again, here we talk about going beyond language. Let's think about motions, let's think about trajectories. Here, I would say the field's at a 4 out of 10, because I think while we've had signs of life, maybe sparks of what could become a promptable or steerable robot learning paradigm, none of these have been scaled up to a large scale, and we don't yet know what kind of data requirements or kind of bottlenecks that will occur when we do try to scale these methods. And we don't know if these will scale to more dexterous embodiments such as humanoids or consumer robots. And finally, for scalable eval, again, maybe we can think about generalization or simulation. I would score this at a 3 out of 10, just because we oftentimes don't even know what we should be evaluating for, right? Even before we can design the eval, we need to kind of set up the paradigms, the structure, the formalisms, all of that is still kind of very ad hoc, and it's done on a per project basis almost. And so definitely in the future, I hope that maybe either concerted efforts or just, by bringing robot action prediction and low-level control closer to foundation modeling, these problems of evaluation can also become more homogeneous. With that, then I'll take these final, last points that we just saw, why I gave these ratings. Maybe we can try to predict what solutions to these might be. This is, I would say, what might happen in the 2025 to 2026 horizon. I think the first one is that, once we understand PLAs better, once it turns into a science and it's not just an art, I think maybe robotics research will also start to split into pre-training and post-training, just as foundation modeling has. Once you have access to very robust starting points of foundation models from, maybe from Google DeepMind, maybe from OpenAI, from other companies, once you have great starting points, then post-training your robot will become more of what your daily cycles are going to be looking like as a practitioner or as a researcher. For robot-specific data, again, I think robot data engines, again, if you're really thinking about scale deployments at a society scale, here I think is where industry and startups will be able to contribute a lot to the field. And what that's going to look like, we'll see. But I think the race is really starting up this year with so many startups and exciting new companies being formed. And then finally, for evaluations, with all of the amazing progress we're seeing in video modeling, again, I think I'm really excited to see what the action condition variant of these world models will look like. How well they'll be able to model out of distribution behaviors and not just in distribution training data. Because I think for evaluating robot policies, you don't just want them to be aesthetic or realistic. You want them to actually measure these long tail of very rare events, or you want them to model contact forces and physical causality, which may not always correlate to aesthetic pre-training video YouTube data that they maybe were trained on. As well as, of course, product deployments. So I think their evaluations is another setting where we'll see industry and startups contribute to. Those are, again, just my own opinions, but I think I'm very excited to see how the field of robotics research evolves. With that said, thanks for your time. Reach me on the email here, and I'll share the slides after, but thanks for your time.
Very much, Ted, for the great talk. There's already a question. You go ahead.
You mentioned some of the dimensions of the product, something like that, something like large number of these or maybe a company has so how do we go about knowing what kind of maybe actually we kind of arguing so much might actually the model performance, but certain companies for the maybe using a certain range of power from demonstration. Is there any scientific support on that?
So I guess the question here was, with texture randomization being kind of one axis of generalization, a distribution shift that seems challenging, are there maybe methods or is there any data points we have on how to address that? I think it's also, there have been some works on data augmentation for robotics, maybe in a semantic fashion, where instead of just broadly domain randomizing, just random textures, actually using semantically relevant textures of what's actually appropriate. You don't want a neon random RGB wallpaper in your home. You want wallpapers that are actually seen in people's homes. I think this is still very nascent, but I think there's already been very good results of people pushing up on these generalization settings with methods like diffusion models for innate.
Other questions? Yes, please.
Yeah, I was wondering, are you saying video data, real data, simulation data, they're all contributing or if you have to pick one, which one would you go for? Or is there a transfer between, or it doesn't even matter?
Yeah.
In your representation, like where you look at.
Yeah, absolutely. So the question, I guess, is video data, sim data, real data. How do we view? Are they all equal? Do they transfer? My sense is at least based on the last few years. Again, real data is absolutely king. So if you offer me the same quantity of real data versus sim versus video, I'm picking real any day of the week. However, then maybe at some point there will be diminishing returns, or maybe if you offer me 1,000 times more or 1,000,000 times more sim or video data compared to robot action data, then maybe the trade-off starts to become different. But in the past, I would say that's also not a very good predictive measure of what might happen in the future, because in the past, again, the robot kind of foundation model policy capacities were so small that if you could only kind of operate over the scale of 100,000 trajectories, then you would of course just operate on 100,000 real trajectories. You never had the opportunity to be operating at the scale of an internet scale VLN, where you did have the capacity to consume 1,000,000 times more sim or video data. And I think we have the opportunity to do that in the next year or even now.
Yeah, there was a question here in the front.
Thanks for the presentation. You were talking also about what's missing from the robotics and the vision, the language, and everything. Physical sense, physical sensing. People born blind, they can language instructions and physical interaction, they can still learn limitations that
Yeah, great question. So the question here was, physical touch, right? Sensing. This is so important for humans. How about for robots? I think my sense here is that, I kind of put two columns of like what could make robots steerable or what's missing from foundation models that's unique to robots. I would definitely put sensing and other modalities here as well. The reason I think maybe it's a little bit farther off, or for me at least not a top priority, is that I think just grounding the idea of temporal motion into putting that into visual language latent space, if that is already so hard, then adding a completely new modality like touch sensors, where you don't have a lot of data, where it is noisy, where it's so different from internet data, that's going to be even harder. So if we can't even add trajectories of motions, then adding sensing data might be even harder lift. So that's why, for me at least, my aim is to try to make some progress on hitting the motions, the physics, the trajectories first, and then sensing maybe, I think, hopefully that'll tell us how we should approach sensing as well.
In the interest of time, let's have two last questions. So I see two hands. You can start in front and then other questions.
The interface between the higher level module and the lower level module is what language. Does it necessarily need to be language or would it not?
Yeah, great question. So the question here is that in this RT hierarchy work, the interface between the high level planning and the low level control was this like low level language motion. And does it have to be language? And yeah, absolutely. I think there's many other kinds of representations you could use. For example, even these trajectories is one, right? Your high level plan could be like, hey, how do I swivel the chair? And then the interface is this like RGB like curve. But I think there's definitely a lot more. Language is just a natural one where you could hope to get a bit more transfer from chain of thought in non-embodied domains. But great point.
And the final question.
Yeah, so I have a question around generalization versus I feel like designing about something rather than the internet scale data will still be seen as an integration part within the data platform. What is your thought about any architectural pieces that are referenced to have algorithms without relying on backwards patterns?
Yeah, the question was interpolation versus true out of distribution generalization and reasoning. Maybe oftentimes when we claim we're generalizing to new objects or light conditions, it's actually just interpolating the data that we already saw. And definitely I think I think here, right, when I define emergent, I try to embrace this by saying that emergent doesn't mean that it's not present in any of the training data and it's emerged magically. It's that it was in the data, but internet scale data is too much for us to codify. So it's just emerging, like we're finding out what was in the data basically, right? Like we're finding out what's in the data and now it's being projected into the robot action space and we're seeing what has successfully projected. So I think again, I don't even know if we need necessarily to solve like true generalization in order for robotics to work well. I think if we're able to solve like just interpolation at scale, that's in a very like, you know, predictable fashion, I think I would be already happy with that in terms of getting general purpose robots. I think, but beyond that, for AGI, I know it's a loaded term, yes, probably.
Okay. Sorry. So let's send the speaker again. And we have our final speaker, Li Chen. So briefly introduce him while he's preparing. Li is currently a researcher at OpenDrive Lab in Shanghai AI Lab. His research interests include autonomous driving and computer vision. And he's a recipient of the WAIC Yunfan Award and of the Best Paper Award at last year's CiviCrowd with the UniAD paper. Welcome, Lee, and the scene is yours.
Thank you for the introduction. Hello, everyone. My name is Lee, and I'm from OpenDrive Lab at Shanghai Lab. And my talk today will be visual models and foundation models for autonomous systems. Okay, let's start. Okay, so we are living in a very complex world. Like we have very complex teaching indoor houses, and we have very complex factory scenarios, and we have complex outdoor environments. Like the picture I took today outside of this simulation center. So we have. Okay. And we live in the world, but nowadays we are building the robots and autonomous vehicles, and we call these systems as autonomous systems. And we would like them to behave like humans, to act as an artificial general intelligence. Like we have humanoid robot, we have robot arms and robot dogs and robot vehicles. So these autonomous systems, they receive multimodal context, including sensing information or very high-level commands from humans or drivers or whatever, and they reason the world and they make actions and they interact with the world. So in a more formal way, everyone like this figure. So the environment gives the current state to the agent, and the agent do the action, and the environment then returns the next state and the reward. This is a very traditional figure in reinforcement learning and policy learning. And in reinforcement learning, people find that exploration space is too high, and they want to make a world model to represent the environment, to select some very complex concepts and model the relationships between the agents and the environment, and to represent the whole system. So the world model typically has a memory component that makes predictions about future based on historical information, and humans can train another simple and very shallow controller or policy network with an internal world model. This is a very initial definition of world model we are talking about today. So as Yang said, this is a possible autonomous machine intelligent version, and today we are talking about the world model and foundation model. So this is a history, and we get very traditional works like Dreamer series and some presidential papers. And especially in recent years, like in last year and today, we can see very popular and fascinating works like general world models from Tesla in last year's CVPR workshop, and Gaia 1 from Wave, and Jenny and Unify and Unison. This model also build a world of autonomous driving systems and some robot systems from large-scale videos. And today we are questioning about what the foundation models for our robots and autonomous vehicles. Actually, some may claim that like video predictions like Sora, they last year released this year, and some large language models. Some may ask if this video prediction model and large language models can behave like a world model for autonomous systems. The answer to us, or to me, is no, because they have very bad hallucination problems, and some you can see from these two figures in the left part, and you can see some research papers in ACL or some NLP groups. They claim that these large language models can behave very badly about some basic rules or some real world common senses. So the question is what we should do to build a world model for these autonomous systems, or what is the foundation model for these systems. So as some speakers mentioned today, so the foundation model has to be trained on large power data, and they should behave very generalizable ability, and they can be fine-tuned or prompted to diverse range of downstream usage, and they generally has some self-supervision training strategies. However, there are some takeaways about these autonomous systems, like they have label data for one specific task, such as image classification or image segmentation, and they are optimized text-wisely, and they are supervised learning. But for our visual world model and for the foundation models, we need to train our model with raw data, and we need to incorporate the model with world knowledge. So we need to train our models with self-supervised manner. Unlike presenters speak lately today, they show a lot about vision language models or vision language action models. I personally will focus more on the reputation learning or the foundation models. So I will give talks about these three parts about data and model and applications. So basically, I will talk about how we can find large corpus of data, especially for autonomous driving, to help our effective generalization. And how can we design a very effective world model with intricate world knowledge with self-supervised learning. And in the end, I will try to answer what the abilities of the world model in autonomous driving. So this is work of from a group and some collaborators from like Compound University of Science and Technology and Tübingen University of Tübingen. And this is the highlighted work will be presented in Thursday, and you can talk to us then. So a very quick overview. This is a very large video prediction model on web scale driving videos, as mentioned by NJ, and it enables the very great generalization across a wide spectrum of domains and tasks. So this is a dataset, and we have a model, and in the end, we have multiple tasks for downstream demonstration. First, data. So as you can see, we have many datasets in last years. So we have Kitty, Arborverse, Waymo, and Nuisance, etc. So they are very relatively small scale, including 5 hours videos or sensor data in Nuisance and about tens of hours data in Waymo or Arborverse. These are very small scale for training a very generalizable world models, since they are collected in a specific region, like Nuisance is collected in 3 cities, and Waymo is most of the same scenarios in Waymo is in the Bay Area. So what we want to do is to find a large corpus data to train our very generalizable model. How to scale up our data. So this is a very good attempt. There are some good attempts in the industry, like in Tesla and Wave. But what we want to do in our academia is to find a very large-scale public dataset and build our own world model to show the ability of the world model to do some frontier research. So in our group, we developed the largest public driving datasets. We call it open OpenDB, which stands for Open Driving Videos, and it contains over 700 cities and regions and over 2,000 hours compared to other public datasets. So basically, we collect data from YouTube, such as similar to the large language models. They collect data from the website, and we feature these data sets with very diverse geography, weather things, and we do not have labels for these data sets, so we have to find a self-supervised learning way to learn the one model. So some status it has over 2,000 hours because we also include some public datasets in our own datasets, and it covers more than 700 areas, and you can find the datasets in our GitHub. It is shown as a YouTube link, and you can download them in your own drive, about tens of terabytes. So to download this data, we first manually screen all YouTubers with very high quality driving videos, and we select those videos and we annotate. We discard those low quality data such as distorted frames and black frames. These are also some driving tool instruction at the beginning of the videos and some description note at the end of the videos. At the end, we want to add some annotations, especially the linguistic descriptions about the videos. So we manually fine-tune a multimodal model. Predict2 is very Predict2 we fine-tune the Predict2 to the driving scenarios, and we pair the YouTube data with the fine-tuned multimodal model, and we can get a paired textual annotation and and the videos. The textual annotation includes a high-level command such as go straight or turn left, turn right, and some context to describe the scenarios. And okay, so after we can get the data, it has the large scale data in the driving scenarios, and we can train a very generalizable video prediction model. So the video prediction model is based on image generation model as stable diffusion XL, and we transferred it into a high capacity video prediction model. So this is the first stage. We trained the image diffusion model based on our OpenDB YouTube data, and we can condition it on some linguistic descriptions and commands, and we can then transfer it into a video diffusion model by adding some temporal denoising layers and some temporal reasoning blocks. And specifically, we can add some core designs to make it generate very high fidelity videos. So first, we integrate some temporal blocks to between the spatial attention layers to make very sufficient spatial temporal interactions, and then we also in the attention layers we design some decoupled spatial attention to efficiently model the long-range modeling about the x-axis and the y-axis in the image. And then in the temporal layers, we add some causality masks to predict very coherent predictions, and also more importantly, we need the causality masks to avoid some causal confusions in the temporal dimension. So I just gave some basic methods. You can refer to our paper, and we just quickly go into our results. This is a very concise comparisons about some image or video diffusion models 2 hours. We can get very decent zero-shot video predictions on bouncing datasets. And other text or downstream applications include language condition prediction, such as we can condition the model with different high-level fonts or very specific descriptions, such as a parking lot or some high-level commands like turning into the mountain, and it can generate some counterfactual results. So we can instruct the future with free-form text. And besides text, we can also fine-tune our model to action condition. So it behaves like the simulation in this task. So basically, we fine-tune our model on new things, and we can inject the model with the trajectories, and it can predict videos based on the conditioned trajectories. So basically, it simulates the future differently conditioned on the given trajectories, but there are some other conditions, and we like angles or velocities and some action command. These are not incorporated in this work, and we will introduce shortly. And the last question is about how can we apply this for representation learning. And in this work, we freeze Gen80 model, which was a video diffusion model in our work, and we freeze it and add a very shallow, lightweight planner above it, and we can predict the motion planning result. And surprisingly, it achieves very similar performance compared to UniAD, which it only has very limited training parameters, and we can achieve this very quick training time without the ego status. So from this work, we can have some takeaways, some simplistic takeaways, like we now introduce a very large scale available driving data. It has 2,000 hours of videos, and the great diversity ensures the generalization. And for the model, we have a video prediction model conditioned on high-level instruction. And sorry, I'll just. And for the application, we can learn the learned application can be simply trained for profit prediction and some language condition or some action condition applications. As I mentioned, so in this work, we only condition the model with action trajectories, but how about some other conditions we can directly apply in the real world, such as velocity or angles and some high-level commands? And additionally, how about the typical applications such as the rewards for model-based recurrent learning in the traditional pipelines? So this comes the following up work about we introduced about Vista. This is work on Archive, and you can also refer to the paper about some details, and I will just briefly introduce it. So compared to existing driving world models, you can see this is data from OpenDB YouTube, and it has very huge resolution. But the most important thing is here we want to inject the world model with multiple action control modes. Like here we can have angle and speed and the trajectory and bound and goal point. These are all very common conditions in the real world, and we need them to show as a very unified representation to the world model. So this is a typical video diffusion model, like we have initial brain sense conditions or primary brain sense conditions, and we predict the future prediction. And here, this is a special point about Vista is we condition the model with multiple control conditions, like high-level commands and high-level goal point, and we have also low-level conditions such as trajectories, angles, and speed. These multiple conditions can behave very unifiedly to condition the video diffusion model. And here are some techniques we use to make this in real. So to generate a very high fidelity videos, we need to inject some dynamic priors, like we can replace the latent to absorb varying numbers of condition frames, and we use two novel losses to inject some dynamics of weight and preserve high frequency structure features to make this make the videos very high fidelity. And this stage is trained solely on YouTube data. And for the second stage, we train the YouTube data and the nuisance data, which contains the action of the whole suite of action conditions, and we can call train them into a action condition video prediction model. So this is efficiently trained via LoRa strategy, and in fact, this can be trained in several hundred hours, but the second stage we only need tens of hours. And after the second stage training, we can realize versatile contributed condition on the unified action conditions. Okay, here are some results, and I didn't put some existing works results here, but I only put our results. So our model can show very high fidelity future predictions, like the resolution is very high, and we can also regressively condition on the generated frame to roll out very long horizon videos. And the most important part is our zero-shot action contributing. So our action are only available on new scenes, but due to the co-training strategy, we can zero-shot our action on YouTube data. So this is from the YouTube data, but we can also give some high-level commands or very specific trajectories or angles and see, and it can predict corresponding videos based on these actions. So for now, this is water model part, and we now want to see how it can apply into the traditional reward pipeline. From the previous works like Drive W and Drive into the Future, they get the reward from a detection model. So, like they predict the future and they use detection models such as object detection and map detection to perceive the world, and they calculate the collision rate or some distance to the boundaries to get the final rewards. However, this includes additional steps, so we are wondering if we can provide the reward without front-shoot actions or additional detection models. So we resort to the uncertainty method. Here, I show the results of reward about, corresponding to the average L2 error. Though L2 error is not ideal in open loop settings, but for a conceptual way, you can see that lower L2 error corresponds to a higher reward. So it means that the reward indeed captures the conceptions about how to drive very well or reasonable in the complex driving things. So in this example, so you can see that when we drive along the road, you can get a relative higher reward. And in this example, though the red points correspond to some lower L2 errors, because the recorded trajectory is much more smaller or shorter than the green points, but in reward part, we can show that the reward for the green trajectories are much higher. So this shows the reward from our model is more reasonable than the average distance error. So this is a summary about our Vista program. So we can inject all kinds of conditions with very efficiently to make it a real world model compared to the Gen80 project. And for the application of our stochastic diffusion process, we can learn some uncertainty and transfer it into a very inherent reward to help some model-based RL functions. But the reality is that we cannot apply these models in the real world, because applying this diffusion model on vehicles is very time-consuming, and we do not have such large-scale data, like hundreds or millions of data in the industry to realize deployment. And so the next question is, can we have more industry-friendly approaches like data model and text applications? Also, how can we evaluate these models, as Ted just mentioned? There comes another work in our group, so we resort to the LiDAR points. So LiDAR is viable sensors in the industry for many years, and the people have developed some future prediction models based on LiDAR points. And in last year's APR, CMU has also invented some methods about world model turning the LiDAR prediction into a faulty occupancy prediction. And so in our group, we are thinking about the images captures more semantic clues, but LiDAR have some geometric clues. So can we combine them to generate a multimodal world model to get a very strong contextual in both semantics and geometrics? So this is our work about VIDA. So VIDA is actually has some previous namings in both CES and TRI. They are mostly about multi-view stereos or self-supervised designation. So these works are mainly for reconstruction purposes, but they lack of exploration in temporal dimension. And since the reconstruction purpose most focus on the geometric expectation, so they lack the reasoning ability of the environment. But we think if we can condition these models, condition the models on the ego motion or ego planning status, we can turn these models into a world model and also get the reasoning ability of the environment. So this is also a highlight work in the CPR and on Thursday, just beside the Gen80 project, and you can also go there to have further discussions. So I will introduce this very briefly. So for this work, we train a multimodal world model by visual point forecasting, and it actually can both entry and over driving. So the concept is that we input history visual inputs, and our VIDA model, visual point cloud forecasting model, we predict future point clouds, and we can use the pre-trained visual encoders to various downstream tasks. Like we can apply it into detection tasks, and we can use it for prediction models, because we are building some temporal reasoning abilities for the model. And in the end, we can also use it for planning. So the method is very easy, and we have history encoder, but to help the rendering part in the image domain, we need a latent renderer to solve the ray-shaped drawbacks in the image, in the V features. And finally, we have an auto-regressive future decoders to decode the bird's eye view features and decode into occupancy and data points in the future. So these are the results, and as you can see, we inject action conditions in here as future ego motions, and so we can condition this ego motions as a decoder input. And in this example, we can condition this as go straight or turn left, and future LiDAR prediction can behave similarly as high-level commands. Okay, so it can also effectively model relative motion, because we explicitly build the correspondence between LiDAR points and these objects. And finally, we can apply it into entry-level driving, and with the pre-trained VIDA encoders, the Uni-AD model gets much higher performance in all these tasks in the driving stack. So for this part, we have another summary here. So the image LiDAR pairs are very helpful and to capture both semantic and geometric information in the environment. And for the model part, besides the video prediction models, we can also build some bird's eye view based models to effectively model the world. And for the application, the spatial temporary layer, the spatial temporary pre-training techniques improve all tasks in driving and serves as a foundation model. Okay, so how about robotics? So one model in driving is relatively very straightforward, and we can predict future based on the images and the LiDAR points. But how about the robotics? Like Unison, they model the world with very large corpus of data, but the challenges in robotics is that we have very heavy interactions between the robots and the environment, and how we need to build the interactions. And another point is there are more diverse tasks and environments in robotics, such as indoor manipulation tasks or some navigation tasks, but the vehicles are only running on the road. So we are still recording these points, such as we are using visual data and we need to encode the world knowledge, and we are resorting to the representation learning techniques to improve the robotics tasks. So, but the additional point is about the visual world models compared to the driving is that we need to highlight the interactions in robotic applications. So here is the work about learning manipulation by predicting interactions. So there are some reputation learning frameworks in previous works like conjunctive learning or MAE-based methods or video prediction methods. They mainly focus on either high-level semantics or very low-level details. But as I mentioned, we need to highlight the manipulation tasks about the interaction process. So here in this work, we explicitly model the interactive dynamics about the patterns of behavior and the physical interactions, and we can get both the high-level semantics and the low-level details. So this is work about published in Robotics Science and Systems and will be presented next month in Delft. So to realize the objective about manipulation interaction and about the world model. So we have two parts for the modeling part. So one is where to interact corresponding to the objects, and how to interact corresponds to the world model. Like here, in this part, we build how to interact based on two sets of frames. Like for one, we can predict the transition frame with the initial frame and the final frame. And another part is we can also predict the final frame based on the initial frame and the transition frames. These two conditions also help our generalization about the world model. And where to interact corresponds to we need to detect the objects we are interacting. This transition and the future states can make our visual models highlighted with interactions. Okay. And for the robotics application, we do not have very large-scale robotic datasets, so we can only use some public human interaction datasets such as Eagle 4D, and we can build our model, build our representation learning model with VIT encoders and distributed language encoders, and we pre-train them to predict to our two objectives. Sorry. So this part corresponds to the image prediction, and this part is a detection task. So they are for two objectives about where to interact and how to interact. With the pre-trained encoders, we can do some real-world experiments to add a very shallow MLP policy head to predict to learn the policy, and we can also do some complex tasks such as in the manipulation. And we can also refer some objects and ground them in the image. As you can see, we achieve very good performance compared to some existing works. So here are some generalization results about the varying object and the backgrounds. So final part, how about video prediction in robotics? The MPI work also still predicts only one frame, but how can we apply the popular video prediction work in the robotics? So the challenge here is video prediction is hard to determine the transition and the replay. Like in this task, we can only we have very relatively long horizon tasks, and we need to use some large large language models or whatever models to divide these tasks into some subtasks. But how can we determine if our video prediction is finished, or when we should replan the video planner? So in this work, this is a work on the review. So but you can see it on archiving reason in the future lately. So in this work, we learn from the closed loop controlling the traditional pipelines, and we find that based on our error measurement learning and our latent can get very high quality and high quality latents corresponding to these circles, and we can use these very good patterns to determine our replan and the transition stages. So these are findings from the video prediction for robotics, and here's the final conclusion. So for world models in autonomous systems, we can have utilize the visual data to utilize the large-scale videos such and the image that appears to get a very generalized world model by self-supervised learning. And models can be very diverse, including the diffusion models and the bird's eye view prediction models, and we can utilize multiple conditions, and they can also as very effective environmental objections. So diffusion models can be some research-based research, but bird's eye view may be some very friendly formats for the industry. And for the application, the world models can can learn some very good representations, and they can help downstream applications, including policy learning and reward evaluation and diverse driving tasks. So this is a conclusion: visual world models as foundation models for autonomous agents, and my prediction for the future is we can incorporate more large language models or VLMs to the visual world models, and they can get much more stronger abilities, including the language abilities. So they can, in the future, they may behave as the foundation models for autonomous agents. Thanks. That's all for my today's talk. I'm happy to answer some questions.
Yeah, please. Yeah, just one clarification question. Where do you get your data from? Your videos?
Which work?
The first one.
Okay, so yeah.
You get it from YouTube, you said?
Yeah, actually, the full data set has. Wait a second. Sorry. Yeah, so the full data set has multiple parts, so it also includes some public data set, but the main part, like YouTube part, has 1,700 hours of data. So the main part is from YouTube, but it has no labels, and we can get some additional parts from existing data sets.
So that's driving data.
Yeah, these are all about driving data sets, and this is the largest data set we can get. We believe.
And I was wondering, actually, my question is, like, you don't want to. I mean, I guess you want to have diversity of data. Otherwise, if I give you 1,000 hours of highway driving, it's not very useful.
Yeah.
How do you calibrate that?
Indeed, we didn't calibrate, or we didn't choose which data we to reserve. We only reserve data based on their quality. But in fact, there are many highway data on the YouTube, and but in this public data, they also have some very urban complex scenarios, and we believe this actually behave very similarly in the real world. Like people in most times people drive from the highways, especially in the Western countries. But like in China or some developing countries, people can drive in most times they drive in the urban cities. So this is a very natural distribution, and we don't do much balance or about that.
Visual LiDAR. Learn how to train
Okay, so this is the question. The question was how we train this visual lidar, right? So it is self-supervised because we have image and lidar pairs, and we input the historical images, and we predict future lidars based on the conditions. So this condition is unique in during training, and we can supervise the model with the collected lidar data. Yeah. This work was trained in image and lidar paired data set. Okay. So the question was how can we balance scarcity about the dense lidar points? So the way is that we first predict the bird's eye view features as shown here. We predict future bird's eye view features, and we convert it into 40 occupancy in this work. I didn't show here. So we first predict for the occupancy, which was 3D occupancy in the temporal dimension, and we can render the lidar points based on the mechanism we think that the lidar points should cast.
Yeah.
Just
Could you have more?
Yeah, so like most LiDAR samples.
Yeah.
All of those images like
Oh, the question is that did we use surrounding images like 360 degrees views of images? The answer is yes. Yes, we use surrounding images, and we can in nuisance we have 6 cameras for the surrounding cameras.
But each step we have 6 images.
Yeah, correct.
Other questions from the audience? Maybe I can ask you a question. So you are using a lot this BV space, like for the representation. Also, you argued for its utility for building work models, but also for more complex robotic scenarios, like in industrial cases or in home environments, that we can have also some, some objects occupying the same part of the BV space.
Yeah.
Also in driving environments, like you can have like cyclists on bikes, and there can be some intersection. How do you approach this limitation? What do you think about that?
Actually, we didn't do the bird's eye view prediction in robotics because we are mainly doing the image level prediction, and in the driving scenarios we are also doing the video prediction, which are in the image level. So I personally do not believe bird's eye view prediction or image level prediction, which is better, and I can only think about these are very valuable approaches, but in the industry, people are not using now the image level prediction due to its time consuming feature. So, but it is still very valuable to do research to utilize these very strong image generation or video generation techniques these days. And maybe in the future, we can utilize these very strong models, these prediction models in the industry.
Okay, thank you. Maybe a last question because we're a bit behind time. Any other questions? If not, we can thank Lee again. And we switch to the panel discussion.
That's a shit here.
That close.
Yeah, it's mine.
Yeah. I can accept you.
I think we need to put the chairs.
The
over
thing
there.
is that the microphone, they can't be
I see.
used over there,
Okay.
so they have to sit around the table.
Oh, it's a wire.
Yeah, that wire, yeah.
Okay.
Thank you all very much for staying until the last event of the day, which is the panel discussion with our. I think that the panel is very interactive, so we'd like to all of you to start a code over here. And if you don't have any functionality, you can just go to title.com. There's going to be 3 topics, and for each topic, you can the question related to it. And you can also upvote the question that you like. And I try to ask the question to the panel, the question which are the most popular. So maybe let's begin by introducing the panelists with a brief bio. So Andre is the Deputy Scientific Director at Valeo AI and Research Associate at the Astra Inra team working on perception for assisted and autonomous driving. Alex is the co-founder and CEO of Wave. He founded the company in 2017 with the belief that end-to-end AI would unlock generalized autonomy at global scale. Hong Yam is an assistant professor at the Uni of Hong Kong and research scientist at Open Drive Lab. His research focus is on autonomous driving and embodied AI. Christos is a lecturer and senior postdoc at ETH Zurich. The focus of his research is on semantic and geometric visual perception. And finally, Ted is a senior research scientist on the robotics team at Google DeepMind, and he works on problems in scaling robot learning, foundation models, and reinforcement learning. Let's begin with the first topic, which is around the technical challenges around building a foundation model. We're going to talk about data, model, and algorithms, all the good stuff. So let me begin with this first question. One of the assumptions under training a foundation model is that we need to find the recipe, which includes a model architecture, training task, data, and so on, which is computationally efficient and scales well with data and model size. Do you think as a research community, we have converged on the recipe? And how do you ensure that the training task leads to a representation which is general enough and usable for downstream tasks? So who would like to get started on this question?
Given that my talk was on the missing pieces, I would say no, we do not have the solved recipe yet. I think we have very great existence proofs and signs of life that we can get to this recipe in the next maybe year or 2 or 3. But I think we do not have all the missing pieces ready today for either the data problem or the algorithmic modeling problem.
An interesting comment I'd make is that I think we need to go all in on diversity. What I mean by that is, we've seen in the language community that if you train on a data set that is, say, predominantly one task, let's say comprehension, and then you have a little bit of data of something like mathematics, it won't perform very well in mathematics. But if you have lots of diverse data comprehension, reading, I don't know, like I'm not a language person, so I don't know the different tasks. But if you have like 100 different tasks, you know, very diverse and balanced data sets, then you learn these general purpose programs to tasks like mathematics. And so the thing I take from this is that if we really want to build a foundation model which is truly embodiment agnostic, what I mean by that is that it can be deployed on a new robot and not, and understand what that sensor setup can or can't see, understand how that system can operate in a zero or few shot setting. I think we need to go all in on diversity of data and platforms at scale. And I think that's something I'd love to see more of. I think there's a huge gap between the data sets we're seeing in maths today and what it's going to take to make such a foundation model possible.
Thank you, Ted and Alex. I have a question from the audience, unless you want to add something on the topic.
It resonates with Alex. You gave a response which was pretty generic, so just to put things down into perception, for instance, which you're also doing it at Wave. Why is it important, this diversity? Because I was also tracing on that we have driving data, but it's not sufficient. I mean, you still need the internet, the homemade, all these videos to catch all those corner cases that you will never see in driving. And in addition to driving, the thing that crossed my mind recently, seeing this paper Dora, I don't know if you saw it, where they do self-supervised retraining on walking tours videos. So they take videos from YouTube, like 40 minutes to 1 hour, and they do a self-supervised retraining just on one of them. So it kind of made me think also what you guys are doing at Wave, driving a car, and I remember your early days with the Twizy. Why not? I mean, adding to this part, I mean, the pedestrian perspective, right? How does the pedestrian see the road and interacts with it? How does the biker see the road and interacts with it? So it kind of, I think that bringing to this, well, you can not only check it by giving it feedback, but also having the raw data of acquiring some diverse data, visual data to in your environment that your vehicle or your robot will interact with. I think it's quite important. And there's cheap ways of doing that. Of course, we like having them calibrated with LiDAR, with all these things. But we saw with some colleagues, with the colleagues at OpenTrack, that okay, with this open DV tablet, you can do quite a lot of things by exploiting some existing data sets on the side for the actions.
Thank you, Andre. So for the panel question, I'm just going to be democratic there and ask the question which are the most upvoted. Starting with this one with 7 thumbs up, which is a bit spicy actually. So, question is autonomous driving really the best path towards embodied AI? It seems the embodiment is simple and focuses on navigation, minimizing environment interaction. Who would like to take this one?
Okay, well, I wrote a blog on this recently, so please have a read if you want to dive deeper on Wave's website. But look, it's interesting. If you look at the results from RTX and you look at navigation and manipulation data, navigation data improves manipulation more than manipulation data improves navigation. That's a really interesting result. It suggests why this is. I was actually debating this over lunch with some colleagues. Well, why might this be? I don't have any data, but a hypothesis might be that navigation is, tends to be more varied in the visual scene and the dynamic nature of the data, the open set world that we might drive in compared to, say, manipulation or manufacturing robotics, which tends to be more of a closed and controlled ecosystem. But that's one example where I really believe the point that autonomous driving is the most economically viable and possible path to scale data in an open setting. And I think that is what is required to build and enable a foundation model for embodied AI. So for that reason, I can't see, just to look at the counterfactuals, if you look at humanoid robotics, I think humanoid robotics is really like self-driving in 2017, right? There is a very expensive hardware path ahead of us to build platforms, and they're operating in very constrained environments that are a bit like Phoenix in Arizona, like where self-driving started. Or manipulation robotics and manufacturing tends to be in very constrained repetitive tasks. If we really want to build embodied AI, we can't have these constrained and simplified environments. We've got to be exposed to a problem at scale, and I think there's no better opportunity for that than self-driving. My prediction is I think self-driving will enable us to build the first foundation model in a way that we really solve the safety and trust problem. And then we'll be able to take that and generalize it to those other domains in a way that helps them as well. But I don't see another robotics domain that is getting access to as much open set and diverse data as self-driving. And so, when we started Wave in 2017, we wanted to build embodied AI. Actually, we were debating this, and the reason why we went into self-driving is for this reason, because it's economically viable, and is the hardware out there today. There are vehicles literally being shipped in production lines at millions of volume that have surround cameras and an onboard GPU that make it all possible. And so I think it provides the path of least resistance to embodied AI at scale.
Yeah, I tried to argue a bit like against. So I think we need to take advantage of every person's routine and everyday life. And we have, of course, driving as a core part of our routine worldwide. But we also have, for example, cooking, where we can have also current advances in AR, VR, and mixed reality. We can have also massive data of real experts, people, like in everyday indoor activities. Of course, the hardware that we need to basically simulate or construct is not as advanced as you argued. Indeed, for cars, like cars are really robots, if you think about it, that are there for 150 years now. But if we can have access to a huge amount of data also for this different setting, and with this we can hopefully also build better models for embodied AI. So I think that, of course, like I'm more on the driving side, so maybe talking against myself here, but I think that there are definitely also other alternatives that have certain pros, and perhaps navigation is one part, because you hope that you don't even touch the other agents, you don't collide with them. But manipulation is even more challenging, because you have also this more intricate physics, grasping and finding the correct pose, exactly like reasoning about very detailed geometric attributes. So there we can also have more challenging tasks to solve.
Thank you very much, both of you. So moving on to the next question from Dipti, which is: to achieve robust/generalized model, should we focus on obtaining diverse data or on learning techniques for robustness, like those in domain generalization literature?
Okay, the question is, do we need more to learn more data?
Yeah, so the question is about how to build a truly general model. Should we focus on the data part or on the algorithm part?
I would definitely go for the data part. So I will narrow down this question into a technical, or this is an academic conference, right? It's not an expo or whatever thing. So everyone is talking about foundation model. As I mentioned earlier in the morning, there is not a single definition as to what is a foundation model specific to be specific in auto driving. The only two papers that I've ever seen on arXiv, not to mention is accepted or not, as for the foundation model for auto driving, one is the Gaia paper and the other one is a JNAD paper. So the other papers are all discussing word models or foundation models, or how to fine-tune the VLMs into auto driving on new things, which is only 5 hours of data, and which consists of 90% of the things are simply going straight. So this is insane. So this is the reason I barely see papers nowadays. So I will definitely go for the data part, but to put it into real implementation, we really need to have some collaboration to prove, okay, So for the VLMs or LMs, they have approved so the effect of scaling law are to have massive amount of data, and you can show great capability to achieve generalization. But for auto-driving or for the embodied AI, or I would use rather prefer robotics, the term robotics. I've often heard some people, some professors from Jiajun or other professors, even in robotics, they don't have massive amount of data. So that's why they have this concept called data pyramid. So compared to the general vision, where you can easily get web data, billions of data, we really should get some collaboration mechanism to collect all the data whenever you're driving or robotics, and try, at least to try the scaling law in auto driving. So you know what? So the GenAD data set you mentioned, as Jenny mentioned, it consists of 3T of storage of drive. If you have the storage is 3T, and you can imagine, since I'm a little bit clumsy, I'm sorry about that. So since it's released, I think it has been released for 3 months or 4 months. I think there are only a few downloads. So in the academia, so really few people can have the storage or have enough GPUs to train or to even testify the generalization capability. So in my sense, since I'm from the Shanghai AI Lab, it's kind of a hybrid between the university, which is very poor in its resource, but it got great ideas, and between the big techs, it's got great power or resources, but it got pressure in the production, so that it has few space. So I would rather encourage people to contribute more in the data exploration part. I'm not sure I'm making it very clear, but that's the sense.
Just because I agree with you. I just would like maybe to nuance a bit. Because yeah, we've seen that the more data, the better data, the simpler tend to be the algorithms. But yeah, when you're constrained in resources, or if you think of a shorter horizon, I think algorithms is to play with. And kind of speaking also from your standpoint, maybe to resonate with what you said, Alex, you also want an economically feasible solution. So speaking from with the hat of an ADAS guy, we need to deliver things for the ADAS for the cars right now. Well, you want to finance what you'll do in 3-4 years from now, where data will take over. So now the algorithms kind of may have a bigger role. Then, assuming that you have all the data that you want, you still have an algorithm component related to the data itself, to the curation of the data itself, and the filtering. Take Inno-V2. Well, algorithmically, there's nothing new, but the big contribution there is the cleaning up of the data that they did at a web scale, finding automatically what data is relevant for your self-supervised test. And actually, some of the guys left and created a startup for data curation called Lapology. So they said they run a business on that, and it's something useful. Also in LLMs, it's kind of the same thing. The amount of effort that is invested in there, certainly you have the scaling laws, but before you get to reach your data set, there's some certain amount of cleaning that you need to do. And speaking of the long tail of events, because that's what we care of, well, they're long tail, they're rare, so they tend to be dominated by the main modes, but also there are many long tails actually. Right? We call one event that is long tail, but actually there's more of them. So they're not selected properly. If they're properly, they can either become nodes, or they can just be faded out in the data. So there's actually quite a lot of algorithms and know-how to be built into the data itself, such that then you'll have your life easier with very simple algorithms that can just leverage whatever you have in the data and have your very nice one. Yeah, I think one of the interesting things we often debate around is, if we took our current stack and scaled data to infinity, would it just solve self-driving? And I think the answer is unclear. Like, scale of data is certainly necessary, and to be able to build these kind of systems into a product, you do need call it the scale of data to bring these systems out, but is it sufficient? I think the distinction I draw when it comes to working on algorithms is that we should strive, and as a team we often talk about this, is that we should work on algorithmic improvements that will survive the test of data. So what I mean by that is finicky little augmentations to solve things in a low data regime. I think they will be solved by data. If you think about as data does scale, and particularly if you're fortunate enough to be in a position where you are growing it by 10 or 100x year on year, like what we've experienced at Wave, then what are the algorithm challenges that will survive the test of that? Can you build a representation that's aware of something, aware of what it's handle can't see? Can you build a system that increases the temporal context window or something like that? All of these are examples of probably really better ones, but examples of things that survive this.
Thank you very much to all of you for your answers. Moving on to the next question, which is from Anonymous. How will the chicken egg problem of data scaling for robotics be solved? No deployment till they are good enough, which requires large scale data.
I don't know if this will be true or not, but there's a belief right now, at least in Silicon Valley, I don't know how many years I'm from the Bay Area, but that the bootstrapping problem of the chicken or the egg is something that just can be handled by VC checks of the cumulative of like $30 billion. Like you can just get past this problem by just running like paid data collection operations either locally in warehouses or out at paid customer sites, and you can just get enough data, I don't know, million trajectories, 10 million, 100 million trajectories, and just bite the bullet, pay that upfront cost, and then, maybe after that, you solve the chicken and egg problem. I don't know whether this is true or not, but it's being explored right now by probably like 3 other companies in Silicon Valley and around the world. And I think we'll maybe get the answer to whether this approach will work in like 5 years. But yeah, just one data point at least.
I think we've got to find the best way. We're forcing it. I think there's going to be a better way. There are those customers out there where we can ask them and being so required to follow product. One example is driver assistance. Driver assistance allows you to put a system out there where it isn't yet fully robust and it's something you can learn with development and application, but it is a bit of growth. Examples that can allow us to grow it up. I think that's the one we've found a way of being out AI to employ as a driver assistance stack, and the extension to that will allow us to scale data to train and validate a system that can be deployed as an L5 or L4 autonomy system. But I'm sure there are many others out there. That's perhaps a different way of relying on our right.
So I think also there's nothing about simulation, right? And whether we can actually bring humans into our simulation in creative ways, so that, for example, for mapping, there was like this Pokemon, that they gamify the reconstruction or the mapping of like very difficult parts of the cities. Regions. So if we can also efficiently put humans in the loop, I don't have a clear this might be easy, but I think we can also try to make our systems more
Thank you, Business. So maybe one last question on this topic, and we need to move on to topic number 2. The last question is, what role do you see for sensitive data coming from traditional simulators?
Simulations.
for example. So it's not real. So you will be faced being asked all the time. So what's the real question? So that's why I've seen some advertisement from some companies saying that their performance or their effect is more good. It's more realistic than the color, but it's still the demo level. So it's really a big challenge. So the very key techniques behind all the simulations is how to use neural rendering or the Gaussian splashing, especially with the turbulence or the other occurrences or challenges, especially facing different scenarios or cases. For example, the car is moving downhill or going to the or based on traffic calculations. So it's really challenging, even for the neural rendering community itself. So if done it right, you will have this universe in the engine create a lot of safety critical cases. So I would bet that simulation is a very good platform or a very scientific problem. No offense, color has its historical role to provide a very fair valuation platform, but the community really need a way better simulation engine.
So I think there are two main aspects here. One is the rendering quality and the realism of the visual appearance, and this has to do with reflectance properties, geometry, materials, and I think that in this regard we need to look more on the computer vision community grasp the materials. So we are much more progressive in terms of geometry, but I think we need to look more there because there are not really, again, from the data side, not really very good real world data sets especially for outdoor scenarios that model materials, and this can be really important where we have different conditions, for example, wet road with very intense specular reflections and other medium density, medium density, etc. The other side is about the behavior realism. So this is more on the, let's say, prediction, world models, and I think there, the traditional simulators, they have some very nice heuristics, but probably with more advanced and hierarchical and compositional world models, it can bring it to the next level. But I think it's still a very valid baseline.
My friend, I think because so the learning is really hard. Maybe versions like this from here. Well, of course, we had learned and the other units from just that there were several by either. So already we've seen because of the particle framework that you have in Gaussian flattening, you have more and more people that are excited by the physics. I don't know if you saw these Gaussians, and there's a few other papers like that where they insert the physics and they start deforming the objects and introducing the physics there. And if you couple with what we saw in Prism 1, but also in others, rendering simulators, environments that we have there, we'll revisit the notion of simulation, I think, based on that. Because once you have access to actually having an impact on the object and getting the feedback, because there's some physical realism in terms of training, but also validation, we can go pretty far with these types of new generation simulations.
Thank you, Andre and Christos. So moving on to topic number 2, which is about real-world challenges in network AI. Let me begin with this first question. Let's assume we have trained a foundation model. It was trained on a wide variety of data in a big compute cluster. It shows superhuman performance across a broad set of tasks, ranging from perception, prediction, planning, and reasoning, the dream. What are the unique challenges in leveraging this foundation model and specialize it to a particular task and embodiment? Would like to get started on this one.
Speaking at least right now for manipulation, one of the open challenges right now, again, is how exactly do you fit a broad generalist foundation model into a given embodiment while retaining the generalization, the intelligence, the constant transfer that you get from the base model. I think this right now, at least, is very understudied because the data distributions of your in-domain robot data is just so far from the pre-training mixtures that these large foundation models are trained with. And so I think until we can figure out either an algorithm that makes merging these very these data islands that are very sparse together, or you can actually just fill out the data islands with some kind of data that is friendlier for this frontier model, so to speak. I think until we solve that gap, then fine-tuning for a specific robot embodiment is gonna lose a lot of the reasons why you wanted to start with foundation models to start with.
I love talking about engineering. So getting the algorithm right is just a start. I think getting these systems integrated into a robot platform is an enormous task in itself. Optimizing inference, drivers, all of this kind of stuff together, and making that all work seamlessly is an enormous challenge. Building the right safety case allows for fail-safe or fail-redundant pathways, ensures that you have a some kind of whatever your model of safety is in play that allows you to quantifiably measure performance. All of these kind of tasks are really critical. Underappreciated when we talk about getting a system built, but to go from a demo that's we've all done this at a robot demo where it's sort of duct tape and handheld, and it started from command line into a slick product that can be operated with a UI that doesn't require expert training to use, and actually just works not just 99 but 99.59% of the time. This is really what it's going to take to make these kind of systems scale, and something that we've a lot about recently. I like when it comes to inference, I like the opportunity that integrated systems because because there are such great libraries available today optimizing systems, because it's relatively accessible as opposed to robot systems of the old, where we sure we build one ROS and have a really nice message passing system, but you've got so many different nodes that run asynchronously that need to pass with different latencies that pass messages around. The nice thing about an end-to-end stack is it's just one neural network, and you're simplifying this, but your inference node is just modeled up forward. Is the option here.
Also about finding the module that you can keep intact from your pre-foundation model and not touch at all, and finding also the other modules that you might want to adapt to fine-tune where that relates to the task. And also, I think you might need to design that you want to talk to Andre before, like what tasks you need to solve in each case and how you choose these tasks. Of course, like we have heard today that you can try to unify this tasks together and try to blur the boundary between them, but sometimes you have to make some decision, like what your output will be, and then you need to also find to define the scope of your application, right? What is the
target domain, the operational design domain that we want to address. So this can change a lot all these other points of view.
Thank you, Christos. It's actually quite hard to find questions because you're answering questions as they come. So I have to find a question which has not been answered before. And I think I got one. Is there a gap between what students learn at uni and what's required to solve real-world AI problems?
I think many of us are trying to close this gap as much as possible. So trying to stay up to date with the latest developments. Of course, you need time to also integrate, as an academic feature, these parts and still provide them in a, let's say, didactic fashion. But I think that we're trying our best to also provide the resources from the university as much as possible to students so that they can solve real-world, state-of-the-art, cutting-edge tasks. And I think this has also great impact to attracting researchers afterwards, after they finish their studies, both in the academia and the industry, to keep working on these problems and not just change gears or go to more mundane, real, low level applied areas.
The question was for undergrads, for high schools, and PhDs. Undergrad. This was the question. Okay, good. Well, in a previous life, I was quite involved in engineering education at the European level as a student, so we had the same question. Yeah, how relevant is what the engineering students are studying to the market, because there was internet. There was always something. So personally, I'm more optimistic because as time advances and of course the bar is higher, right? It's higher than ever for any job, for anything right now. It's higher than ever. But also, I think at disposal, at our reach, we have students, but also us included, because I think we're continuing to be students ourselves in various aspects of life. And technical is that you have so many resources and so many things you can access to. What I think is one of the most important things is to keep your curiosity alive, whatever the means you can. Because that's what's the most important thing. Well, you will never, as an engineer, it was the case before, and it's definitely the case even now. It does not end at the end of your school. You're always learning, you're always advancing. So, and I think that will not change. Maybe the rate can seem more accelerated, but I'm not sure about that. So I have some meta patterns that are there and that you can grasp on. And I think we have a lot of the needs and so many content that is free, art, code, Cola. I mean, there's a lot of things that are reachable for many of the students, provided that they're able to see the
That's good.
The curiosity is such an amazing gift. Specifically, some of the things that I found really helpful in my experience going through. I've also agree that we're still students, we're still learning, we should be, but I found that outside of the technical research skills, well, some of the things that were really important there was knowing what not to work on as well as what to work on. And
never release their course.
Skill research ideas, making sure you have a portfolio of things in the funnel was really important.
We need some video
during
demos.
my PhD. Giving talks was a great way for me to actually stretch my ideas, because it forced me to put together a narrative. And I found that going out, putting yourself out there to give talks was a great way to learn and to refine your ideas, as well as learning to market and sell your ideas, which is a big part of growing your research base as a researcher, or even growing collaborations and things like that. And then outside of that, I think the complementary skills that I was fortunate enough to do an internship at the most incredible robotics company, Stadio, during my PhD. But that taught me skills from even just coding in a team to building unit tests. And I came back in my PhD repo and immediately flooded it with unit tests, and it just made it a lot better. Anyway, these kind of things to source control, actually doing that properly. Whereas before then, I just didn't bother with my academic code, and again, it was a nightmare. And so all of these kind of skills about how to software engineer, I but those things are important to me.
Thank you, Alex. Moving on to the last topic of the day, which is about large-scale deployment of those autonomous systems, especially in safety-critical scenarios. So let me begin with this first question. Given that embodied AI operates in the real world, we have a responsibility in terms of safety when deploying our AI models. According to you, how are foundation models better placed to solve the long tail of scenarios? Those extremely rare scenarios that we oftentimes only see once in a lifetime, but that we need to perfectly handle.
That's a challenge that I haven't figured out yet. But I think if you make an analogy to humans, right, we got everything. We've seen several green fingers, and we just made media reactions to those cases. So if the large language model, the so-called language model, has some capabilities of knowledge, then the key part is how to transfer those knowledge into the driving cases or to specific driving applications. So then again, we are back into the problem. Our data cannot create the basics or whatever we have seen. So this is why we need simulation or simulation intelligence or whatever. So so my guess is we can bundle with this problem with the new benchmark or data engine to create some cases and see what.
One interesting perspective I've been thinking about, and we haven't talked about this earlier, but is that I feel like actually the progress towards the deployment of autonomous systems that will interact with humans at a society scale, right? You have like, large scale autonomous vehicles. And again, these are also very safety critical systems. But then you might also have deployments of home robots or, with factory settings or other humanoids or whatever, that will maybe not be safety critical, but also will have a large kind of compact space where humans and, the elderly and children and then your pets will be interacting with them. Even if it's not safety critical, it's not life or death. Those are very different types of human-robot interaction than you see when, a human and a self-driving car are interacting in the road, right? So I think it's also interesting to think about whether or not the behavioral prediction problems in self-driving also transfer to HRI within a home or within a, like a retail space, or whether these are different problems altogether.
Thank you, Ted. Yeah, I want to add something.
So it's interesting because also with technologies that are not strictly speaking AI, like cell phones, we see that the whole social behavior of human beings changes. So you can see all of us are now with the cell phone all the time, and this also creates more, let's say, not on the, let's say, pure physical side, but also on the emotional, mental side, different like patterns, problems, but also new opportunities. So we need to stay close and grounded to the end users, and for this we also need to really pinpoint to them and to the community the limitations and not be shy or afraid to show the failure cases. Actually, this can be even better because with the failure cases we have like the loss or the training signal in order to improve and then iterate on the method space and make more advanced and more reliable, more ethics aware models. Very rough. I'm speaking very rough. Of course, it's huge, like components.
Thank you, Christos. And here's the last questions, and we're going to stop torturing the panel. So, final question is, how can we build public trust in deploying learned systems in the real world, considering the potential harm caused by embodied AI? That's one.
Yeah, I think this answer is setting meeting expectations for society, and so everything from the way that we market or communicate or talk about these systems, as at the moment, actually, you know, in the UK, self-driving cars just got legalized through Parliament, and one of the key things in this law was not only the safety requirements in these systems, but also marketing language to ensure that the correct expectations are going to be set with consumers. So that's one point. And then, of course, there's ensuring that we build them not just with performance of but give them a sense of what those boundaries are and the ability to detect distribution or things that go beyond what we can quantitatively that we can operate in, and then building backup mechanisms or things like that to be able to support it. So I think these kind of things are important. You can also talk about it from an experience perspective, like in a self-driving car system, you know, building up exposure to it through, say, driver assistance, or if there's a robotaxi or ride-hailing service, maybe mixing it with you know, other vehicles that human-driven that perhaps aren't limited by snowstorm or stuff like that. It keeps the experience more seamless, and then as the systems get better and they can start to produce a more effective deployment, will start to grow. But I think about that gradual increase with setting the right expectations is what generally builds trust over time. That's one way to think about it.
Probably we used to call autopilot something that just right on the highway. If it was speed constant, you'll have a hard time on the layout and the functionalities that you'll have. We'll feel like a retail fallback from whatever models we have, autopilot in these thing, and I relate so much. I didn't know this part of setting expectations. It was great. But the thing that we need to make right, and it's which is really tough, and I think that you touched a bit on that, is really the evaluation, how to properly do the evaluation, and there's a lot of work to be done there. You take doctors. Doctors make mistakes, but usually you have to become a doctor. You have an exam, kind of everybody knows that this exam is a clear assessment of the competencies of that person. Of course, in time they will get better, but it's kind of enough to have them after all this training, these years of training. You have these exams in for lawyers and so forth. You have some way of certifying that this person is able to conduct the task that is they're supposed to have. So yeah, validation is really important. And then I really relate to your idea that you're proposing, by the way, on having these self-checkers. So having this always mindset of having a sort of beat, well, sometimes it's redundancy, but also groundbreaking checking for the model, checking itself all the time and assessing its performance, and also communicating it to the users in a calibrated manner, because that's also something that to be mindful of. It's also one of the ways to build up trust. Because humans are actually pretty fastly adapting to technology, more than, and I think they tend to adapt faster than we hope for. Like if the car drives well on the highway, they can have more confidence on it than it actually is. And they believe, people can believe that it's more intelligent than it is, and I think there is the problem. I think less worried about the panicking, but more people who rely too much on the competencies of the car. And when you couple it with some bad advertising and over whatever else is exaggerating its actual capability,
Thank you, Alexander. I think we are getting kicked out.
So maybe standard and specifications, and also consensus and the coordination between all the stakeholders, especially industrial stakeholders. So I think these are all important points.
Yeah, I think it's an incredible difficult exercise to answer questions on the spot, and I think the panelists did an amazing job. So let's thank them for that.
Huge thank you to the organizers, so on behalf of speakers, I'm sure all of us here, on the whole team. Yeah. Awesome.
No. I think, yeah, that's all for today's workshop. Thank you all for attending our workshop. Yeah.